Before stars, before space, before the very concept of time, what was there? Science tells a story of a universe born from an infinitely hot, dense state, expanding over 13.8 billion years to form the vast cosmic web we see today. But this story has a profound edge. What existed before the beginning? Could everything have emerged from a true nothing? Or was there a dynamic quantum realm, a sea of fluctuating energy from which reality sprang forth? As we journey from the very first moments of creation to the grand architecture of the cosmos, we find that the universe is not just a collection of brilliant galaxies, but a tapestry woven with threads of light and shaped by immense silent voids. What secrets lie hidden in the largest, emptiest place we have ever discovered? As we prepare to journey millions of light years away to witness this cosmic marvel, let's ground ourselves for a moment. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. Before stars, before space, before time itself, there was nothing. Or maybe something. Then suddenly everything began. In a tiny fraction of a second, the universe exploded into being. It was hot, dense, and full of energy. This is what we call the Big Bang. But if the Big Bang created the universe, what caused the Big Bang? Scientists have searched for answers for decades. They've found ancient light still travelling through space. They've seen galaxies moving apart and time stretching like rubber. In 1964, they discovered a strange glow coming from every direction, a leftover signal from the beginning. But even now, the moment before the Big Bang remains a mystery. Could there have been something before everything? And if so, what? Before we begin the journey, let us know where in the world you're watching from and what time it is for you right now. Post it in the comments below and settle in for a fascinating ride through space. The story of the universe, as understood by modern science, begins not with an explosion in space, but with the expansion of space itself from an incredibly hot, dense state. This foundational idea is known as the Big Bang theory. It describes how our universe evolved from its earliest moments to the vast, complex cosmos we observe today. The theory does not attempt to explain what existed before this moment, nor what caused it, but rather provides a comprehensive framework for the universe's development after its initial state. It is a scientific model built upon a bedrock of observational evidence and theoretical predictions, which has been refined over many decades. The conceptual seeds of the Big Bang theory were sown in the early 20th century, a time of profound shifts in scientific thought. Albert Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity, space, and time. It proposed that gravity is not a force acting at a distance, but rather a curvature of space-time caused by mass and energy. When scientists began to apply Einstein's equations to the entire universe, they found that a static, unchanging universe, as was commonly believed at the time, was unstable. Einstein himself initially added a cosmological constant to his equations to force a static solution, a decision he would later call his biggest blunder. Independent of Einstein's initial preference for a static universe, several scientists began to explore the implications of a dynamic cosmos. In 1922, Russian physicist Alexander Friedmann developed solutions to Einstein's equations that described an expanding universe. His work, however, was not widely known in the West at the time. The crucial observational evidence began to emerge from the realm of astronomy. Vesto Slipher, an American astronomer, had been observing the spectra of spiral nebulae, which we now know are galaxies, since 1912. He found that most of these nebulae were moving away from Earth at very high speeds, indicated by a shift in their light towards the red end of the spectrum, a phenomenon known as redshift. It was a Belgian priest and physicist, Georges Lemaître, who, in 1927, independently derived the expanding universe solutions from general relativity and crucially connected them to Slipher's observations. Lemaître proposed that the universe began from a single, extremely dense point, which he called the primeval atom. He suggested that this atom then expanded and diversified, eventually forming the universe we see. His work, initially published in an obscure Belgian journal, gained wider recognition when translated into English in 1931. The most compelling observational evidence came from the American astronomer Edwin Hubble. Working at the Mount Wilson Observatory in California, Hubble, along with his assistant Milton Humason, made groundbreaking measurements of the distances to these spiral nebulae. By 1929, Hubble announced his discovery. The further away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, provided powerful empirical support for the idea of an expanding universe. If everything is moving away from everything else, it implies that, in the past, everything must have been much closer together. This was a pivotal moment, shifting the scientific consensus from a static to a dynamic universe. The term Big Bang itself was coined in 1949 by British astronomer Fred Hoyle during a BBC radio broadcast. Hoyle was a proponent of the rival steady-state theory, which proposed that the universe was eternal and unchanging, with new matter continuously being created to fill the gaps left by expansion. Hoyle used Big Bang somewhat derisively to describe Lemaitre's theory, intending to ridicule its seemingly abrupt beginning. Ironically, the catchy name stuck and became the widely accepted term for the theory it was meant to discredit. While the observational evidence for expansion mounted, theoretical work continued to strengthen the Big Bang model. In the 1940s, George Gamow, along with his students Ralph Alpher and Robert Herman, made key predictions based on the hot, dense early universe. They reasoned that if the universe started from such extreme conditions, it would have been hot enough for nuclear fusion to occur in its earliest moments, leading to the formation of light elements like hydrogen and helium in specific proportions. Furthermore, they predicted that the residual heat from this early hot phase should still be detectable today, as a faint glow of microwave radiation permeating the entire universe. This prediction, made in 1948, would become one of the most significant pieces of evidence for the Big Bang. The accidental discovery of this cosmic background radiation in 1964 by Arno Penzias and Robert Wilson at Bell Labs provided the smoking gun. They were working with a new horn antenna and kept detecting a persistent uniform static or noise that they could not eliminate. It came from every direction in the sky, regardless of the time of day or year. Simultaneously, researchers at Princeton University, led by Robert Dick, were independently searching for this very radiation, unaware of Penzias and Wilson's discovery. When the two groups connected, it became clear that Penzias and Wilson had stumbled upon the cosmic microwave background, CMB, the faint afterglow predicted by Gamow and his colleagues. This discovery effectively sealed the fate of the steady-state theory and cemented the Big Bang as the leading cosmological model. The Big Bang theory, therefore, is not a description of an explosion that happened at a specific point in space, with matter flying outwards into an empty void. Instead, it describes the expansion of space itself, carrying galaxies and all matter along with it. Imagine a balloon being inflated. Dots drawn on the surface move further apart as the balloon expands, but no single dot is at the centre of the expansion, and the dots are not moving through the balloon's surface, but rather the surface itself is growing. Similarly, in the universe, every point appears to be the centre of the expansion, and galaxies are not rushing through pre-existing space, but the fabric of space-time between them is stretching. This stretching causes the light from distant galaxies to be redshifted, providing the primary observational evidence for this ongoing cosmic expansion. Over the decades, further observations and theoretical advancements have continued to refine and support the Big Bang model. The observed abundances of light elements in the universe, such as hydrogen, helium, and lithium, precisely match the predictions made by the Big Bang nucleosynthesis theory, which describes element formation in the first few minutes after the Big Bang. The large-scale structure of the universe, with its vast cosmic web of galaxies and voids, also aligns with predictions from the Big Bang model, especially when combined with the concept of dark matter and dark energy. While the Big Bang theory provides an incredibly successful framework for understanding the universe's evolution from a tiny fraction of a second after its beginning, the question of what initiated this expansion or what existed before remains a profound area of ongoing scientific inquiry and speculation. One of the most profound and counterintuitive aspects of observing the universe is that when we look out into space, we are simultaneously looking back in time. This seemingly magical ability is not due to any special properties of our telescopes, but rather a fundamental consequence of the finite speed of light. Light, the fastest thing we know, travels at a specific, measurable speed through the vacuum of space. This speed is approximately 300,000 kilometers per second, or about 186,000 miles per second. While this speed seems incredibly fast in our everyday experience, the distances in the cosmos are so immense that light takes a considerable amount of time to travel from its source to our eyes or our instruments. Consider the most familiar example, the Sun. The light we see from the Sun left its surface approximately 8 minutes and 20 seconds ago. This means that if the Sun were to suddenly vanish, we would not know about it for over 8 minutes. We're always seeing the Sun as it was in the recent past, not as it is in the present moment. This principle extends to every object we observe in the universe. The further away an object is, the longer its light has been travelling to reach us, and consequently, the further back in time we are seeing it. To manage the immense distances involved in astronomy, scientists use a unit called the light year. A light year is not a measure of time, but a measure of distance. It is the distance that light travels in 1 Earth year. This distance is approximately 9.46 trillion kilometers, or about 5.88 trillion miles. Using this unit, we can grasp the scale of the cosmos. For instance, the nearest star to our solar system, Proxima Centauri, is about 4.2 light-years away. This means that the light we receive from Proxima Centauri left that star 4.2 years ago. We are seeing it as it was 4.2 years in the past. Now, extend this concept to galaxies. The Andromeda Galaxy, our closest large galactic neighbour, is about 2.5 million light-years away. When we gaze at the Andromeda Galaxy through a telescope, we are seeing light that began its journey 2.5 million years ago. This light originated when early humans were just beginning to evolve on Earth. The implications are staggering. Every image of a distant galaxy is a snapshot from the past. This principle is the cornerstone of observational cosmology, allowing astronomers to piece together the history and evolution of the universe. Telescopes, in essence, become time machines. By observing objects at progressively greater distances, we are effectively looking at different epochs in cosmic history. The most powerful telescopes, like the Hubble Space Telescope and more recently the James Webb Space Telescope, are designed to peer deep into the universe, capturing light from objects billions of light-years away. For example, when astronomers observe galaxies that are 10 billion light-years away, they are seeing those galaxies as they appeared 10 billion years ago, when the universe was only a few billion years old. At these immense distances, we are observing the universe in its infancy. We can see the earliest, most primitive galaxies, which look very different from the mature, well-formed spiral and elliptical galaxies we see closer to us. These early galaxies are often smaller, more irregular, and undergoing rapid bursts of star formation. By comparing these ancient galaxies with closer, younger ones, scientists can trace the evolutionary pathways of galaxies over cosmic time. The furthest back in time we can see with a light is to the cosmic microwave background, CMB radiation. This faint glow, detected across the entire sky, is light that was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for the first stable atoms to form. Before this time, the universe was so hot and dense that light could not travel freely. It was constantly scattered by free electrons and protons, making the universe opaque, like a dense fog. When the universe cooled and atoms formed, electrons combined with nuclei, and the universe became transparent. The light from that moment, now stretched and cooled by billions of years of expansion, is what we detect as the CMB. It represents the baby picture of the universe, the oldest light we can ever hope to observe directly. Beyond the CMB, our understanding relies purely on theoretical models, as no light from earlier epochs can reach us. However, the CMB itself provides invaluable information about the conditions of the early universe, including its temperature, composition, and slight variations in density that eventually grew into the large-scale structures we see today. Different types of telescopes allow us to observe different wavelengths of light, each revealing unique aspects of the universe's past. Optical telescopes observe visible light, showing us stars and galaxies as we typically imagine them. Radio telescopes detect radio waves, which can penetrate dust clouds and reveal regions of star formation or distant active galaxies. X-ray telescopes observe high-energy X-rays, allowing us to study phenomena like black holes and hot gas in galaxy clusters. Each wavelength provides a different window into the past, painting a more complete picture of cosmic evolution. The ability to look back in time is not just a fascinating curiosity, it is a critical tool for testing and refining cosmological models, including the Big Bang Theory. If the Big Bang Theory is correct, then the universe should have looked different in the past, and these differences should be observable. The fact that we see galaxies evolving over time, the presence of the CMB, and the distribution of light elements all provide strong confirmation of the universe's dynamic history, as described by the Big Bang model. Without the finite speed of light, and our ability to measure and interpret it, our understanding of the universe's origins and evolution would be vastly more limited, confined to only the present moment of cosmic existence. The expansion of the universe is not something we can directly see in the way we observe an object moving away from us in everyday life. Instead, scientists infer this expansion from a crucial piece of evidence: the redshift of light from distant galaxies. To understand redshift, we first need to briefly consider the nature of light itself. Light is a form of electromagnetic radiation, which travels in waves. Like all waves, light waves have a wavelength, the distance between two consecutive crests or troughs, and a frequency, the number of waves that pass a point in a given amount of time. The colour of visible light depends on its wavelength. Red light has the longest wavelength, while violet light has the shortest. The phenomenon of redshift is an example of the Doppler effect, which is familiar from sound waves. Imagine an ambulance siren. As the ambulance approaches you, the sound waves are compressed, leading to a higher pitch. As it moves away, the sound waves are stretched out, resulting in a lower pitch. The same principle applies to light waves. If a light source is moving towards an observer, the light waves it emits are compressed, causing their wavelength to shorten. This shift towards shorter, bluer wavelengths is called blue shift. Conversely, if a light source is moving away from an observer, the light waves are stretched, causing their wavelength to lengthen. This shift towards longer, redder wavelengths is called redshift. In astronomy, redshift is a critical tool. When astronomers analyze the light from stars and galaxies, they use a spectroscope to break the light down into its component colors, creating a spectrum. This spectrum contains dark lines or bright lines at specific wavelengths, which are like fingerprints of the chemical elements present in the star or galaxy. For example, hydrogen atoms absorb or emit light at very precise known wavelengths. If a galaxy is moving away from us, these characteristic spectral lines will be shifted towards the red end of the spectrum, compared to where they would be if the galaxy were stationary. The amount of this redshift directly tells us how fast the galaxy is receding. The systematic observation of redshift in distant celestial objects began in the early 20th century. Vesto Slipher, an American astronomer at the Lowell Observatory, was one of the pioneers in this field. Starting in 1912, he meticulously measured the radial velocities, motion towards or away from us, of various spiral nebulae, which were then thought to be gas clouds within our own Milky Way galaxy. To his surprise, Slipher found that the vast majority of these nebulae were exhibiting significant redshifts, meaning they were moving away from Earth at tremendous speeds. By 1917, he had measured the velocities of 25 nebulae, and only a few showed blue shift. This was a puzzling observation at the time, as it implied a general outward motion from our position. The true significance of Slipher's redshifts became clear with the work of Edwin Hubble. Working at the Mount Wilson Observatory in California in the 1920s, Hubble made two monumental contributions. First, he definitively established that many of these spiral nebulae were not gas clouds within our galaxy, but were, in fact, independent galaxies far beyond the Milky Way. He did this by identifying a type of variable star called Cepheid variables in some of these nebulae, which allowed him to accurately determine their distances. Second, and most crucially for the Big Bang theory, Hubble combined his distance measurements with Slipher's velocity measurements. In 1929, he announced his groundbreaking discovery. There was a direct relationship between a galaxy's distance from us and its recession velocity. The further away a galaxy was, the faster it was moving away. This relationship is now famously known as Hubble's law. It can be simply stated as velocity equals Hubble's constant multiplied by distance. This linear relationship was a profound revelation. It was not just that things were moving away, but that the rate of their recession increased with distance. Hubble's law provided the strongest observational evidence yet for an expanding universe. If all galaxies are moving away from each other, and the further ones are moving faster, it implies that the space between them is stretching. It's crucial to understand that this is not like an explosion, where fragments fly outwards from a central point. Instead, it's the fabric of space itself that is expanding, carrying the galaxies along with it, much like dots drawn on the surface of an inflating balloon. As the balloon expands, the dots move further apart, but no single dot is at the centre of the expansion, and the dots themselves are not moving on the surface, but the surface itself is growing. Similarly, in the universe, there is no central point of expansion. Every observer, no matter where they are located, would see all other galaxies receding from them. The redshift observed in distant galaxies is therefore not just a measure of their speed through space, but a cosmological redshift, caused by the stretching of the light waves as the space they travel through expands. As the universe expands, the wavelength of the light travelling through it gets stretched, making it appear redder by the time it reaches our telescopes. This cosmological redshift is a direct signature of the universe's ongoing expansion. The discovery of the redshift-distance relationship, formalized as Hubble's law, provided powerful support for the Big Bang model, which inherently predicts an expanding universe. It showed that the universe is not static but dynamic and evolving. The rate of this expansion, quantified by Hubble's constant, also allows scientists to estimate the age of the universe. By running the movie backward, if we know how fast things are expanding now, we can calculate how long it would have taken for everything to have been compressed into a very small, dense state. Current estimates, based on the most precise measurements of the Hubble constant and other cosmological parameters, place the age of the universe at approximately 13.8 billion years. The universe, as described by the Big Bang theory, began in an incredibly hot and dense state. As it expanded, it cooled. A crucial prediction of this model, made decades before its discovery, was that the residual heat from this early fiery period should still be detectable today as a faint uniform glow of microwave radiation permeating all of space. This ancient light, often called the cosmic microwave background, or CMB, is the most compelling single piece of evidence supporting the Big Bang. It is essentially the universe's baby picture, showing us what the cosmos looked like when it was only a few 100,000 years old. The idea that such radiation might exist dates back to the 1940s. George Gamow, along with his students Ralph Alpher and Robert Herman, were working on the theory of Big Bang nucleosynthesis, which describes how the first light elements were formed in the early universe. Their calculations indicated that if the universe had been hot and dense enough to fuse hydrogen into helium in its first few minutes, it must have been filled with intense radiation. As the universe expanded and cooled over billions of years, this radiation would have stretched to longer wavelengths, eventually becoming microwaves. In 1948, Alpha and Herman specifically predicted that this leftover radiation should have a temperature of about 5 Kelvin, or 5 degrees above absolute zero, a temperature that would correspond to microwave wavelengths. Their prediction, however, went largely unnoticed by the broader scientific community for many years. For the first 380,000 years after the Big Bang, the universe was a scorching hot opaque plasma. It was so hot that electrons were not bound to atomic nuclei. Instead, free electrons and atomic nuclei, mostly protons and helium nuclei, moved independently. Light or photons could not travel far in this environment without colliding with these free electrons. Imagine trying to walk through an extremely dense fog. you can only see a short distance. The early universe was like this, but for light. Photons were constantly scattering off the charged particles, making the universe effectively opaque. This period is often referred to as the photon epoch. As the universe continued to expand, it cooled. When the temperature dropped to approximately 3000 Kelvin, a critical event occurred. This was about 380,000 years after the Big Bang. At this temperature, the free electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable neutral atoms, primarily hydrogen and helium. This process is known as recombination, though it is a bit of a misnomer because electrons and nuclei were combining for the first time, not recombining. With the electrons now bound within atoms, they were no longer free to scatter photons. Suddenly the universe became transparent to light. The photons that had been trapped and constantly scattering were now free to travel across the cosmos without interruption. These are the photons we detect today as the cosmic microwave background. Over the subsequent 13.8 billion years, as the universe continued its vast expansion, these photons have travelled immense distances. The expansion of space has stretched their wavelength considerably. What was once visible or near-infrared light, with a temperature of 3000 Kelvin, has been stretched so much that its wavelength is now in the microwave portion of the electromagnetic spectrum. Its temperature has cooled to a mere 2.725 Kelvin, or about 2.725 degrees above absolute zero. This is why it is referred to as microwave background radiation. The actual discovery of the CMB was serendipitous. In 1964, two American radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Telephone Laboratories in Holmdel, New Jersey. They were testing a new, highly sensitive horn antenna designed for satellite communication and radio astronomy. Their goal was to eliminate all sources of noise from their receiver. They meticulously checked their equipment, removed pigeon droppings from the antenna, and even considered the possibility of radar from New York City. Despite their best efforts, they kept detecting a persistent uniform low-level static or hiss that came from every direction in the sky, day and night, regardless of the time of year. It was a faint, steady signal that they could not explain or eliminate. Unbeknownst to Penzias and Wilson, a group of physicists at Princeton University, led by Robert Dick, along with James Peebles, P.G. Roll and David Wilkinson, were independently working on the theoretical implications of the Big Bang. They had in fact rediscovered the prediction made by Gamow, Alpha and Herman, that if the universe began with a hot Big Bang, there should be a faint uniform background of microwave radiation left over. The Princeton team was actually building an antenna to search for this very signal. Through a chance phone call, Penzias learned about Dick's work, and Dick learned about Penzias and Wilson's unexplained noise. The connection was immediately clear. Penzias and Wilson had accidentally discovered the cosmic microwave background, the ancient echo of the Big Bang. Their discovery, published in 1965, earned them the Nobel Prize in Physics in 1978. The CMB is incredibly uniform across the entire sky, with variations in temperature of only about 1 part in 100,000. This uniformity is a strong confirmation of the Big Bang's initial homogeneity. However, the tiny variations, or anisotropies, are equally important. These slight temperature differences represent minuscule density fluctuations in the early universe. These tiny ripples, amplified by gravity over billions of years, eventually grew into the vast cosmic structures we see today, such as galaxies, clusters of galaxies, and the large-scale cosmic web. Without these initial seeds of inhomogeneity, the universe would be a featureless, uniform expanse of gas. Subsequent dedicated missions have provided increasingly precise measurements of the CMB. The Cosmic Background Explorer, or COBE satellite launched by NASA in 1989, confirmed that the CMB has a perfect blackbody spectrum, exactly as predicted for thermal radiation from the early universe. This was a crucial test. COBE also detected the tiny temperature fluctuations, providing the first clear evidence of the seeds of cosmic structure. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided much higher resolution maps of these fluctuations, allowing scientists to determine key cosmological parameters with unprecedented accuracy, including the age of the universe, its composition of ordinary matter, and dark energy, and the geometry of space. Most recently, the European Space Agency's Planck satellite, launched in 2009, produced the most detailed maps of the CMB to date, further refining these measurements and providing even tighter constraints on cosmological models. The cosmic microwave background is not just a relic, it is a powerful probe of the early universe. Its existence, its black body spectrum, its uniformity, and its tiny anisotropies all align perfectly with the predictions of the Big Bang theory. It provides a direct observational window into the universe when it was only 380,000 years old, long before the first stars and galaxies had formed. It confirms the universe was once hot, dense, and opaque, and that it has been expanding and cooling ever since. Without the discovery and detailed study of the CMB, the Big Bang theory would remain a compelling hypothesis, but with it, it stands as the overwhelmingly accepted scientific model for the evolution of our cosmos. The Big Bang theory not only explains the expansion of the universe and the existence of the cosmic microwave background, but it also provides a precise account for the observed abundance of the lightest chemical elements in the cosmos. The universe, as we observe it today, is overwhelmingly composed of hydrogen and helium, with trace amounts of lithium. The Big Bang theory accurately predicts the specific proportions of these elements, a process known as Big Bang nucleosynthesis, or BBN. This agreement between theoretical prediction and observational fact serves as another powerful pillar supporting the Big Bang model. To understand BBN, we must go back to the very early universe, specifically the first few minutes after the Big Bang. At this time, the universe was incredibly hot and dense, far too hot for stable atomic nuclei to form. Instead, it was a rapidly expanding and cooling soup of fundamental particles: protons, neutrons, electrons, positrons, neutrinos, and photons. The temperature was so extreme, reaching billions of degrees Kelvin, that protons and neutrons could freely convert into one another. The balance between protons and neutrons was primarily determined by the universe's temperature and the slight mass difference between them. As the universe cooled, the conversion of neutrons to protons became less favourable, leading to a slight excess of protons. For every 7 protons, there was approximately 1 neutron. This ratio is crucial for the subsequent formation of light elements. The actual process of nucleosynthesis began when the universe was only about 1 second old and had cooled to a temperature of about 10 billion Kelvin. At this point, the strong nuclear force, which binds protons and neutrons together, became effective. However, the universe was still hot enough that any newly formed atomic nuclei would be immediately broken apart by high-energy photons. This situation is often referred to as the deuterium bottleneck. Deuterium, an isotope of hydrogen with 1 proton and 1 neutron, is the first step in the formation of heavier elements. But at temperatures above approximately 900 million Kelvin, deuterium nuclei are instantly shattered by energetic photons. Nucleosynthesis could only truly begin when the universe had cooled sufficiently to overcome this deuterium bottleneck. This occurred when the universe was roughly 3 minutes and 46 seconds old, and its temperature had dropped to around 900 million Kelvin. At this temperature, deuterium nuclei could finally survive long enough to fuse further. Once deuterium formed, it quickly combined with other protons and neutrons to build up heavier nuclei. The primary reactions during BBN involved deuterium fusing with protons to form helium-3, and then helium-3 fusing with other nuclei to form helium-4. Helium-4, with 2 protons and 2 neutrons, is an exceptionally stable nucleus, and it was the main product of Big Bang nucleosynthesis. The process was very efficient at converting almost all available neutrons into helium-4. Since there was roughly 1 neutron for every 7 protons, and each helium-4 nucleus requires 2 neutrons, this meant that for every 2 neutrons, there would be 2 protons to form 1 helium-4 nucleus. The remaining 6 protons would stay as individual hydrogen nuclei. This leads to a predicted mass ratio of about 75% hydrogen and 25% helium-4. Beyond helium-4, only trace amounts of other light elements were formed. Some helium-3 and deuterium nuclei did not fuse into helium-4 and remained in their original state. A tiny fraction of lithium-7 was also produced, primarily through the fusion of helium-4 and helium-3, or from the decay of beryllium-7. However, the conditions in the early universe were not suitable for the formation of elements heavier than lithium. The universe was expanding and cooling too rapidly. By the time heavier nuclei like carbon or oxygen could have formed through further fusion reactions, the temperature and density had dropped too low, and the nuclear reactions effectively ceased. All the heavier elements we see today, from carbon to iron and beyond, were forged much later in the cores of stars through stellar nuclear synthesis and supernova explosions. The remarkable aspect of Big Bang nucleosynthesis is the precision with which its predictions match observations. Astronomers measure the abundance of these light elements in the most pristine ancient environments they can find in the universe. This includes distant quasars, which are powered by supermassive black holes in early galaxies, and old metal-poor stars in the halos of galaxies. These environments are chosen because they have undergone minimal stellar processing. That is, their material has not been significantly altered by the nuclear fusion processes occurring in stars, which would change the elemental compositions. The observed cosmic abundance of helium-4 is consistently found to be around 24 to 25% by mass, which aligns almost perfectly with the BBN predictions. The abundance of deuterium is also a crucial test. Because deuterium is easily destroyed in stellar interiors, its primordial abundance is a sensitive probe of the conditions during BBN. Observations of deuterium in distant gas clouds, illuminated by quasars, show an abundance that is also in excellent agreement with the Big Bang model's predictions. Similarly, the observed amount of lithium-7, though subject to some complexities in measurement and theoretical understanding, generally falls within the expected range. The success of Big Bang nucleosynthesis in predicting the primordial abundances of light elements is a powerful validation of the Big Bang model. It demonstrates that the universe was indeed hot and dense enough in its early stages for these nuclear reactions to occur, and that it cooled and expanded at a rate consistent with the observed cosmic expansion. Furthermore, the precise values of these abundances are sensitive to the amount of ordinary matter, or baryonic matter, in the universe. The agreement between BBN predictions and observations allows cosmologists to determine the density of baryonic matter in the universe, which is found to be only about 4 to 5% of the total mass-energy content. This finding provides independent evidence for the existence of dark matter and dark energy, which constitute the vast majority of the universe's mass and energy, respectively. In essence, the light elements serve as fossil records from the universe's infancy. Their measured proportions across the cosmos are a direct consequence of the physical conditions that existed just minutes after the Big Bang. The fact that the Big Bang theory can explain these abundances with such accuracy provides a compelling and quantitative confirmation of its validity, reinforcing its position as the leading scientific explanation for the origin and evolution of our universe. The very first moments of the universe, immediately following the Big Bang, represent a period of extreme conditions where our current understanding of physics is pushed to its absolute limits. While direct observation of this epoch is impossible, theoretical models extrapolated from our knowledge of particle physics and general relativity allow us to paint a speculative yet scientifically informed picture of this unimaginably hot and dense beginning. This period encompasses timescales so brief they are difficult to comprehend, stretching from the Planck time to fractions of a second. The earliest conceivable moment we can discuss is the Planck epoch, which spans from time 0 up to approximately 10 to the power of minus 43 seconds after the Big Bang. At this incredibly tiny fraction of a second, the universe was compressed into a space smaller than a proton, and its temperature was an astounding 10 to the power of 32 Kelvin. In such extreme conditions, all four fundamental forces of nature — gravity, electromagnetism, the strong nuclear force, and the weak nuclear force — are thought to have been unified into a single superforce. Our current theories of physics, particularly general relativity, which describes gravity, and quantum mechanics, which describes the other three forces, break down at this scale. To fully understand the Planck epoch, a complete theory of quantum gravity is required, which scientists are still striving to develop. Theories like string theory and loop quantum gravity are attempts to bridge this gap. As the universe expanded and cooled slightly beyond the Planck time, gravity is thought to have decoupled or separated from the other three fundamental forces. This marked the beginning of the Grand Unification epoch, which lasted until approximately 10 to the power of minus 36 seconds. During this period, the strong, weak, and electromagnetic forces were still unified into a single, grand unified force. The universe was still extraordinarily hot and dense, but the temperature had dropped enough for distinct physical properties to begin to emerge. This epoch is also where the theory of cosmic inflation is often placed. Although inflation will be discussed in detail in another chapter, it is important to note its timing here. If it occurred, inflation was an incredibly brief period of exponential expansion, stretching the universe by a factor of at least 10 to the power of 26 in an almost unimaginably short time, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds. This rapid expansion would have smoothed out any initial irregularities and set the stage for the uniform and flat universe we observe today. Following the Grand Unification epoch, at around 10 to the power of minus 12 seconds, the universe entered the electroweak epoch. During this phase, the strong nuclear force separated from the electroweak force, leaving only the electromagnetic and weak nuclear forces still unified. The temperature had cooled to approximately 10 to the power of 15 Kelvin, which is still vastly hotter than the core of the hottest stars. At these energies, particles like quarks, leptons, such as electrons and neutrinos, and their antimatter counterparts were abundant. They existed in a hot, dense soup, constantly colliding and transforming into one another. A critical event during this early period, perhaps around 10 to the power of minus 11 seconds, was the breaking of the electroweak symmetry. This is when the electromagnetic force and the weak nuclear force separated, becoming the distinct forces we recognize today. This separation is associated with the Higgs mechanism, which gives mass to fundamental particles. Before this point, particles were massless, but after the electroweak symmetry breaking, they acquired mass through their interaction with the Higgs field. By approximately 10 to the power of minus 6 seconds, the universe had cooled to about 1 trillion Kelvin. This marked the beginning of the quark epoch, or hadron epoch. At this temperature, quarks, the fundamental building blocks of protons and neutrons, were still free and unconfined. The universe was filled with a hot, dense quark-gluon plasma, a state of matter where quarks and gluons, the particles that carry the strong force, moved freely, much like electrons in a metal. However, as the universe continued to expand and cool, the strong force became strong enough to bind quarks together. This process, called hadronization, occurred around 10 to the power of minus 6 seconds. Quarks combined to form composite particles called hadrons, primarily protons and neutrons. For every proton and neutron formed, there was also an antiparticle, antiproton and antineutron. A crucial puzzle in cosmology relates to this period, the matter-antimatter asymmetry. In the very early universe, matter and antimatter should have been produced in equal amounts. When matter and antimatter particles meet, they annihilate each other, converting their mass entirely into energy, photons. If matter and antimatter had been perfectly symmetrical, the universe would now be filled only with radiation, with no particles left to form stars, galaxies, or life. However, observations show that our universe is overwhelmingly composed of matter, with very little antimatter. Scientists believe that during these first moments, a tiny subtle asymmetry must have existed, perhaps 1 part in a billion, favouring matter over antimatter. This slight imbalance, known as baryogenesis, allowed a small residue of matter to survive the annihilation process, eventually forming everything we see today. The exact mechanism for this asymmetry is still an active area of research, potentially involving new physics beyond the standard model of particle physics. By 1 second after the Big Bang, the universe had cooled to about 10 billion Kelvin. At this point, the initial chaos had settled somewhat. The vast majority of matter-antimatter annihilation was complete, leaving behind the residual matter. Protons and neutrons were now stable, distinct particles. The universe was still too hot for atomic nuclei to form, but it was ready for the next crucial stage, Big Bang nucleosynthesis, where these protons and neutrons would begin to fuse into the first light elements, setting the stage for the formation of stars and galaxies billions of years later. The study of these first moments is highly theoretical, relying on the standard model of particle physics, which has been rigorously tested in particle accelerators like the Large Hadron Collider. While these accelerators cannot recreate the extreme energies of the very first instant of the Big Bang, they can probe conditions that existed fractions of a second later, allowing physicists to extrapolate backward in time with increasing confidence. Understanding these initial conditions is vital because they set the fundamental parameters for the universe's subsequent evolution, determining its composition, structure, and ultimate fate. The standard Big Bang model, while remarkably successful in explaining the universe's evolution from a very hot, dense state, faced several significant puzzles in the late 20th century. These challenges concerned observations of the universe's large-scale properties that seemed too finely tuned or too uniform to be explained by the standard model alone. To address these issues, a groundbreaking theoretical concept known as cosmic inflation was proposed. Inflation posits that the universe underwent an incredibly brief but extraordinarily rapid period of exponential expansion immediately after the Big Bang. This expansion was so powerful that it stretched the fabric of space itself by an immense factor, far exceeding the subsequent more gradual expansion we observe today. The idea of inflation was first proposed by American physicist Alan Guth in 1980, building on earlier work by others. Guth was initially trying to solve the problem of magnetic monopoles, hypothetical isolated magnetic charges predicted by some grand unified theories, which should have been abundant in the early universe but have never been observed. As he worked on this problem, he realized that a period of exponential expansion could solve not only the monopole problem, but also two other major cosmological puzzles, the flatness problem and the horizon problem. Let us first delve into the concept of this rapid expansion. Inflation is theorized to have occurred extremely early in the universe's history, perhaps starting as early as 10 to the power of minus 36 seconds after the Big Bang, and ending by about 10 to the power of minus 32 seconds. This means it lasted for an unimaginably short duration, less than a trillionth of a trillionth of a trillionth of a second. During this fleeting moment, the universe is believed to have expanded by a factor of at least 10 to the power of 26, and possibly much, much more. To visualize this, imagine a region of space smaller than a proton, expanding to the size of a grapefruit in that minuscule time, or even larger. This expansion was driven by a hypothetical energy field, often called the inflaton field, which possessed unusual properties causing it to exert a repulsive gravitational force, effectively pushing space apart at an accelerating rate. When the inflaton field eventually decayed, its energy transformed into the hot, dense matter and radiation that filled the universe, initiating the standard Big Bang expansion we know. One of the key problems inflation solves is the flatness problem. Observations of the cosmic microwave background, CMB, have shown that the universe's geometry is remarkably flat. In cosmology, flat refers to a universe where the paths of parallel lines never converge or diverge, much like a flat piece of paper. A curved universe, by contrast, would be like the surface of a sphere, positive curvature, or a saddle, negative curvature. Einstein's theory of general relativity shows that the geometry of the universe depends critically on its total energy density. For the universe to be flat, its total energy density must be incredibly close to a specific critical density. Any deviation from this critical density, even a tiny one in the early universe, would have been magnified by expansion over billions of years, leading to a universe that was either very closed, curved like a sphere, and would have recollapsed quickly, or very open, curved like a saddle, and would have expanded so rapidly that structures could not form. The observed flatness is astounding, requiring the universe's initial density to be within 1 part in 10 to the power of 60 of the critical density. Inflation elegantly solves this. Just as stretching a wrinkled balloon to immense size makes its surface appear flat from any small section, inflation stretches any initial curvature of space so dramatically that the observable universe appears perfectly flat. The second major puzzle inflation addresses is the horizon problem. The cosmic microwave background radiation, which provides a snapshot of the universe when it was about 380,000 years old, appears remarkably uniform in temperature across the entire sky. This means that regions of the universe that are now separated by vast distances, so vast that light could not have travelled between them, even over the age of the universe, exhibit nearly identical temperatures. In the standard Big Bang model without inflation, these regions would have been causally disconnected. That is, they could not have exchanged information or heat. So, how did they come to have the same temperature? Inflation resolves this by proposing that all the regions we observe today originated from an incredibly tiny, causally connected patch of space before inflation began. This tiny patch was in thermal equilibrium, meaning it had a uniform temperature. Inflation then rapidly expanded this small, uniform region to astronomical scales, making it appear as if widely separated areas of the sky are in thermal contact, even though they are now beyond each other's light horizon. A third problem that inflation resolves is the magnetic monopole problem. Some grand unified theories, GUTs, which attempt to unify the strong, weak and electromagnetic forces at very high energies, predict the existence of magnetic monopoles, hypothetical particles that carry an isolated north or south magnetic pole, unlike conventional magnets which always have both. These monopoles would have been produced in vast quantities in the extremely hot early universe, and if they existed, they should be easily detectable today. However, despite extensive searches, no magnetic monopoles have ever been found. Inflation offers a solution. The rapid exponential expansion would have diluted the density of these monopoles to such an extent that their current number density in the observable universe would be virtually zero, making them effectively undetectable. Beyond solving these cosmological puzzles, inflation also provides a mechanism for the origin of structure in the universe. During inflation, tiny quantum-scale fluctuations in the inflaton field were stretched to macroscopic sizes. These microscopic quantum jitters, which are an inherent part of quantum mechanics, became macroscopic density variations. After inflation ended, these slight density enhancements acted as the seeds of cosmic structure. Over billions of years, gravity amplified these initial density differences, pulling more matter into the slightly denser regions, which eventually collapsed to form the first stars, galaxies, and the large-scale cosmic web we observe today. The pattern of these density fluctuations, as imprinted on the cosmic microwave background, is remarkably consistent with the predictions of inflation. For instance, CMB maps show a nearly scale-invariant spectrum of fluctuations, meaning that variations in density occurred on roughly all scales, which is a key prediction of inflationary models. The specific pattern of polarization in the CMB, particularly the B-mode polarization, is also a target for future observations, as it could provide direct evidence of gravitational waves generated during inflation. While inflation theory has become an integral part of the Big Bang model, and its predictions are strongly supported by observations from missions like COBE, BUMAP and Planck, it is important to remember that it is still a theory. The exact nature of the inflaton field remains unknown, and there are various different models of inflation. However, the basic framework of inflation provides such elegant solutions to fundamental cosmological problems that it is widely accepted by the scientific community as the leading extension to the standard Big Bang theory. It transforms the Big Bang from a moment of unexplained initial conditions into a more comprehensive narrative that addresses why the universe possesses the large-scale properties we observe. In the earliest moments of the universe, immediately following the Big Bang, the cosmos was a place of unimaginably extreme conditions. It was incredibly hot and dense, so much so that matter as we know it could not exist. Instead, the universe was filled with a fundamental soup of pure energy and elementary particles, constantly interacting and transforming into one another. This transformation from raw energy into the building blocks of all matter is a crucial part of the universe's early story. The foundation of this process lies in Albert Einstein's famous equation, E mc2, which describes the equivalence of mass and energy. This equation tells us that mass can be converted into energy, and, critically for the early universe, energy can be converted into mass. in the superheated environment of the very early cosmos, photons or particles of light carried enormous amounts of energy. When two sufficiently energetic photons collided, their energy could spontaneously convert into a pair of particles, a particle and its corresponding antiparticle. For instance, two high-energy photons could produce an electron and its antimatter twin, a positron. This process was happening constantly throughout the universe. So, in the first fractions of a second after the Big Bang, the universe was not empty space but a churning, seething plasma. This plasma was a dense mix of fundamental particles such as quarks, which are the building blocks of protons and neutrons, leptons, which include electrons and neutrinos, and their respective antiparticles, along with a vast sea of energetic photons. These particles were moving at relativistic speeds, meaning their speeds were a significant fraction of the speed of light, and they were constantly colliding, creating new particles and antiparticles, and then annihilating back into pure energy. Let us trace this process through time as the universe expanded and cooled. In the first instance, from the Planck epoch up to perhaps 10 to the power of -6 seconds, the universe was a quark-gluon plasma. At these extreme temperatures, individual quarks were not bound together. They existed freely, along with gluons, which are the force-carrying particles for the strong nuclear force that binds quarks. The universe was a hot, dense fluid where quarks and gluons moved independently, constantly being created and annihilated. As the universe continued to expand, its temperature rapidly dropped. Around 1 microsecond, 1/1,000,000th of a second after the Big Bang, the temperature had cooled to approximately 2 trillion Kelvin. At this critical temperature, the strong nuclear force became strong enough to confine quarks. This process is called hadronization. Quarks could no longer exist freely and instead bound together to form composite particles called hadrons. The most familiar hadrons are protons, which are made of 2 up quarks and 1 down quark, and neutrons made of 1 up quark and 2 down quarks. This was a pivotal moment, as the basic constituents of atomic nuclei were now formed. During this period of particle creation and annihilation, a fundamental imbalance played a critical role in the universe's ultimate fate: the matter-antimatter asymmetry. According to our current understanding, energy should have produced equal amounts of particles and antiparticles. For instance, every time an electron was created, a positron, anti-electron, should also have been created. When a particle encounters its antiparticle, they annihilate each other, converting their entire mass back into energy. If there had been a perfect balance between matter and antimatter, all of the particles and antiparticles produced in the early universe would have annihilated each other, leaving behind a universe composed only of photons and neutrinos, with no ordinary matter to form stars, planets, or life. However, our universe is clearly dominated by matter. There are stars, galaxies, and people, and very little antimatter. This implies that there must have been a tiny, yet incredibly significant asymmetry in the early universe, favouring matter over antimatter. For every billion antiparticles, there was roughly 1,000,000,001 particles. This minuscule excess of matter, perhaps generated through processes like baryogenesis, which is still an active area of theoretical and experimental research, was what survived the annihilation epoch. As the universe continued to cool, the remaining particles and antiparticles annihilated each other, with a tiny surplus of matter, particles being the only survivors. This surviving matter is what makes up everything we see today. After the formation of protons and neutrons, and the general annihilation of antimatter, the universe continued to cool. Electrons, being much less massive than protons and neutrons, could still be readily created and annihilated by photons for a longer period. It wasn't until the universe was about 1 second old that the temperature dropped below the threshold for creating electron-positron pairs. At this point, most electrons and positrons annihilated, leaving behind a residual population of electrons, balancing the positive charge of the protons. Neutrinos, which are very light and interact only via the weak nuclear force, also decoupled from the rest of the matter and radiation around this time, forming a cosmic neutrino background that is difficult to detect but is another relic of this hot, dense epoch. So, by approximately 1 second after the Big Bang, The particle soup had largely resolved into its more familiar constituents. The universe was still a very hot, dense plasma, but it was now primarily composed of protons, neutrons, electrons, and photons, along with a vast number of neutrinos. These were the raw ingredients for the next stages of cosmic evolution, including Big Bang nucleosynthesis, where protons and neutrons would fuse to form the first light atomic nuclei, paving the way for the later formation of atoms, stars, and galaxies. The transformation from pure energy to this initial particle content was a fundamental step in shaping the universe we inhabit. The universe around us is governed by four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces dictate how particles interact, how atoms form, how stars shine, and how galaxies cluster together. At first glance, these forces appear distinct, operating in different ways and at vastly different strengths and ranges. However, a cornerstone of modern physics, particularly the study of the very early universe, is the idea of unification, that these seemingly distinct forces were once, under conditions of extreme energy and temperature, unified as a single fundamental force. As the universe expanded and cooled from its initial hot state, this unified force broke into the separate forces we observe today. Let us first briefly describe each of these four forces as they appear in our present-day, relatively cool universe. Gravity. This is the force of attraction between any two objects with mass or energy. It is the weakest of the four forces but has an infinite range. It governs the motion of planets around stars, the formation of stars and galaxies, and the large-scale structure of the entire universe. Electromagnetism. This force governs the interactions between electrically charged particles. It is responsible for all chemical reactions, the behavior of light, electricity, and magnetism. It holds electrons in orbit around atomic nuclei, forming atoms and molecules. Like gravity, it has an infinite range, but its strength is vastly greater than gravity. Strong nuclear force. This is the strongest of the four forces, but it acts only over incredibly short distances, typically within the nucleus of an atom. It is responsible for binding quarks together to form protons and neutrons, and for holding these protons and neutrons together within atomic nuclei. Without the strong force, atomic nuclei would fly apart due to the electromagnetic repulsion between positively charged protons. Weak nuclear force. This force is responsible for certain types of radioactive decay, such as beta decay, where a neutron transforms into a proton, or vice versa. It plays a crucial role in nuclear fusion processes in stars, including our Sun, but it has a very short range, even shorter than the strong force, and is significantly weaker than the strong and electromagnetic forces. The concept of force unification is not new to physics. A major triumph in the 19th century was James Clerk Maxwell's unification of electricity and magnetism into a single theory of electromagnetism. Before Maxwell, electricity and magnetism were considered separate phenomena, but he showed they were two different manifestations of the same underlying force, with light itself being an electromagnetic wave. Building on Maxwell's success, physicists in the 20th century began to wonder if the other forces could also be unified. The first major step beyond electromagnetism came in the 1960s and 70s with the electroweak unification. Sheldon Glashow, Abdus Salam, and Steven Weinberg independently developed a theory that showed that at very high energies, the electromagnetic force and the weak nuclear force are not separate, but are two aspects of a single electroweak force. This unification was a monumental achievement, as it demonstrated that forces could indeed merge under specific conditions. This theory predicted the existence of new force-carrying particles, the W and Z bosons, which were later experimentally discovered at the European Organisation for Nuclear Research, or CERN, in the 1980s, providing strong confirmation of the electroweak theory. The energies required for electroweak unification correspond to temperatures that existed in the universe when it was only about 10 to the power of minus 12 seconds old, or 1/1,000,000,000 of a second after the Big Bang. At this incredibly hot stage, particles interacted via the unified electroweak force. As the universe cooled below this critical temperature, the electroweak force broke into the distinct electromagnetic and weak forces we observe today. The next ambitious step in unification is the development of grand unification theories, or GUTs. These speculative theories aim to unify the electroweak force with the strong nuclear force. If a GUT is correct, then at even higher energies, corresponding to temperatures found when the universe was perhaps 10 to the power of minus 36 seconds old, these three forces, electromagnetic, weak, and strong, would have been unified into a single, grand unified force. At these energies, the universe would have been too hot for individual protons and neutrons to form, existing instead as a quark-gluon plasma. As the universe cooled through this epoch, the grand unified force would have broken down, first separating the strong force from the electro-weak force, and then the electro-weak force further splitting into the electromagnetic and weak forces. GUTS make several predictions, such as proton decay and the existence of magnetic monopoles, none of which have been definitively observed yet, which means that either these theories are incorrect, or the phenomena occur at rates too rare for us to detect with current technology. The ultimate goal for physicists is to achieve a theory of everything, or TOEU, which would unify all four fundamental forces, including gravity, into a single, comprehensive framework. Such a unification is thought to have occurred at the very highest energies, corresponding to the Planck epoch, which existed up to approximately 10 to the power of minus 43 seconds after the Big Bang. At these unimaginably high temperatures, 10 to the power of 32 Kelvin, gravity would have been as strong as the other forces and unified with them. Developing a theory that successfully integrates gravity with quantum mechanics, which describes the other three forces, is one of the most significant unsolved problems in physics. Theories like string theory and loop quantum gravity are leading candidates for such a quantum theory of gravity and a potential theory of everything. The early universe serves as the only natural laboratory where such extreme energies and temperatures existed, allowing for these force unifications to occur. By studying the remnants of the Big Bang, such as the cosmic microwave background, and by probing high-energy interactions in particle accelerators, scientists hope to find clues that will lead to a complete understanding of how these fundamental forces were unified in the universe's first moments, and how they subsequently separated to shape the physical laws that govern our cosmos today. The idea of forces uniting in the hot, dense early universe is a powerful concept that underscores the deep interconnectedness of physical reality. As the universe continued its rapid expansion after the Big Bang, its temperature steadily decreased. This cooling was essential for the formation of the first stable atomic nuclei and, later, the first complete neutral atoms. This process occurred in two distinct phases. First, the creation of light atomic nuclei during Big Bang nucleosynthesis, and then, much later, the formation of neutral atoms during recombination. Big Bang nucleosynthesis, or BBN, began when the universe was only about 3 minutes and 46 seconds old. Before this time, the universe was too hot, with temperatures exceeding billions of Kelvin, for atomic nuclei to hold together. Instead, it was a dense plasma of fundamental particles, primarily protons, neutrons, electrons, positrons, and a vast sea of energetic photons. Protons and neutrons could interconvert, but as the universe cooled, the conversion of neutrons into protons became less favourable, leading to a slight excess of protons. For every 7 protons, there was approximately 1 neutron. This precise ratio was critical for what was to follow. The initial hurdle for nucleosynthesis was the deuterium bottleneck. Deuterium, an isotope of hydrogen containing 1 proton and 1 neutron, is the simplest compound nucleus and the essential stepping stone for building heavier elements. However, at temperatures above approximately 900 million Kelvin, the high-energy photons in the universe would immediately smash apart any newly formed deuterium nuclei. This meant that even though protons and neutrons were present, they could not combine to form stable nuclei until the universe cooled sufficiently. Once the temperature dropped below this critical threshold, around 3 minutes and 46 seconds after the Big Bang, deuterium nuclei could finally survive. This opened the floodgates for a rapid series of nuclear fusion reactions. deuterium quickly combined with other protons and neutrons to form heavier isotopes. For example, a deuterium nucleus could fuse with another proton to form helium-3, which has 2 protons and 1 neutron. Helium-3 could then fuse with a neutron to form helium-4, which has 2 protons and 2 neutrons, or with another deuterium nucleus to form helium-4. Helium-4 is an exceptionally stable atomic nucleus, and the nuclear reactions during BBN were highly efficient at producing it. Because each helium-4 nucleus requires 2 protons and 2 neutrons, and neutrons were relatively scarce compared to protons, the 1:7 ratio, virtually all available neutrons were incorporated into helium-4 nuclei. The remaining protons, which constituted the vast majority of the baryonic matter, remained as individual hydrogen nuclei. This process continued for about 17 minutes, effectively ending around 20 minutes after the Big Bang, when the universe had expanded and cooled so much that the density and temperature were too low for further nuclear fusion to occur. The result of Big Bang nuclear synthesis was a universe composed of approximately 75% hydrogen and 25% helium-4 by mass, with only trace amounts of deuterium, helium-3 and lithium-7. No heavier elements like carbon, oxygen or iron were formed during this period. The universe simply did not remain hot and dense enough for a sufficient duration to build up these more complex nuclei. The conditions for forming elements beyond lithium require the extreme pressures and temperatures found only in the cores of stars, which would not form for hundreds of millions of years. The predicted abundances of these light elements are one of the strongest pieces of evidence supporting the Big Bang theory. Astronomers observe the cosmic abundances of hydrogen, helium, and lithium in the most pristine ancient regions of the universe, such as distant gas clouds and the oldest stars, which have not been significantly altered by later stellar processes. The measured proportions match the BBN predictions with remarkable accuracy. This agreement confirms that the universe was indeed hot and dense enough in its early stages for these specific nuclear reactions to occur, and that it expanded and cooled at a rate consistent with our current cosmological models. Furthermore, the precise values of these abundances are sensitive to the amount of ordinary matter, or baryonic matter, in the universe. The success of BBN in matching observations provides a strong constraint on the total amount of baryonic matter, indicating it makes up only about 4 to 5% of the universe's total mass energy content. While the nuclei of the first elements were formed within the first 20 minutes, the universe was still too hot for these nuclei to capture electrons and form complete neutral atoms. Free electrons still roamed independently, constantly scattering photons. This state persisted for a much longer period. The universe remained an opaque ionized plasma, much like the interior of a star, where light could not travel freely. The second crucial phase, known as recombination, occurred much later, approximately 380,000 years after the Big Bang. By this time, the universe had continued to expand significantly, and its temperature had dropped to about 3000 Kelvin, roughly the temperature of the surface of a cool star. At this critical temperature, the kinetic energy of the free electrons was low enough that they could be captured by the positively charged atomic nuclei, protons and helium nuclei, to form stable neutral atoms. The term recombination is a bit misleading, as it was the first time electrons and nuclei combined, not a recombination. As electrons combined with nuclei, the universe underwent a dramatic transformation. With electrons now bound within atoms, they were no longer free to scatter photons. The universe suddenly became transparent to light. The photons that had been trapped and constantly scattering within the opaque plasma were now free to travel across the cosmos without interruption. These photons, released at the moment of recombination, are what we detect today as the cosmic microwave background radiation. Its uniform distribution and specific temperature of 2.725 Kelvin are direct evidence of this event. The formation of these first neutral atoms, primarily hydrogen and helium, marked the end of the plasma era and the beginning of the dark ages of the universe. For the first time, matter was organized into stable, neutral structures. This transition was fundamental because it allowed light to travel freely, and it also set the stage for the next major phase of cosmic evolution: the gravitational collapse of this neutral gas to form the first stars and galaxies. Without the birth of these first atoms, the universe would have remained an undifferentiated plasma, incapable of forming the complex structures we observe today. Following the formation of the first neutral atoms during the epoch of recombination, the universe entered a period known as the Cosmic Dark Ages. This era, spanning from approximately 380,000 years after the Big Bang to roughly 300 million to 500 million years later, is characterized by the absence of light sources in the visible spectrum. While the universe was no longer an opaque plasma, it was a largely featureless expanse of neutral gas, primarily hydrogen and helium, with no stars or galaxies yet to illuminate it. The onset of the Dark Ages was marked by the decoupling of matter and radiation. Before recombination, photons were constantly interacting with free electrons, making the universe opaque. Once electrons combined with atomic nuclei to form neutral atoms, these photons were free to travel unimpeded. This moment, 380,000 years after the Big Bang, is when the cosmic microwave background CMB radiation was released. As the universe continued to expand, these CMB photons stretched to longer wavelengths and cooled, eventually becoming the faint microwave glow we detect today. During the Dark Ages, the CMB was the only significant source of radiation, and its temperature continued to drop, meaning it provided less and less light in the visible range. During this long stretch of cosmic history, the universe was indeed dark. There were no stars shining, no galaxies blazing with starlight. The gas was almost entirely neutral, meaning its atoms had their full complement of electrons. This neutral gas, predominantly hydrogen and helium, was distributed relatively uniformly throughout space. The small density fluctuations that were imprinted on the cosmic microwave background, originating from quantum fluctuations in the very early universe, were still present, but they were very subtle. The dominant force at play during the Dark Ages was gravity. While the gas was largely uniform, the tiny overdensities, or regions where the gas was slightly denser than average, began to slowly attract more matter due to their slightly stronger gravitational pull. This process of gravitational collapse was incredibly slow during the Dark Ages because the universe was still relatively smooth, and the gravitational forces were weak over the vast distances. An essential component influencing this gravitational collapse was dark matter. Dark matter is a mysterious substance that does not interact with light or other electromagnetic radiation, making it invisible to telescopes. However, it does interact gravitationally. Cosmological models suggest that dark matter makes up about 27% of the universe's total mass energy content, far more than ordinary baryonic matter. During the Dark Ages, dark matter began to clump together under its own gravity, forming invisible structures known as dark matter halos. These halos acted as gravitational scaffolding, providing the initial gravitational wells into which the ordinary neutral gas could slowly fall. Without dark matter, the gravitational pull of ordinary matter alone would have been insufficient to form structures within the observed timescale of the universe. The temperature of the neutral gas during the Dark Ages continued to fall from the initial 3000 Kelvin at recombination. It eventually reached a minimum of around 10 Kelvin, or 10 degrees above absolute zero, after about 10 million to 100 million years. After this point, as the first structures began to form and contract, the gas within these collapsing regions would start to heat up again due to compression. The chemical composition of the universe during the Dark Ages was extremely simple. It consisted almost exclusively of hydrogen and helium, with only trace amounts of lithium. There were no heavier elements like carbon, oxygen, or iron, as these elements are forged in the interiors of stars and supernova explosions, which had not yet occurred. This lack of heavier elements meant that the cooling mechanisms for the gas were very limited. In the present-day universe, heavier elements act as efficient coolants, allowing gas clouds to radiate away energy and collapse more easily. In the Dark Ages, the primary coolant was molecular hydrogen, H2, which is less efficient than heavier elements. This limited cooling had implications for the properties of the first stars that would eventually form. Observing the Dark Ages directly is extremely challenging. Since there were no stars or galaxies emitting visible or ultraviolet light, conventional telescopes cannot see this period. However, scientists are exploring various indirect ways to probe this era. One promising avenue is through the detection of the 210 centimeter line of neutral hydrogen, also known as the hydrogen line, or spin-flip transition. This specific radio wavelength is emitted when the spin of the electron in a neutral hydrogen atom flips. By observing the redshifted 210 centimeter line from different points in the universe, astronomers hope to map the distribution of neutral hydrogen during the Dark Ages and study how the first structures began to emerge. Projects like the Low Frequency Array, or LOFAR, and the Square Kilometre Array, or SKA, are designed to detect these faint signals. The Dark Ages were a crucial transitional period. It was a time when the universe was literally dark, but beneath the quiet, expanding expanse, the seeds of future cosmic structures were slowly germinating. Gravity, guided by the distribution of dark matter, was patiently gathering the primordial gas into progressively denser clumps. This gradual accumulation of matter laid the groundwork for the universe's next major cosmic revolution, the ignition of the very first stars, which would end the Dark Ages and usher in the era of Ryanization and the formation of galaxies. Without this long, quiet period of gravitational growth, the universe would not have been able to build the complex cosmic tapestry we observe today. The Cosmic Dark Ages, a period of profound darkness lasting for hundreds of millions of years, eventually came to an end with the ignition of the very first stars. These pioneering celestial bodies, often referred to as Population 3 stars, were fundamentally different from the stars we see in the night sky today. Their formation marked a pivotal moment in cosmic history as they began the process of illuminating the universe, forging the first heavy elements, and setting the stage for the formation of galaxies. The birth of these first stars was a direct consequence of the gravitational collapse that slowly unfolded during the Dark Ages. As discussed, the universe during this era was filled with a relatively uniform distribution of neutral hydrogen and helium gas, along with the invisible scaffolding of dark matter halos. These dark matter halos, formed by the gravitational clumping of dark matter, created gravitational potential wells into which the ordinary baryonic gas could slowly fall. Within these dark matter halos, regions of slightly higher gas density began to attract more and more surrounding gas. As the gas accumulated, its density increased, and the gravitational pull became stronger, leading to a runaway collapse. However, the process was not as straightforward as in the modern universe. The primordial gas consisted almost entirely of hydrogen and helium, with only trace amounts of lithium. Crucially, there were no heavier elements, which astronomers refer to as metals. In the modern universe, metals play a vital role in cooling gas clouds, allowing them to fragment into smaller, denser clumps that can form stars of various sizes. Without these efficient coolants, the primordial gas had fewer ways to radiate away the heat generated by gravitational compression. The primary cooling mechanism available to the primordial gas was the formation and excitation of molecular hydrogen, or H2. Hydrogen atoms could combine to form H2 molecules, which could then radiate energy away, allowing the gas cloud to cool and contract further. However, H2 is not a very efficient coolant compared to metals. This limited cooling meant that the gas clouds had to be much more massive before they could collapse sufficiently to form stars. As a result, the first stars are predicted to have been extraordinarily massive. Theoretical models suggest that Population 3 stars typically had masses ranging from tens to hundreds, or even thousands of times the mass of our Sun. Some models even propose that the very first stars could have been as massive as 100,000 solar masses. This immense mass had profound implications for their characteristics and lifespans. Because of their enormous mass, Population 3 stars were incredibly hot and luminous. Their cores reached extreme temperatures and pressures, causing nuclear fusion reactions to proceed at a furious rate. They burned through their hydrogen fuel much more quickly than smaller stars. Consequently, their lifespans were incredibly short, lasting only a few million years, compared to the billions of years our Sun is expected to live. The death of these massive first stars was as dramatic as their birth. They ended their lives in spectacular supernova explosions. These were not just any supernova. They were likely a specific type known as pair instability supernova for the most massive ones. In such an explosion, the star completely disintegrates, leaving no remnant behind. These first supernovae were crucial because they were the universe's first cosmic factories for heavier elements. Inside the cores of these massive stars, nuclear fusion had forged elements up to iron. The supernova explosions then dispersed these newly created heavier elements, such as carbon, oxygen, nitrogen, and silicon, into the surrounding intergalactic medium. This chemical enrichment was essential, as these metals would later become the building blocks for subsequent generations of stars, planets, and eventually life. The supernovae of the first stars also had another profound impact. They contributed to the reionization of the universe. After recombination, the universe was filled with neutral hydrogen and helium. The ultraviolet light emitted by the first stars was energetic enough to strip electrons from these neutral atoms, reionizing the intergalactic medium. This process was gradual, starting in localized bubbles around the first stars and galaxies, and eventually spreading throughout the cosmos. By about 1 billion years after the Big Bang, the universe was largely reionized, making it transparent to ultraviolet light once again. This reionization epoch is another critical phase in cosmic evolution, and its timing and progression are actively studied using observations of distant quasars and the cosmic microwave background. Directly observing population 3 stars is extremely challenging because of their short lifespans and the vast distances involved. They existed billions of years ago, and their light is incredibly faint and redshifted. Current telescopes, even the most powerful ones like the James Webb Space Telescope, are pushing the limits to detect the faint light from the very first galaxies which would contain these stars. While individual population 3 stars have not yet been definitively observed, their existence is inferred from the properties of the cosmic microwave background, the observed abundances of light elements, and the presence of heavier elements in later generations of stars. The chemical composition of the oldest stars we can observe today, known as population 2 stars, shows very low abundances of metals, consistent with them having formed from gas that was only slightly enriched by the supernovae of population 3 stars. The first stars were cosmic pioneers. They ended the long darkness, initiated the chemical enrichment of the universe, and began the process of reionization. Their short, violent lives set in motion a chain of events that led to the formation of the galaxies, stars, and planets we see today, ultimately making the universe a more complex and hospitable place. The formation of the first galaxies represents a crucial stage in the evolution of the universe, transforming a relatively smooth, dark expanse of gas into the complex, luminous structures we observe today. This process, which began hundreds of millions of years after the Big Bang, was driven primarily by gravity, with a pivotal role played by the mysterious substance known as dark matter. The standard cosmological model, often referred to as lambda CDM, lambda for dark energy and cold dark matter, provides the framework for understanding how these structures emerged through a hierarchical process, where smaller clumps of matter merged and grew into larger ones. The seeds of galaxy formation were sown much earlier, during the epoch of cosmic inflation, when tiny quantum fluctuations in the very early universe were stretched to macroscopic scales. These fluctuations manifested as minute variations in the density of matter and energy, imprinted on the cosmic microwave background. During the subsequent Dark Ages, as the universe expanded and cooled, these slight overdensities began to exert a stronger gravitational pull on surrounding matter. Crucially, the vast majority of the matter in the universe is not the ordinary baryonic matter, protons, neutrons, electrons, that makes up stars and galaxies, but rather dark matter. Dark matter, which accounts for about 27% of the universe's mass-energy content, does not interact with light or other electromagnetic radiation, making it invisible to telescopes. However, it does interact gravitationally. Because dark matter does not experience the electromagnetic forces that would cause ordinary gas to exert pressure and resist collapse, it was able to clump together much earlier and more efficiently than ordinary matter. During the Dark Ages, dark matter began to coalesce under its own gravity, forming invisible structures known as dark matter halos. These halos were the first large-scale structures to emerge in the universe. They varied in size, from small clumps with masses equivalent to 1 million suns to much larger ones. These dark matter halos acted as gravitational scaffolding, creating the potential wells into which the ordinary baryonic gas, primarily hydrogen and helium, could slowly fall. The process of gas accumulating within these dark matter halos was gradual. As the neutral gas fell into the gravitational embrace of a dark matter halo, it became compressed and heated. For stars to form, this gas needed to cool down so that it could become dense enough to collapse further. In the early universe, without the presence of heavier elements, which act as efficient coolants in modern gas clouds, the primary cooling mechanism for the primordial gas was the formation and excitation of molecular hydrogen, H2. This limited cooling meant that the gas clouds had to be quite massive before they could cool sufficiently to initiate star formation. The very first stars, known as population 3 stars, formed within these early, relatively small dark matter halos. These stars were typically much more massive than our Sun, burning through their fuel rapidly and ending their lives in spectacular supernova explosions within just a few million years. These supernovae were vital as they dispersed the first heavy elements, forged in the star's cores, into the surrounding gas. This chemical enrichment was a critical step, as these newly synthesized metals would later enable more efficient cooling in subsequent generations of gas clouds, allowing for the formation of smaller, more diverse stars. The earliest galaxies were not the grand, spiral or elliptical structures we see today. Instead, they were likely much smaller, irregular clumps of stars and gas, forming within the most massive and densest of the early dark matter halos. These nascent galaxies, sometimes referred to as proto-galaxies or mini-halos, were the building blocks of larger galaxies. The process of galaxy formation is thought to be hierarchical, meaning that small structures formed first and then merged over cosmic time to create progressively larger ones. As the universe continued to evolve, these early mini-halos and proto-galaxies, still embedded within their dark matter halos, began to attract each other through gravity. They collided and merged, a process that was particularly frequent in the early universe when structures were closer together. These mergers were violent events, disrupting existing stellar orbits, triggering bursts of star formation, and leading to the growth of larger, more complex galaxies. Each merger brought in more gas, more stars, and more dark matter, contributing to the overall growth of the galactic structures. The role of dark matter in this hierarchical formation is paramount. Without its gravitational influence, ordinary matter alone would not have been able to clump together quickly enough to form the observed large-scale structures in the universe. The pressure exerted by the hot gas in the early universe would have prevented it from collapsing into structures on the scales of galaxies. Dark matter, by providing the initial gravitational scaffolding without being affected by pressure or electromagnetic forces, allowed the first structures to form, which then served as the gravitational anchors for ordinary matter. Observations from powerful telescopes like the Hubble Space Telescope and, more recently, the James Webb Space Telescope provide direct evidence for this hierarchical formation. These telescopes can peer deep into the universe, allowing astronomers to observe galaxies as they appeared billions of years ago, when the universe was much younger. They reveal numerous small, irregular, and often interacting galaxies in the early universe, which are consistent with the idea that larger galaxies formed through the mergers of smaller ones. The most distant galaxies observed are often small and appear to be actively forming stars, indicating they are in their early stages of development. Over billions of years, this process of gravitational collapse and hierarchical merging continued. Smaller galaxies merged to form larger ones, and these larger galaxies then grouped together to form galaxy clusters and superclusters, creating the vast cosmic web of filaments and voids that spans the universe today. The dark matter halos continued to grow, encompassing these larger structures. The properties of galaxies, such as their shape, size, and star formation rates, are influenced by their environment and their merger history. For example, elliptical galaxies are thought to be the result of multiple major mergers, while spiral galaxies may have experienced fewer significant merger events. The idea of nothing is a profoundly complex and endlessly fascinating subject that has puzzled thinkers for millennia, from ancient philosophers to modern scientists. When we talk about nothing, especially in the context of the universe's beginning, or what might have existed before the Big Bang, it is crucial to understand that nothing is not a single simple concept. It carries different meanings in philosophy compared to science, and even within science itself, its definition shifts as our understanding of reality evolves. To truly grapple with the question of whether nothing existed before the Big Bang, we must first clarify what exactly we mean by that seemingly straightforward word. In philosophy, nothing often refers to absolute non-existence, a state utterly devoid of being of properties of anything whatsoever. This is the most profound and perhaps most challenging definition to grasp, because it is by its very nature the absence of all that we know. For ancient Greek philosophers like Aristotle, the concept of a true vacuum or empty space was problematic. He believed that nature abhorred a vacuum, arguing that every space must be filled by something, even if it was an invisible substance or an ether. His view was largely a reaction to earlier atomists, who proposed that the universe consisted of tiny, indivisible particles moving in an infinite void or empty space. For Aristotle, nothingness was more akin to a privation, or the absence of a particular quality or form from something that already existed, rather than a complete absence of existence. The idea of something arising from literally nothing was largely inconceivable in many classical philosophical systems, where creation was often seen as the rearrangement of pre-existing material or an emanation from a divine source. Centuries later, the philosopher Gottfried Wilhelm Leibniz posed his famous question, why is there something rather than nothing? This query encapsulates the core philosophical challenge of existence itself. If absolute nothingness is the simplest and most natural state, then why do we find ourselves in a universe filled with matter, energy, space, and time? It implies that something must account for existence itself, not just the particular form it takes. From an existentialist perspective, nothingness can also refer to the absence of inherent meaning or purpose in the universe, forcing humanity to create its own values and significance. This philosophical exploration of nothingness often pushes the boundaries of human intuition, requiring us to think beyond our direct experiences of the world, where even what we perceive as empty is filled with air or fields or potentials. Moving from the abstract realms of philosophy to the concrete observations of science, the meaning of nothing begins to change fundamentally. For a long time, even in scientific discourse, empty space was considered relatively inert, a passive stage upon which the drama of the universe unfolded. The 17th century marked a pivotal shift with experiments by Torricelli, Pascal, and Boyle, providing experimental proof of the vacuum. Torricelli's barometer, for instance, demonstrated that mercury could be suspended in a tube by atmospheric pressure, leaving a space above the mercury where air was absent of void. These experiments challenged the Aristotelian notion of a plenum, where all space must be filled, and laid the groundwork for understanding empty space as a physical entity capable of being studied. However, even then, the vacuum was often seen as simply the absence of matter, a region where particles were not present. Later in the 19th century, the concept of the luminiferous ether was introduced, a hypothetical medium thought to permeate all of space to carry light waves. This was another attempt to fill the vacuum, reflecting a discomfort with the idea of truly empty space, until Einstein's theory of relativity showed the ether was unnecessary. The advent of quantum mechanics in the 20th century profoundly revolutionized the scientific understanding of nothing, or more accurately, the quantum vacuum. In the classical view, a vacuum is simply space with no particles in it. However, quantum mechanics teaches us that this is not true. According to the Heisenberg uncertainty principle, which states that certain pairs of physical properties like energy and time cannot both be known with perfect precision, simultaneously, even empty space is teeming with activity. It is impossible to have an absolutely empty void where nothing is happening. Instead, the quantum vacuum is a dynamic, bubbling soup of virtual particles, constantly popping into existence and then vanishing again in incredibly short periods of time. These virtual particles are not directly observable, but their effects can be measured. One of the most striking pieces of evidence for the quantum vacuum's activity is the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that if two uncharged metallic plates are placed very close together in a vacuum, they will experience a small but measurable attractive force. This force arises because there are fewer virtual particles and their associated electromagnetic fluctuations that can exist in the tiny gap between the plates compared to the space outside the plates. The difference in quantum vacuum energy between the inside and outside of the plates creates a net inward pressure pushing the plates together. The experimental verification of the Casimir effect demonstrates that the quantum vacuum is not inert, but possesses real measurable energy known as zero-point energy. This energy represents the lowest possible energy state of a quantum field even at absolute zero temperature. Furthermore, in modern quantum field theory, every fundamental particle in the universe is understood not as a distinct tiny ball, but as an excitation or vibration of an underlying quantum field that permeates all of space. For example, there is an electron field, a photon field, a quark field, and so on. The vacuum state in this context is the lowest energy state of all these quantum fields. It is a state where there are no excitations, no particles, but the fields themselves are still present and continually fluctuating. This means that even in the absence of observable particles, the fundamental building blocks of reality, the fields themselves are still very much there. The Higgs field, for instance, is a field that permeates all of space and interacts with certain fundamental particles, giving them mass. Even in the vacuum state, the Higgs field has a non-zero background value, known as its vacuum expectation value, which is crucial for the existence of mass in the universe. So the scientific vacuum is far from nothing in the philosophical sense. It is a complex energetic entity with inherent properties and potential. When we extend this understanding to cosmology and the question of what existed before the Big Bang, the definition of nothing becomes even more intricate. The standard Big Bang model describes the evolution of the universe from an extremely hot, dense state. It points to a beginning where all matter, energy, space and time were compressed into an infinitely small and infinitely dense point called a singularity. This singularity represents a breakdown of our current laws of physics. If space and time themselves began at the Big Bang, then the concept of before the Big Bang loses its conventional meaning. How can something exist before time began? Does nothing then mean the absence of space and time as we know them, a state that is fundamentally inconceivable within our normal experience? Many contemporary cosmological theories attempt to address this issue by proposing different scenarios for the pre-Big Bang epoch, or by seeking to avoid the singularity altogether. Some theories suggest that what we perceive as the Big Bang was not the ultimate beginning, but rather a transition from a previous state. For example, cyclic universe models propose that our universe is just one phase in an endless cycle of expansion and contraction, or bounces. In these models, nothing before our Big Bang is simply the highly compressed or collapsed state of a previous universe, or the phase between one cosmic cycle and the next. This means that something always existed in some form, just not necessarily the current form of our universe. Another influential idea comes from inflationary cosmology, which proposes a period of extremely rapid expansion in the very early universe. This theory introduces the concept of an inflaton field, which drove this rapid expansion. In some inflationary scenarios, the Big Bang itself could have arisen from a quantum fluctuation in a pre-existing quantum vacuum, or a false vacuum, a state of higher energy that rapidly decayed, releasing enormous amounts of energy and creating the matter and radiation we see today. In this view, nothing is not an absolute void, but a highly energetic and unstable quantum vacuum from which our universe inflated. This vacuum might itself be part of a larger meta-vacuum, giving rise to multiple universes in a multiverse scenario. In such a context, our universe springs from a quantum foam, or a larger cosmic substrate, which is far from nothing in the absolute sense, but rather a fertile ground for cosmic creation. The search for a theory of quantum gravity which aims to unify general relativity, the theory of gravity at large scales with quantum mechanics, the theory of matter at small scales is crucial for understanding the ultimate nature of nothing before the Big Bang. Theories like loop quantum gravity suggest that space-time itself might not be continuous, but rather composed of discrete fundamental loops, or quanta. In this framework, the Big Bang singularity could be resolved as a quantum bounce, where the universe did not collapse to infinite density, but instead reached a minimum size before rebounding into expansion. In this view, there was no true singularity, and thus no nothing, in the sense of complete non-existence before the bounce. Similarly, string theory, a candidate for a unified theory of everything, posits that fundamental particles are not point-like, but rather tiny vibrating strings. It also suggests the existence of extraspatial dimensions curled up or hidden from our perception. In some string theory-inspired cosmological models, the universe's beginning might be explained as a collision of higher dimensional branes, or membranes existing in a larger bulk. In this context, nothing before the Big Bang would be a state of other branes, or the higher dimensional space they inhabit a complex and energetic realm that predates our familiar four-dimensional space-time. These models hint at a pre-geometric state where space-time as we know it does not yet exist but rather emerges from a more fundamental quantum foam or network. Ultimately, the scientific understanding of nothing, especially in the context of the universe's origin, is constantly evolving and becoming more nuanced. It is clear that the nothing from which the universe may have sprung is not an absolute philosophical void. Instead, it is understood as a highly complex dynamic and potentially energetic state that defies our everyday intuition. Whether it is a quantum vacuum teeming with virtual particles, a pre-existing space-time from a previous cosmic cycle, a higher dimensional brane, or a fundamental quantum foam, the scientific nothing is always something with inherent properties and the potential for existence. The distinction between philosophical nothingness and scientific nothingness is paramount. When scientists discuss the origin of the universe from nothing, they're almost always referring to a scientific vacuum, a state of minimum energy of quantum fields, or a realm where space and time as we understand them had not yet fully emerged. They are not typically referring to the absolute non-existence of everything, including the laws of physics themselves. The question of whether true absolute nothingness could ever spontaneously give rise to something remains largely in the domain of philosophy and metaphysics, as it lies beyond the empirical methods of science. Our attempts to define and comprehend nothing continue to push the boundaries of human thought, revealing that the apparent void is far richer and more complex than we could ever imagine. The quest to understand what, if anything, came before the Big Bang fundamentally depends on how we define that elusive concept of nothing itself. The Big Bang theory stands as the leading cosmological model explaining the observable universe's origins and evolution. It describes how the universe began from an extremely hot, dense state and has since expanded and cooled to become the vast, complex cosmos we see today. It is important to understand that the Big Bang was not an explosion in space, as if matter suddenly flew outward into pre-existing emptiness. Instead, it was an expansion of space itself, carrying matter and energy along with it. Every point in the universe expanded away from every other point, creating the fabric of space-time. This concept is fundamental to grasping the theory's core message, that the universe has a history and that it has changed dramatically over time. The development of the Big Bang theory was a gradual process built on a series of key observations and theoretical insights over many decades. One of the earliest and most pivotal figures was Georges Lemaitre, a Belgian priest and physicist in the 1920s. Independently of others, he proposed that the universe began from a single primordial atom, a highly condensed state of matter and energy that expanded outwards. His idea later became a cornerstone of the Big Bang model, although the term Big Bang itself was famously coined much later by astronomer Fred Hoyle, a proponent of a rival theory, the steady-state theory. Hoyle used the term disparagingly to describe Lemaitre's idea of a definite beginning for the universe, but it stuck and ironically became the widely accepted name. Another crucial piece of the puzzle came from Edwin Hubble, an American astronomer in the late 1920s. Hubble observed that distant galaxies were moving away from Earth and that the speed at which they receded was proportional to their distance from us. This relationship, known as Hubble's law, provided the first direct observational evidence for an expanding universe. The light from these distant galaxies was shifted towards the red end of the spectrum, a phenomenon called redshift, similar to how the pitch of a siren changes as an ambulance moves away. This redshift indicated that the space between galaxies was stretching, carrying the galaxies farther apart. Hubble's findings strongly supported Lemaitre's concept of an expanding universe and undermined the prevailing static universe models. For a time in the mid-20th century, the Big Bang theory competed with the steady-state theory. The steady-state model proposed that the universe was eternal, unchanging in its overall appearance even as it expanded because new matter was continuously being created to fill the gaps left by the expansion. This meant the universe had no beginning and no end. However, two major discoveries decisively tipped the scales in favour of the Big Bang model. The first was the discovery of the cosmic microwave background radiation, or CMB, in 1964 by Arno Penzias and Robert Wilson. They were working with a large horn antenna and detected a persistent faint static, like signal coming uniformly from all directions in the sky. This signal was initially thought to be interference, but it turned out to be the leftover radiation from the very early universe. According to the Big Bang theory, the early universe was extremely hot and dense, filled with a plasma of matter and radiation. As the universe expanded, it cooled and eventually became transparent, allowing this radiation to travel freely. The CMB is essentially the cooled down afterglow of the Big Bang, a relic from a time when the universe was only about 380,000 years old. Its uniformity and temperature distribution precisely matched predictions made by the Big Bang model, providing incredibly strong evidence for a hot, dense beginning. The second major piece of evidence came from the observed abundance of light elements in the universe. The Big Bang theory predicts that in the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion reactions to occur, a process called Big Bang nucleosynthesis. During this period, protons and neutrons fused to form the nuclei of light elements, primarily hydrogen and helium, along with trace amounts of lithium. The theory accurately predicts the relative proportions of these light elements observed in the universe today, about 75% hydrogen and 25% helium by mass. This precise agreement between theoretical predictions and cosmological observations served as another powerful confirmation of the Big Bang model's accuracy. These three pillars, the expansion of the universe, the cosmic microwave background, and the abundance of light elements, form the robust observational foundation of the Big Bang theory. The story of the Big Bang begins at an incredibly early moment in time, perhaps as early as the Planck epoch, which is approximately 10 to the power of minus 43 seconds after the conceptual beginning. At this time, the universe was unimaginably hot and dense, so much so that all four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, are thought to have been unified into a single superforce. Our current understanding of physics breaks down at this extreme point, and a complete theory of quantum gravity is needed to truly describe this earliest moment. Immediately following the Planck epoch, the universe entered a period of rapid and exponential expansion known as the inflationary epoch. This concept was proposed in the early 1980s primarily by Alan Guth to address several puzzles that the standard Big Bang model on its own could not fully explain. These problems included the horizon problem, which questioned how distant parts of the universe could have the same temperature if there had not been enough time for light to travel between them to equalize their temperatures. The flatness problem pondered why the universe's geometry appears so incredibly flat, which is a very specific condition among many possibilities, and the monopole problem addressed why certain exotic heavy particles predicted by some theories are not observed today. Inflation suggests that the universe underwent an incredibly brief but mind-bogglingly rapid expansion, stretching its size by a factor of at least 10 to the power of 26 in a tiny fraction of a second. This super expansion would have smoothed out any initial irregularities, flattened the universe's geometry, and diluted away any unwanted exotic particles, effectively solving these cosmological problems. Inflation also provides a mechanism for generating the tiny density fluctuations observed in the cosmic microwave background, which later grew through gravity to form the large-scale structures like galaxies and galaxy clusters we see today. After inflation, the universe continued to expand, but at a much slower rate. The extreme energy of the inflationary period was converted into a hot, dense soup of elementary particles and antiparticles, a state known as the quark-gluon plasma. At this point, the universe was still too hot for quarks to bind together. As the universe continued to cool, the strong nuclear force became strong enough for quarks to combine, forming protons and neutrons, which are types of hadrons. This period is known as the Hadron Epoch. Crucially, during this time, there was a tiny asymmetry between matter and antimatter. For every billion antiquarks, there were 1,000,001 quarks. As the universe cooled, matter and antimatter annihilated each other, leaving behind a small surplus of matter, which eventually formed everything we see today. Following the Hadron epoch was the lepton epoch, where leptons such as electrons, positrons, and neutrinos dominated the universe's energy density alongside photons. About a few minutes after the Big Bang, when the universe had cooled to about 1 billion degrees Celsius, the conditions were just right for Big Bang nucleosynthesis (DBN) to occur. Protons and neutrons fused together to form the nuclei of the lightest elements, deuterium, an isotope of hydrogen helium-3 and helium-4, and trace amounts of lithium-7. These reactions lasted for only about 20 minutes before the universe became too cool and too diffuse for fusion to continue. The precise ratios of these light elements observed in the universe today are one of the most compelling pieces of evidence for the Big Bang model. These abundances perfectly match the predictions made by the theory, providing a powerful confirmation of the universe's hot, dense early state. For the next several 100,000 years, the universe was a hot opaque plasma, primarily composed of ionized hydrogen and helium nuclei and free electrons. Photons, light particles, were constantly scattering off these free electrons, meaning light could not travel far without being absorbed or deflected. This was the photon epoch where radiation dominated the universe. As the universe continued to expand and cool, the temperature eventually dropped to about 3,000 Kelvin, roughly 38,000 years after the Big Bang. At this critical temperature, electrons were able to combine with hydrogen and helium nuclei to form stable neutral atoms. This event is known as recombination. Once electrons were bound in atoms, photons were no longer constantly scattering off free charged particles. The universe became transparent and photons were free to travel across space unimpeded. These photons form the cosmic microwave background radiation, a direct observable relic of this epoch often referred to as the surface of last scattering. It is literally the oldest light we can detect, providing a direct image of the early universe. After recombination, the universe entered a period known as the Cosmic Dark Ages. For hundreds of millions of years, there were no stars or galaxies to produce light. The universe was filled with neutral hydrogen and helium gas, and a diffuse background of CMB photons. This was a period of darkness and gradual evolution, as gravity slowly began to pull together the slightly denser regions of gas and dark matter that were seeded by the tiny fluctuations from the inflationary epoch. Over vast stretches of time, these gravitational pulls led to the collapse of gas clouds, forming the first stars and quasars. These first luminous objects began to reionize the neutral hydrogen gas, filling the universe with ultraviolet radiation. This marked the end of the Dark Ages and the dawn of the cosmic reionization era, roughly 150 million to 1 billion years after the Big Bang. As the universe continued to evolve, gravity played an increasingly dominant role in shaping its structure. The small density enhancements continued to grow, attracting more matter. This led to the formation of progressively larger structures. Galaxies formed from collapsing clouds of gas and dark matter, and then clustered together to form galaxy groups and larger galaxy clusters, which themselves are organized into vast superclusters. This hierarchical clustering process led to the creation of the cosmic web, a filamentary structure of galaxies separated by vast empty voids that characterizes the large-scale distribution of matter in the universe today. Dark matter, an invisible and mysterious substance that interacts only through gravity, is crucial for this process. It provides the gravitational scaffolding around which ordinary matter collects. Without dark matter, the universe's structures would not have formed as they have. In the last few billion years, the expansion of the universe has taken an unexpected turn. Observations of distant supernovae in the late 1990s revealed that the expansion is not only continuing but is actually accelerating. This acceleration is attributed to a mysterious force or energy called dark energy. While dark matter helps structure formation, dark energy works against gravity, pushing things apart. It is thought to be a property of space itself, or a new kind of energy field. Dark energy now dominates the energy density of the universe, and its continued influence will determine the ultimate fate of the cosmos. If dark energy remains constant or increases, the universe will continue to expand at an accelerating rate, leading to a cold, empty future, where galaxies move so far apart that they become isolated and stars eventually die out. Despite its remarkable success in explaining a vast array of cosmological observations, the Big Bang theory still faces significant challenges and leaves several fundamental questions unanswered. The most prominent question remains what happened before the Big Bang itself. The theory describes the evolution of the universe from a very early hot dense state, but it does not fully explain what initiated that state or what came before it. The singularity at the beginning, where our current laws of physics break down, remains a theoretical hurdle. The precise nature of dark matter and dark energy, which constitute the vast majority of the universe's mass and energy content, also remains unknown. While their effects are observed, their fundamental properties are still a mystery. Furthermore, the mechanisms and precise details of cosmic inflation are still areas of active research and debate. While inflation solves several problems, the exact field that drove it and how it transitioned to the hot Big Bang plasma are not yet fully understood. The realization that our universe is not a static, unchanging entity, but rather a dynamic system that is continuously expanding, is one of the most profound discoveries in the history of science. This understanding fundamentally reshaped our view of the cosmos, moving us away from ancient philosophical notions of an eternal and fixed universe towards a model of cosmic evolution with a definite beginning. The evidence for this expansion is abundant and compelling, primarily rooted in meticulous astronomical observations and the underlying physics of light and gravity. To fully appreciate how we know the universe expands, we must delve into the historical context, the observational methods and the theoretical implications of this remarkable phenomenon. Before the 20th century, the prevailing view of the universe was largely static. Isaac Newton's laws of gravity, for instance, suggested that a static universe would be inherently unstable, eventually collapsing under its own gravitational pull unless it was infinitely large and uniformly distributed. However, such an infinite universe presented its own set of paradoxes. When Albert Einstein developed his theory of general relativity in the early 20th century, which describes gravity as the curvature of space-time, his initial equations also pointed towards a dynamic universe, either expanding or contracting. Uncomfortable with a non-static universe because it conflicted with the then accepted view, Einstein introduced a mathematical term called the cosmological constant into his equations to force the universe to remain static. This term acted as a repulsive force counteracting gravity. This move later became one of his self-confessed biggest blunders in scientific thought. Intriguingly, around the same time, Dutch astronomer Willem de Sitter found solutions to Einstein's equations that described an empty universe that was expanding, demonstrating the inherent dynamism of general relativity even without matter. These early theoretical hints, however, were not yet backed by direct observational evidence. The first significant observational steps towards understanding cosmic expansion were taken by American astronomer Vesto Slipher. Starting in 1912, Slipher began to measure the spectral lines of light coming from distant nebulae, which were then thought to be gas clouds within our own Milky Way galaxy. He noticed that the light from most of these nebulae was shifted towards the red end of the spectrum, a phenomenon known as redshift. This redshift indicated that these objects were moving away from Earth. A smaller number showed blue shift, meaning they were moving towards us. By 1917, Slipher had measured the velocities of 25 such nebulae, and found that almost all of them were receding from us at very high speeds. While Slipher himself did not interpret these redshifts as evidence for a universally expanding cosmos, his meticulous measurements provided the essential data that would later be combined with other discoveries to paint the complete picture of cosmic expansion. At this stage, the true nature of these nebulae as separate galaxies beyond our own was not yet firmly established. The crucial breakthroughs came with the work of Edwin Hubble, building on Slipher's observations. Hubble, another American astronomer, made two pivotal contributions. First, using the powerful 100-inch Hooker telescope at Mount Wilson Observatory, he began to resolve individual stars in some of the nearby spiral nebulae. In particular, he identified Cepheid variable stars in the Andromeda Nebula. Cepheid variables are a type of star whose intrinsic brightness fluctuates in a predictable way, and crucially, there is a direct relationship between their period of pulsation and their absolute luminosity or true brightness. By comparing the apparent brightness of a Cepheid as seen from Earth with its known absolute brightness, astronomers can accurately calculate its distance. Hubble's measurements of Cepheids in Andromeda conclusively proved that it was not a gas cloud within the Milky Way, but an independent galaxy located far outside our own. This discovery shattered the long-held belief that the Milky Way comprised the entire universe, and established the existence of countless other galaxies. Having established that these nebulae were indeed distant galaxies, Hubble then proceeded to combine his distance measurements with Slipher's existing recessional velocity data. In 1929, he published his groundbreaking finding that there was a direct and proportional relationship between the distance of a galaxy from Earth and its recessional velocity. This relationship became famously known as Hubble's law. It states that the farther away a galaxy is, the faster it appears to be moving away from us. Mathematically, this can be expressed very simply, where the velocity is equal to the Hubble constant multiplied by the distance. The Hubble constant represents the rate at which the universe is expanding. This discovery was a monumental paradigm shift. It provided the first compelling observational evidence that the universe was not static but was actively expanding. Understanding redshift is central to comprehending cosmic expansion. When most people think of redshift, they often think of the Doppler effect, which explains why the pitch of an ambulance siren changes as it moves towards or away from you. For sound waves, a moving source compresses the waves ahead of it and stretches them behind it, leading to a higher or lower pitch. A similar effect occurs with light waves. If a light source is moving away from an observer, its light waves are stretched, making them appear redder. If it is moving towards the observer, its light waves are compressed, making them appear bluer. While the Doppler effect explains the redshift of nearby stars and galaxies due to their individual motions through space, the redshift observed from distant galaxies is overwhelmingly due to a different phenomenon called cosmological redshift. Cosmological redshift is not caused by galaxies moving through space, but by the expansion of space itself between the galaxies. Imagine drawing dots on the surface of an uninflated balloon. As you inflate the balloon, the dots move farther apart from each other, not because they are crawling across the balloon surface, but because the surface itself is stretching. Similarly, in the expanding universe, the light waves travelling from a distant galaxy are stretched as the space they are traversing expands. The wavelength of the light increases, shifting it towards the red end of the spectrum. The greater the expansion of space between the emission point and the observation point, the greater the cosmological redshift. Therefore, redshift from distant galaxies serves as a direct measure of how much the universe has expanded since the light was emitted. Observing highly redshifted light means we are looking at light from very distant galaxies that was emitted when the universe was much younger and smaller. Further observational confirmations of cosmic expansion came in later decades, especially with the use of Type Ia supernovae as standard candles. Type Ia supernovae are powerful stellar explosions that occur when a white dwarf star in a binary system accumulates enough matter from its companion to exceed a critical mass limit known as the Chandrasekhar limit. Because they explode at a very consistent mass, their peak intrinsic luminosity, or absolute brightness, is remarkably uniform. This makes them excellent standard candles, meaning their true brightness is known. By comparing their observed apparent brightness with their known absolute brightness, astronomers can determine their distance with high accuracy, even across vast cosmic distances. Observations of Type Ia supernovae at very large redshifts confirmed Hubble's law at greater distances, and unexpectedly revealed in the late 1990s that the universe's expansion is not only happening, but is actually accelerating. This led to the revolutionary concept of dark energy, which is thought to be responsible for this accelerating expansion. The discovery of dark energy provided yet another layer of evidence for the dynamic nature of the cosmos, and deepened our understanding of its expansion history. The implications of an expanding universe for its past are profound. If the universe is expanding now, it means that in the past it must have been smaller and denser. Tracing this expansion backward in time leads us to a point where all matter and energy were concentrated into an incredibly hot and dense state. This theoretical point is the Big Bang singularity, the conceptual beginning of the universe as we understand it. The expansion implies a dynamic evolving universe rather than a static one. It suggests a finite age for the cosmos, and a specific starting point for its observable history. The rate of expansion encapsulated by the Hubble constant allows astronomers to estimate the age of the universe. By inverting the expansion rate, we can approximate how long it has taken for the universe to reach its current size. Early estimates based solely on Hubble's constant were refined over time with the inclusion of factors like the density of matter and the influence of dark energy. Current estimates place the age of the universe at approximately 13.8 billion years, a figure remarkably consistent with various other cosmological measurements. It is crucial to distinguish between the expansion of space itself and the movement of objects through space. While galaxies are moving away from each other, this is not because they are rocketing through a pre-existing empty void. Instead, the very fabric of space-time is stretching and carrying the galaxies along with it. This is why even a galaxy that is gravitationally bound to another, such as the Andromeda Galaxy, which is on a collision course with our Milky Way, can be seen as an exception to the overall cosmic expansion. On local scales, gravity can counteract the expansion pulling objects together. However, on the vast scales of galaxy clusters and beyond, the expansion of space dominates, ensuring that these distant structures move apart. The understanding that the universe has no center and no edge further supports this concept of expanding space. Every observer in every galaxy would see the same pattern of expansion, with distant galaxies receding faster, suggesting that there is no special place in the universe. This is a key aspect of the cosmological principle, which states that on large scales the universe is homogeneous, meaning it is roughly the same everywhere, and isotropic, meaning it looks the same in all directions. Further evidence supporting cosmic expansion comes from observing galaxies at different stages of their evolution. Because light takes time to travel from distant galaxies, when we look far away, we are effectively looking back in time. We see distant, highly redshifted galaxies as they were billions of years ago. Observations show that these early galaxies were generally smaller, less massive and more irregular in shape, compared to the mature spiral and elliptical galaxies we see in our cosmic neighbourhood today. They also had different star formation rates and chemical compositions. This evolution of galaxy populations over cosmic time is precisely what one would expect in an expanding and evolving universe that started from simpler conditions and gradually formed complex structures through gravity. The observation of quasars, which are extremely luminous active galactic nuclei powered by supermassive black holes, also predominantly at high redshift, suggests an era when such energetic phenomena were more common, fitting into a picture of a younger, more active universe. Despite the strong evidence for cosmic expansion, the precise measurement of the Hubble constant remains an area of active research and some debate. Different methods of measurement using various cosmic distance ladders and different types of standard candles yield slightly different values for the Hubble constant, leading to what is sometimes called the Hubble tension. This tension could point to new physics beyond the standard cosmological model, or simply indicate remaining systematic uncertainties in our measurement techniques. Ongoing and future observations with advanced telescopes are aimed at resolving this discrepancy, further refining our understanding of the universe's expansion history and its precise age. The exploration of cosmic expansion also continues to shed light on the mysterious nature of dark energy, which appears to be driving the accelerating expansion. Understanding dark energy is one of the biggest challenges in modern cosmology, with profound implications for the ultimate fate of the universe, whether it will continue to expand indefinitely, become infinitely cold and dilute, or if dark energy itself might change, leading to a different cosmic destiny. The expansion of the universe is not just a scientific fact, but a foundational concept that underpins our entire understanding of the cosmos's past, present and future. The journey back in time to the earliest moments of our universe reveals a state utterly alien to our everyday experience, a universe incredibly hot, unbelievably dense, and filled with a primordial soup of fundamental particles known as plasma. This epoch represents a crucial stage in cosmic evolution, bridging the gap between the unimaginably extreme conditions of the Big Bang's first fractions of a second and the formation of the first stable atoms. Understanding this early universe plasma is essential for comprehending how the elementary building blocks of matter came into existence, how the fundamental forces began to operate independently, and how the raw ingredients for stars and galaxies were forged. Immediately after the very first fractions of a second following the Big Bang, the universe was a place of unimaginable energy. If we consider the moment after the inflationary epoch, when the universe underwent an incredibly rapid expansion, or perhaps directly after the Planck epoch, where all the fundamental forces were unified, the universe was not empty space, but a cauldron of extreme heat and density. Temperatures soared to billions or even trillions of degrees Celsius, far hotter than the core of any star. At such extreme temperatures, matter as we know it could not exist. Atoms could not form, molecules were impossible, and even the nuclei of atoms would instantly break apart. Instead, the universe was filled with a plasma, a state of matter, where particles are ionized, meaning they carry an electric charge. This plasma was not the familiar hot gas we might encounter in a neon sign or a lightning bolt. It was a far more exotic form, a soup of fundamental particles, protons, neutrons, electrons, and their antiparticle counterparts, as well as countless photons of light. In this early universe plasma, the energy density was extraordinarily high. Everything was so compressed and so hot that particles were constantly interacting, colliding, and transforming into other particles. The universe was completely opaque to light because photons could not travel far without colliding with a free electron or other charged particle. It was like being inside an incredibly thick fog where visibility was essentially zero. The energy of the photons was so immense that they would immediately ionize any atom that tried to form, stripping away its electrons. This constant dance of ionization and recombination meant that the universe remained in this charged plasma state for a significant period. To truly understand this plasma state, it is important to briefly consider the fundamental forces of nature. There are 4 known fundamental forces: gravity, which governs the attraction between masses and shapes, large-scale structures; electromagnetism, which governs interactions between charged particles, and is responsible for light-chemical bonds and electricity; the strong nuclear force, which binds quarks together to form protons and neutrons and holds atomic nuclei together; and the weak nuclear force, which is involved in radioactive decay and certain particle interactions. In the extremely hot and dense conditions of the very early universe, it is theorized that these forces were not distinct, but were unified as different manifestations of a single superforce. As the universe expanded and cooled, these forces successively separated or decoupled from each other. Gravity was the first to separate at the Planck epoch, followed by the strong nuclear force, and then the electro-weak force, which later separated into the electromagnetic and weak nuclear forces. The strengths of these forces and the order in which they separated profoundly influenced how particles formed and interacted in the subsequent plasma era. One of the earliest and most exotic phases of this plasma was the quark-gluon plasma. For the first few microseconds after the Big Bang, temperatures were so incredibly high that even protons and neutrons could not exist as stable particles. Instead, the universe was filled with a superheated soup of fundamental particles called quarks and gluons. Quarks are the building blocks of protons and neutrons, while gluons are the force-carrying particles that bind quarks together through the strong nuclear force. In this quark-gluon plasma state, the quarks and gluons were not confined within larger particles, but roamed freely, interacting intensely. This state is thought to have existed briefly until the universe cooled to about 1 trillion degrees Celsius, at which point the strong nuclear force became strong enough to bind quarks together, a process known as hadronization. As the universe cooled further, a critical event occurred: a period of matter-antimatter annihilation. In the very early universe, matter and antimatter were created in almost equal amounts. For every particle, like a quark or an electron, there was a corresponding antiparticle, an antiquark or a positron, with the same mass but opposite charge. When a particle and its antiparticle meet, they annihilate each other, converting their mass entirely into energy, usually in the form of photons of light. If matter and antimatter had been perfectly balanced, they would have completely annihilated each other, leaving behind a universe filled only with photons and no matter to form stars, planets, or life. However, observations show that our universe is overwhelmingly composed of matter. This implies that there must have been a tiny imbalance in the early universe. For every billion antimatter particles, there was approximately 1,000,000,001 matter particles. This tiny surplus of matter survived the annihilation epoch and constitutes all the matter we observe in the universe today. This process set the stage for the formation of stable protons and neutrons during the Hadron epoch. After the Hadron epoch, during which protons and neutrons formed the universe, entered the Lepton epoch. During this time, the universe's energy density was still dominated by photons and leptons, which include particles like electrons, positrons, and neutrinos. As the universe continued to expand and cool, The temperature dropped to the point where electrons and positrons also began to annihilate. Similar to the quark annihilation, a tiny excess of electrons survived the annihilation process. Neutrinos, however, being weakly interacting particles, mostly decoupled from the rest of the plasma very early on, forming a cosmic neutrino background that still permeates the universe today, but is extremely difficult to detect. This period also saw the ratio of protons to neutrons being set, which was crucial for subsequent nucleosynthesis. For a significant period, roughly from about 10 seconds to 38,000 years after the Big Bang, the universe was primarily a radiation-dominated era. This means that the energy density of the universe was overwhelmingly dominated by photons of light rather than matter. The expansion rate of the universe during this epoch was dictated by the energy density of these photons. As the universe expanded, the wavelength of these photons stretched and their energy density decreased. While matter was present, it was the dominant presence of these high-energy photons that kept the universe in its plasma state. One of the most critical events that took place within this early universe plasma was primordial nucleosynthesis, or Big Bang nucleosynthesis (BBN). This process occurred when the universe was only a few minutes old, specifically between about 3 minutes and 20 minutes after the Big Bang. At this point, the universe had cooled to temperatures around 1 billion degrees Celsius, still incredibly hot, but cool enough for protons and neutrons to begin to fuse together to form light atomic nuclei. During this brief window, the strong nuclear force allowed protons and neutrons to combine, forming deuterium, which is an isotope of hydrogen containing 1 proton and 1 neutron. Deuterium then quickly fused to form helium-3 and helium-4, the most abundant isotope of helium. Trace amounts of lithium-7 also formed. The temperature dropped too rapidly for heavier elements like carbon or oxygen to form through fusion. The exact proportions of these light elements depended sensitively on the conditions of the early universe, particularly the ratio of protons to neutrons, and the overall density of baryonic or ordinary matter. The remarkable agreement between the observed abundances of these light elements in the universe today and the predictions of Big Bang nucleosynthesis is one of the strongest pillars of the Big Bang model. Throughout this entire plasma era, from the quark-gluon soup to the period of nucleosynthesis, the universe remained fundamentally opaque. Because electrons were not yet bound to atomic nuclei, they were free to move independently. Photons of light could not travel far without colliding with these free electrons. This constant interaction meant that the universe was like an incredibly dense fog or a thick soup of charged particles and light. Any light emitted would be immediately scattered or absorbed, keeping the universe in a state where it was impossible for light to propagate freely. This opacity is a key characteristic of the early universe plasma. The end of the plasma era and the transition to a transparent universe occurred approximately 38,000 years after the Big Bang. By this time, the universe had expanded and cooled significantly, reaching a temperature of about 3000 Kelvin, roughly the surface temperature of a cool star. At this critical temperature, the energy of the photons was no longer sufficient to keep hydrogen and helium nuclei ionized. Electrons could now combine with these nuclei to form stable, electrically neutral atoms of hydrogen and helium. This event is known as recombination, even though it was the first time these particles combined, not a recombination. Once the electrons were bound in neutral atoms, the photons were no longer constantly interacting with free charged particles. These photons were now free to travel across the universe unimpeded. This event is called photon decoupling, and the vast bath of these decoupled photons constitutes the cosmic microwave background CMB radiation. The CMB provides a direct snapshot of the universe when it was in its plasma state, serving as a powerful observational window into the conditions of the very early cosmos. The patterns and slight temperature variations in the CMB reveal the initial tiny density fluctuations that would later grow through gravity to form all the large-scale structures we see in the universe today. The transition from an opaque plasma to a transparent universe marked the end of the radiation-dominated era and the beginning of the matter-dominated era. This also led to the cosmic dark ages, a period where no new light sources existed until gravity finally pulled matter together to form the first stars and galaxies. The early universe plasma was thus the crucible in which the fundamental forces separated the basic particles formed and the initial conditions were set for the vast and complex universe we inhabit. The universe in its earliest moments was a place of extraordinary energy, a realm where familiar matter as we know it had not yet fully coalesced. Following the unimaginably rapid expansion during the inflationary epoch, or the conceptual start from the Planck era, the cosmos was a superheated soup of fundamental particles and energy. This period marks the crucial transition where the raw energy of the Big Bang began to transform into the elementary building blocks of everything that would follow from protons and neutrons to stars and galaxies. Understanding how these fundamental particles emerge from this high-energy soup requires delving into the principles of quantum physics and the behavior of matter at extreme conditions. In the very early universe, radiation dominated. Photons, the particles of light, possessed immense energy due to the extremely high temperatures. According to Albert Einstein's famous equation, E equals mc squared, energy and mass are interchangeable. This principle is fundamental to particle formation in the early universe. When photons carry enough energy, they can spontaneously convert into particle-antiparticle pairs. For example, a high-energy photon can transform into an electron, and its antiparticle a positron. Conversely, when a particle meets its antiparticle, they annihilate each other, converting their mass back into energy in the form of photons. This constant creation and annihilation was the prevailing state of affairs in the universe's initial moments. As the universe expanded, it cooled. The temperature of the cosmos dictated which types of particles could be readily created. Only photons with energy exceeding the combined rest mass energy of a particle-antiparticle pair could produce that pair. In the earliest fractions of a second, when temperatures were highest, even the most massive fundamental particles could be created. As the temperature dropped, only lighter particles could be continuously produced. This dynamic process meant that the universe was a bustling environment of particle production and destruction, constantly in thermal equilibrium, where creation and annihilation rates were balanced. Theoretical physics suggests that at incredibly high energies, beyond what we can replicate in particle accelerators today, the fundamental forces of nature may have been unified. This concept is explored in grand unified theories, or GUITs, which propose that the strong nuclear force, the weak nuclear force and the electromagnetic force were once aspects of a single unified force. Gravity would have separated from this superforce even earlier during the Planck epoch. As the universe cooled and its energy density dropped, these unified forces would have successively decoupled from each other, manifesting as the distinct forces we recognize today. The separation of the strong force from the electro-weak force, for instance, would have played a pivotal role in the subsequent formation of protons and neutrons. The breaking of this grand unified symmetry would have released enormous amounts of energy, contributing to the universe's overall energy budget and influencing particle interactions. The primary constituents of the early universe from which all other matter would form are quarks and leptons. These are considered fundamental particles, meaning they are not known to be made of any smaller components. There are 6 types or flavors of quarks: up, down, charm, strange, top and bottom. Quarks also possess a property called color charge, which is related to the strong nuclear force. Protons and neutrons are made up of combinations of quarks. For example, a proton consists of 2 up quarks and 1 down quark, while a neutron is composed of 1 up quark and 2 down quarks. Leptons are another family of fundamental particles. The most familiar lepton is the electron, which carries a negative electric charge. Other leptons include the muon and the tau, which are heavier cousins of the electron, and 3 types of neutrinos: the electron neutrino, muon neutrino and tau neutrino, which are electrically neutral and interact very weakly with other matter. In the very first moments after the Big Bang, when temperatures were extraordinarily high and particles were constantly being created and annihilated, the universe was a hot, dense soup of quarks, gluons and leptons, along with their corresponding antiparticles. This state is often referred to as the quark-gluon plasma. In this plasma, quarks were not confined within protons and neutrons. The strong nuclear force which binds quarks together was not yet strong enough to overcome the high kinetic energy of the individual quarks. They moved freely, interacting through the exchange of gluons, which are the force-carrying particles for the strong nuclear force. This state persisted for only a tiny fraction of a second, as the universe continued its rapid expansion and cooling. As the universe expanded further and the temperature dropped to about 1 trillion degrees Celsius, a critical transition occurred. This temperature was low enough for the strong nuclear force to become dominant, leading to the confinement of quarks. This process is known as hadronization. Quarks could no longer exist independently. Instead, they bound together to form composite particles called hadrons. The most important hadrons for the early universe were protons and neutrons, which belong to a class of hadrons called baryons because they are made of 3 quarks. Protons consist of 2 up quarks and 1 down quark, while neutrons consist of 1 up quark and 2 down quarks. This event marked the transition from a quark-gluon plasma to a universe filled with hadronic matter. A profound mystery that arises during this period is the question of baryogenesis, the origin of the observed matter, antimatter, asymmetry in the universe. In the extremely hot conditions of the early universe, fundamental particles and their antiparticles should have been created in almost perfectly equal amounts. For example, for every quark, there should have been an antiquark, and for every electron a positron. If this balance were truly perfect, then as the universe cooled and particles and antiparticles annihilated each other, converting back into energy, the universe would have ended up as a vast sea of photons with virtually no matter left over. However, our universe is clearly composed almost entirely of matter. Stars, planets, galaxies, and all life are made of matter. This means there must have been a tiny imbalance, a slight excess of matter, particles over antimatter particles in the very early universe. Physicist Andrei Sakharov in 1967 outlined 3 fundamental conditions necessary for baryogenesis to occur, and for a matter-antimatter asymmetry to arise from an initially symmetric state. First, there must be baryon number violation, meaning processes that can change the net number of baryons, which are particles like protons and neutrons. Second, there must be C and CP violation, which refers to violations of charge conjugation symmetry and combined charge parity symmetry. These symmetries essentially state that physical laws should be the same for particles and antiparticles, and for particles mirrored in space. If these symmetries are violated, then matter and antimatter can decay or interact differently. Third, there must be out of equilibrium processes, meaning that the universe was expanding and cooling so rapidly that particle interactions could not maintain thermal equilibrium, allowing the matter-antimatter asymmetry to freeze in. While the exact mechanism for baryogenesis is still an active area of research in theoretical physics, various models exist, including those involving grand unified theories or electroweak baryogenesis, but the precise details remain elusive. Regardless of the exact mechanism, the outcome was crucial for existence. A slight excess of matter survived the annihilation epoch, providing the raw material for everything that formed later. After the quarks were confined into protons and neutrons, the universe continued to cool. Electrons and their antiparticles positrons were still abundant. Like the quarks, electrons and positrons were also constantly being created from energetic photons, and then annihilating each other. As the temperature dropped further below the energy threshold required for their production, the remaining electrons and positrons underwent a final wave of annihilation. Just as with the quarks, a tiny surplus of electrons survived this annihilation thanks to similar asymmetry mechanisms that apply to leptons. These surviving electrons would later combine with the newly formed atomic nuclei. Neutrinos, being very weakly interacting particles, essentially stopped interacting with the rest of the matter and radiation in the early universe much earlier than electrons. They decoupled, forming a cosmic neutrino background that still permeates the universe. Today, a faint relic of the lepton epoch that is incredibly challenging to detect. The relative abundance of fundamental particles, specifically the ratio of protons to neutrons, was crucial for the subsequent formation of light elements. Initially, when temperatures were extremely high and the weak nuclear force was active, protons and neutrons could interconvert through interactions involving neutrinos and positrons. For instance, a proton could absorb a positron and convert into a neutron and a neutrino, while a neutron could decay into a proton, an electron and an antineutrino. These reactions kept the numbers of protons and neutrons roughly equal. However, as the universe cooled and the weak interactions became less frequent, neutrons, which are slightly more massive than protons, began to decay into protons, electrons and antineutrinos at a faster rate than protons could convert into neutrons. This process led to a shift in the neutron-to-proton ratio. By the time the universe was about 1 second old, the temperature had dropped to approximately 10 billion degrees Celsius. At this point, the weak interactions effectively froze out, meaning they became too slow to maintain the equilibrium between protons and neutrons. The neutron-to-proton ratio settled at about 1 neutron for every 6 or 7 protons. This specific ratio was critically important because virtually all surviving neutrons would eventually be incorporated into helium nuclei during the process of Big Bang nucleosynthesis. The remaining protons would form the vast majority of hydrogen nuclei. The universe at this stage was essentially a hot dense plasma consisting primarily of free protons, free neutrons, free electrons, and a sea of high-energy photons. The stage was now set for the next major event in the early universe, the formation of the first light atomic nuclei. Even after the fundamental particles had formed and their relative abundances were established, photons still dominated the energy density of the universe. The universe was in what is known as the radiation-dominated era, where the expansion rate was primarily controlled by the energy density of light. These photons continued to constantly interact with the free-charged particles, like protons and electrons, preventing the formation of neutral atoms and keeping the universe opaque until it cooled down much further. The formation of these fundamental particles from a high-energy soup was the essential prerequisite for all subsequent cosmic evolution. The story of the universe's evolution continues from a hot dense plasma of fundamental particles to the formation of the first atomic nuclei, a process known as Big Bang nucleosynthesis, or BBN. This epoch, which occurred just a few minutes after the conceptual Big Bang, is profoundly significant because it explains the observed cosmic abundances of the lightest elements, hydrogen, helium, and lithium, providing one of the strongest pillars of evidence for the entire Big Bang model. Unlike the formation of heavier elements, which takes place inside stars over billions of years, the primordial elements were forged rapidly in the furnace of the early universe under very specific and extreme conditions. For nucleosynthesis to occur, the universe needed to meet precise temperature and density conditions. It had to be hot enough for nuclear fusion reactions to take place, but also cool enough for newly formed nuclei to remain stable without being immediately broken apart by energetic photons. This crucial window of opportunity opened when the universe was approximately 3 minutes old and lasted for only about 17 minutes until the universe was roughly 20 minutes old. During this brief period, the temperature of the cosmos had dropped to about 1 billion degrees Celsius. This temperature was still incredibly high, but sufficiently cool compared to earlier moments to allow for nuclear binding. The density of the universe was also critical, high enough for protons and neutrons to collide and fuse, but not so high that all available neutrons were immediately consumed in reactions, which would have led to an imbalance. The continuous expansion and cooling of the universe played a vital role in setting the precise conditions and eventually halting the nucleosynthesis process. At the onset of Big Bang nucleosynthesis, the universe was primarily composed of free protons and free neutrons, along with a vast sea of electrons and photons. Protons are simply the nuclei of hydrogen atoms, the simplest element. Neutrons, on the other hand, are slightly more massive than protons, and are unstable when they are free, meaning not bound within an atomic nucleus. A free neutron will spontaneously decay into a proton, an electron, and an antineutrino with a half-life of about 10 minutes. In the very early universe before nucleosynthesis began, the weak nuclear force facilitated constant interconversion between protons and neutrons. Reactions like a proton absorbing an electron and becoming a neutron, or a neutron decaying into a proton, kept their numbers in equilibrium. However, as the universe cooled and expanded, the weak interactions became less frequent. By the time the universe was approximately 1 second old, and the temperature had dropped to about 10 billion degrees Celsius, the weak interactions essentially froze out. This meant that the interconversion between protons and neutrons slowed down dramatically. Because neutrons are slightly heavier than protons, and also undergo spontaneous decay, the balance shifted. For every 1 neutron, there were roughly 6 or 7 protons. This precise neutron-to-proton ratio, roughly 1:7, was absolutely critical for the subsequent formation of the light elements. If there had been significantly more neutrons, more helium would have formed. If there had been fewer, or if neutrons decayed faster, then less helium would have formed. The specific ratio determined the ultimate elemental composition of the universe before stars began to form. The first step in Big Bang nucleosynthesis The formation of deuterium, the isotope of hydrogen with one proton and one neutron, presented a significant challenge known as the deuterium bottleneck. Deuterium is a relatively fragile nucleus. In the early moments of the universe, even after the neutron-to-proton ratio froze out, the temperature was still so high that any deuterium that formed would be immediately broken apart by energetic photons. It was like trying to build a sandcastle on a beach being constantly hit by giant waves. The universe needed to cool down sufficiently for deuterium to survive for a long enough period to participate in further nuclear reactions. This deuterium bottleneck effectively delayed the onset of significant nucleosynthesis until the universe was about 3 minutes old, when the temperature had dropped to around 1 billion degrees Celsius. At this temperature, deuterium nuclei became stable enough to withstand the photon barrage. Once deuterium could survive, the floodgates of nuclear fusion opened rapidly. The reactions proceeded quickly, converting almost all of the available neutrons into helium-4 nuclei. Deuterium nuclei would fuse with protons to form helium-3. Deuterium nuclei could also fuse with other deuterium nuclei to form helium-3 plus a neutron, or tritium, which is an isotope of hydrogen with one proton and two neutrons. The helium-3 and tritium then quickly combined to form helium-4, which is a very stable nucleus consisting of 2 protons and 2 neutrons. Because helium-4 is so stable, and the reactions to form it are efficient, virtually all of the neutrons that survived the early neutron decay and were present when nuclear synthesis began ended up locked inside helium-4 nuclei. This process led to a remarkable prediction. The universe should have started with a primordial composition of roughly 75% hydrogen and 25% helium-4 by mass. This percentage is a direct consequence of the 1:7 neutron-to-proton ratio, established earlier as for every 2 protons that make up a hydrogen nucleus, there are 2 protons and 2 neutrons that form a helium-4 nucleus. The remaining protons are just hydrogen nuclei. While hydrogen and helium-4 were the dominant products of Big Bang nucleosynthesis, trace amounts of other light elements were also formed. A small quantity of lithium-7 was produced through a couple of reaction pathways, including the fusion of helium-4 and tritium or beryllium-7, which subsequently decays into lithium-7. However, the amount of these heavier elements formed was extremely small. The conditions in the early universe were simply not suitable for the creation of elements beyond lithium. There are no stable nuclei with atomic masses of 5 or 8, which effectively creates a mass gap, preventing further fusion. For example, if a helium-4 nucleus tried to fuse with a proton or a neutron, it would form an unstable nucleus that would immediately decay. To bridge this gap and form heavier elements like carbon, oxygen, and iron requires a very different set of conditions found only inside stars, where temperatures and densities can be maintained for extended periods, allowing for complex multi-step nuclear reactions. The rapid cooling and expansion of the early universe meant that the nucleosynthesis process stopped after only a few minutes, locking in the primordial abundances of hydrogen, helium, and lithium. The predictions of Big Bang nucleosynthesis are not just theoretical exercises, they are remarkably consistent with observational evidence gathered from various parts of the cosmos. To measure the primordial abundances of these light elements, astronomers look for environments that are as pristine as possible, meaning they have not been significantly contaminated by elements produced later in stars. This often involves observing very old dwarf galaxies or distant gas clouds that show very few heavy elements. For instance, the abundance of deuterium is typically measured by observing the absorption lines in the spectra of light from distant quasars, which pass through intervening clouds of primordial gas. The helium-4 abundance is measured in the gas clouds of the most metal-poor blue compact dwarf galaxies, where star formation has been minimal. Even the trace amounts of lithium-7 are measured in the atmospheres of very old stars in the Milky Way halo, which are thought to have formed from nearly primordial gas. The fact that the observed abundances of hydrogen, deuterium, helium, 3 helium-4 and lithium-7 closely match the precise predictions of Big Bang nucleosynthesis is one of the most powerful pieces of evidence supporting the hot, dense early universe scenario described by the Big Bang model. The success of Big Bang nucleosynthesis goes beyond simply explaining the existence of these light elements. It also serves as a powerful constraint on various cosmological parameters. For example, the predicted abundances of the light elements are sensitive to the density of baryonic or ordinary matter in the universe. By comparing the observed abundances with BBN predictions, scientists can determine the cosmic baryon density. This independently confirms the baryon density derived from observations of the cosmic microwave background, a completely different set of data. The agreement between these independent measurements strengthens our confidence in the fundamental parameters of the universe. Furthermore, BBN predictions were sensitive to the number of light neutrino types. Before direct measurements confirmed it, BBN calculations already strongly suggested there are precisely 3 types of light neutrinos, which was later confirmed by particle physics experiments. While Big Bang nucleosynthesis is a triumphant success, there is one persistent anomaly known as the lithium problem. Observations of primordial lithium-7 abundance in very old stars seem to be consistently lower than the predictions of BBN by a factor of about 2 to 3. This discrepancy is a puzzle that remains an active area of research. Possible solutions include inaccuracies in stellar atmosphere models that affect lithium measurements, new physics beyond the standard model that could alter lithium production or destruction in the early universe, or subtle systematic errors in our understanding of the nuclear reactions themselves. Despite this one unresolved issue, the overall agreement of BBN with observations for hydrogen and helium is so compelling that it remains a cornerstone of modern cosmology. The products of Big Bang nucleosynthesis, the bare nuclei of hydrogen and helium, were the basic building blocks that would later form the vast majority of the visible matter in the universe. These nuclei would remain in a hot ionized plasma state until the universe cooled enough for electrons to combine with them, forming neutral atoms and setting the stage for the cosmic dark ages and the eventual formation of stars and galaxies. The cosmic microwave background, or CMB radiation, stands as one of the most compelling pieces of evidence supporting the Big Bang theory, a faint echo of the universe's fiery beginning. It is a pervasive glow of a microwave light filling all of space uniform in all directions and represents a direct snapshot of the universe when it was only about 38,000 years old. Its discovery and subsequent detailed study have revolutionized our understanding of cosmology, revealing not only the universe's past but also its fundamental properties and composition. The existence of a cosmic background radiation was first theoretically predicted in the mid-20th century. In the late 1940s, physicists George Gamow, Ralph Alpher and Robert Herman, working on Big Bang nucleosynthesis, proposed that if the universe began in an incredibly hot and dense state, then as it expanded and cooled, there should be a leftover glow of radiation permeating space today. They reasoned that this radiation would have cooled significantly over billions of years due to the universe's expansion, shifting its wavelength from visible light to much longer microwave wavelengths. They even estimated its temperature to be a few Kelvin above absolute zero. Their prediction was based on the idea that the early universe would have been so hot and dense that matter and radiation would have been tightly coupled, interacting constantly, creating an opaque plasma. As the universe expanded and cooled, a critical point would be reached where matter and radiation would decouple, allowing the radiation to travel freely. This surface of last scattering would imprint its characteristics on the escaping photons. Despite these predictions, the cosmic microwave background was discovered quite by accident in 1964 by 2 American radio astronomers, Arno Penzias and Robert Wilson, working at Bell Telephone Laboratories in Holmdel, New Jersey. They were conducting tests on a large horn antenna originally built for satellite communication experiments. Their goal was to detect faint radio waves reflected off balloon satellites. However, no matter where they pointed the antenna, they detected a persistent low-level hiss or static that seemed to come uniformly from all directions in the sky. This noise was equivalent to a temperature of about 3.5 Kelvin. Puzzled by this persistent signal, they meticulously tried to identify and eliminate all possible sources of interference. They cleaned the antenna, removing what they famously described as white dielectric material left by pigeons nesting inside it. They checked for radar interference military signals and even radio broadcasts from New York City, but the noise persisted always there, always uniform. Unaware of the theoretical predictions, Penzias and Wilson were at a loss to explain the mysterious signal. Coincidentally, a group of physicists at Princeton University led by Robert Dicke was independently working on a project to search for exactly this kind of cosmic background radiation, as predicted by Big Bang theory. They were preparing to build their own antenna to detect it. When Penzias and Wilson contacted Dickey to discuss their unexplained noise, Dickey immediately realised what they had stumbled upon. He famously told his colleagues, "Boys, we've been scooped." The persistent uniform microwave hiss detected by Penzias and Wilson was indeed the cosmic microwave background radiation, the cooled-down afterglow of the Big Bang. This accidental discovery provided powerful observational confirmation of the Big Bang model and earned Penzias and Wilson the Nobel Prize in Physics in 1978. The cosmic microwave background exhibits several fundamental properties that are crucial to its significance. Firstly, its spectrum is an almost perfect blackbody spectrum. A blackbody is an idealized object that absorbs all incident electromagnetic radiation and emits radiation at a characteristic spectrum that depends only on its temperature. The CMB's blackbody curve is a hallmark of thermal equilibrium, indicating that the radiation originated from a state where matter and radiation were in complete balance. This is precisely what is expected from a hot, dense early universe. Secondly, its temperature is precisely measured to be about 2.725 Kelvin, just under 3 degrees above absolute zero. This exceedingly cold temperature is a result of the universe's expansion over 13.8 billion years, which has stretched the original high-energy photons to much longer lower-energy microwave wavelengths. Thirdly, the CMB is remarkably isotropic, meaning it is almost perfectly uniform in temperature across the entire sky. This uniformity indicates that the early universe was incredibly smooth and homogeneous, on large scales a crucial piece of information for understanding subsequent structure formation. The CMB is a direct witness to a pivotal moment in the universe's history known as the recombination epoch, or the surface of last scattering. Before this epoch, which occurred approximately 38,000 years after the Big Bang, the universe was a hot, dense, opaque plasma. Temperatures were so high that electrons were not bound to atomic nuclei. Instead, electrons and atomic nuclei, mostly protons and helium nuclei, existed as a free sea of charged particles. Photons of light were constantly scattering off these free charged particles, preventing light from travelling far without being absorbed or deflected. The universe was effectively opaque, like a very thick fog. As the universe continued to expand and cool, its temperature eventually dropped to around 3000 Kelvin. At this critical temperature, electrons had sufficiently low energy that they could combine with the atomic nuclei to form stable, electrically neutral atoms of hydrogen and helium. Once electrons were bound in atoms, the universe underwent a dramatic transformation. The free charged particles were largely gone, and photons were no longer constantly interacting with them. The universe suddenly became transparent, allowing photons to travel freely through space for the first time. These photons, which were emitted at the time of recombination, are the cosmic microwave background radiation we observe today. We're essentially looking back in time to the moment when the universe first became transparent to light, hence the term surface of last scattering. The existence and properties of the CMB provide incredibly strong and direct evidence for the Big Bang theory. Its blackbody spectrum at 2.725 Kelvin is exactly what would be expected from the cooled-down remnant of a hot Big Bang. The remarkable uniformity of the CMB across the sky confirms the cosmological principle that the universe is homogeneous and isotropic on large scales. Furthermore, the CMB decisively disproved the steady-state theory, which proposed a continuously creating but unchanging universe, as such a theory could not account for the observed background radiation. The CMB is not just a confirmation, but a foundational pillar upon which modern cosmology rests, providing an indispensable link to the universe's infancy. While the CMB is remarkably uniform, its true power lies in its tiny variations. Initial observations like those by Penzias and Wilson found the CMB to be almost perfectly smooth. However, theoretical models of structure formation predicted that there must be small temperature fluctuations in the CMB. Without these tiny variations, the universe would have remained perfectly smooth and uniform, and gravity would have had no starting points to begin forming the large-scale structures like galaxies and galaxy clusters we see today. In 1992, the Cosmic Background Explorer or COBE satellite made a groundbreaking discovery. After meticulously mapping the entire sky, COBE detected incredibly subtle temperature variations in the CMB at a level of about 1 part in 100,000. These tiny anisotropies or directional variations were exactly what cosmologists were hoping to find. They represented the primordial density fluctuations in the early universe, the seeds from which all cosmic structures would eventually grow through the action of gravity. The significance of these CMB anisotropies cannot be overstated. They are direct evidence of slight overdense and underdense regions in the universe at the time of recombination. Overdense regions were slightly hotter, while underdense regions were slightly cooler. These subtle differences in density meant that gravity would act slightly more strongly in the overdense areas, attracting more matter over billions of years. Conversely, underdense regions would lose matter to their denser surroundings. This gravitational instability provided the positive feedback mechanism necessary for initial tiny fluctuations to grow into the vast cosmic structures we observe today. The existence and precise characteristics of these anisotropies also provided strong support for the theory of cosmic inflation. Inflation predicts that quantum fluctuations in the very early universe would have been stretched to cosmic scales, creating precisely the kind of nearly scale-invariant primordial density fluctuations observed in the CMB. Following COBE, a new generation of dedicated CMB satellites provided increasingly precise measurements of these anisotropies. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, produced a significantly higher resolution map of the CMB anisotropies, further confirming the COBE findings and providing much more detailed information. Then the European Space Agency's Planck satellite, launched in 2009, delivered the most precise and detailed map of the CMB to date, with unprecedented resolution and sensitivity. These missions meticulously mapped the temperature variations across the entire sky, allowing cosmologists to analyze the statistical properties of these fluctuations in exquisite detail. The patterns of these tiny temperature variations in the CMB are not random. They contain a wealth of information about the universe's fundamental properties. The observed peaks and troughs in the CMB power spectrum, which is a statistical representation of the CMB anisotropies, correspond to acoustic oscillations or sound waves that propagated through the hot, dense plasma of the early universe before recombination. As matter and radiation were tightly coupled, the photons created pressure waves. When the universe became transparent, these sound waves were frozen in place, leaving their imprint on the CMB. By analysing the precise positions and heights of these peaks and troughs, cosmologists have been able to determine fundamental cosmological parameters with remarkable accuracy. These parameters include the geometry of the universe, confirming that it is almost perfectly flat, its age, its expansion rate, and the relative densities of ordinary matter, and dark energy. For example, the first peak in the CMB power spectrum strongly supports a flat geometry for the universe, meaning that parallel lines remain parallel, a result with profound implications for the universe's large-scale structure. Beyond temperature anisotropies, the CMB also exhibits polarization. Just as light waves can be polarized in specific directions, the CMB photons also carry information about their polarization. There are two main types of CMB polarization: E modes and B modes. E modes are generated by density variations in the early universe and have been robustly detected. B modes, however, are more elusive. They can be generated by two mechanisms: the lensing of E modes by foreground galaxy clusters, which distorts the light on its journey to us, or more excitingly, by primordial gravitational waves created during the inflationary epoch. Detecting primordial B modes would provide direct evidence for inflation and probe physics at incredibly high energies in the universe's infancy. While lensing B modes have been detected, the search for primordial B modes is an ongoing frontier of CMB research, aiming to unlock secrets of the very first moments of the Big Bang. The CMB map, with its hot spots and cold spots, essentially provides a cosmological blueprint. The slightly hotter regions represent areas where the universe was slightly denser and would eventually grow to become clusters of galaxies. The slightly colder regions were underdense and would evolve into cosmic voids. It is the furthest back in time we can see directly, as the universe was opaque before the CMB was released. We cannot see beyond the surface of last scattering, because any light emitted before that time would have been immediately scattered by the dense plasma. The CMB also allows cosmologists to precisely constrain the age of the universe at about 13.8 billion years and confirms its composition with roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The cosmic microwave background continues to be an invaluable tool for cosmologists, offering a wealth of information about the Big Bang, its initial conditions, and the fundamental properties that govern our universe. Its study remains at the forefront of cosmological research, continually refining our understanding of the cosmos. The universe at its birth, as revealed by the cosmic microwave background, was remarkably smooth and uniform. Yet when we look around us today, we observe a universe filled with intricate and massive structures. Stars clustered into galaxies, galaxies grouped into clusters, and these clusters arranged in vast cosmic filaments, separated by immense empty voids. This striking transformation from a nearly homogeneous early state to the highly clumpy universe we inhabit is one of the most compelling narratives in cosmology. The primary sculptor behind this grand cosmic architecture is gravity acting on tiny initial density variations in the primordial universe. The challenge of explaining how such a smooth early universe could evolve into a structured one was a significant problem for cosmologists. If the universe had been perfectly uniform at the time the cosmic microwave background was released, then gravity would have nothing to act upon to create the inhomogeneities we see. A perfectly smooth distribution of matter would remain perfectly smooth as it expanded. Therefore, the existence of galaxies and galaxy clusters today unequivocally points to the presence of initial imperfections, tiny seeds of structure that were present in the very early universe. These seeds are precisely what were detected as the faint temperature anisotropies, or variations in the cosmic microwave background. These are regions where the density of matter was ever so slightly higher or lower than the average. These minute differences measured in parts per 100,000 were the starting points for all the large-scale structures we observe. The origin of these primordial density fluctuations is deeply tied to the physics of the very early universe, particularly the theory of cosmic inflation. Inflation posits that in the first tiny fraction of a second after the Big Bang, the universe underwent an incredibly rapid and exponential expansion. During this rapid stretching, quantum fluctuations, which are tiny random variations in energy that constantly occur at the subatomic level, were stretched to astronomical scales. These quantum fluctuations became the macroscopic density variations that eventually imprinted themselves on the cosmic microwave background. In essence, inflation took quantum fuzziness and blew it up to cosmic proportions, providing the initial gravitational imperfections necessary for structure formation. Once these tiny density variations were established, the universal force of gravity began its patient work. Overdense regions, those areas with slightly more matter than average, exerted a slightly stronger gravitational pull on their surroundings. This stronger gravity would then attract even more matter from the slightly less dense regions around them. As matter flowed into these overdense areas, they became even denser, and their gravitational pull grew even stronger. This process is a classic example of gravitational instability, a positive feedback loop where denser regions grow denser and rarer regions become rarer. The initial tiny fluctuations were amplified over billions of years of cosmic evolution, leading to the formation of the large-scale structures we see. A crucial player in this process of structure formation is dark matter. Ordinary matter, also known as baryonic matter, the stuff that makes up stars, planets, and us, interacts strongly with radiation through electromagnetic forces. In the early universe before recombination, when the universe was an opaque plasma, photons were constantly scattering off free electrons and protons. This tight coupling between ordinary matter and radiation meant that any small density variations in ordinary matter would be quickly smoothed out by the pressure of the photons. It was like trying to create a lump in a very energetic fluid. The pressure would immediately flatten it. If only ordinary matter existed, structure formation would have been severely hampered, and the large-scale structures we observe would not have had enough time to form. However, dark matter behaves very differently. It does not interact with light or other electromagnetic radiation, which is why it is called dark. It only interacts through gravity. Therefore, dark matter was not subject to the smoothing effects of radiation pressure in the early universe. This meant that the density fluctuations in dark matter could begin to grow much earlier than those in ordinary matter even before the recombination epoch. Dark matter fluctuations acted as the gravitational scaffolding or potential wells into which ordinary matter would later fall. This fundamental difference in behavior between dark matter and ordinary matter is essential for explaining the observed distribution of galaxies. Without dark matter, the universe would look very different, perhaps a much more uniform and less structured place. As dark matter fluctuations grew through gravitational instability, they formed large gravitationally bound clumps called dark matter halos. These halos are not visible directly, but their gravitational influence can be inferred from how they affect the rotation of galaxies and the bending of light from distant objects through a phenomenon called gravitational lensing. These dark matter halos served as the cosmic nurseries for galaxy formation. After the recombination epoch, when the universe cooled sufficiently for electrons to combine with protons and helium nuclei to form neutral atoms, ordinary matter decoupled from radiation. Now that ordinary matter was no longer tightly coupled to photons, it could fall into the gravitational potential wells created by the pre-existing dark matter halos. This process allowed ordinary gas to accumulate and eventually collapse to form stars and galaxies within these dark matter structures. The process of structure formation is fundamentally hierarchical or bottom-up. This means that smaller structures formed first and then gradually merged and accreted to form larger ones. Tiny initial dark matter clumps grew and merged to form mini-halos. Within these mini-halos, the first stars formed known as population 3 stars. These very first stars were massive, short-lived, and played a crucial role in ionizing the neutral hydrogen gas that filled the universe after recombination. These smaller structures continued to merge, forming dwarf galaxies and then larger galaxies. Galaxies in turn clustered together to form galaxy groups, and then massive galaxy clusters. This continuous process of merging and accretion builds up the cosmic structures over billions of years. As the hierarchical clustering unfolded, gravity sculpted the universe into a vast and intricate network known as the cosmic web. Cosmological simulations which track the gravitational interactions of billions of particles in a virtual universe consistently reproduce this striking large-scale structure. The cosmic web consists of dense knots, where galaxy clusters reside, elongated filaments of galaxies connecting these knots, and vast empty regions called voids, where very few galaxies are found. This simulated cosmic web remarkably matches the observed distribution of galaxies in large-scale surveys, providing powerful evidence for our understanding of structure formation. Galaxies are not randomly scattered throughout space, but are organized along these filaments and concentrated at their intersections, forming the backbone of the universe's structure. Within the dark matter halos that populate the cosmic web, ordinary gas cooled and collapsed, leading to the formation of galaxies. As gas clouds collapsed, their density increased and eventually ignited star formation. The evolution of galaxies is a complex interplay of star formation feedback from supernovae explosions and active supermassive black holes, galactic winds and mergers with other galaxies. Early galaxies typically appear smaller, more irregular and chemically poorer than the mature spiral and elliptical galaxies we see today. Over billions of years, these smaller galaxies merged and accreted gas, shaping their morphology and enriching their chemical composition through successive generations of stars. Galaxy clusters are the largest gravitationally bound structures in the universe, typically containing hundreds or even thousands of galaxies. These massive structures are predominantly composed of dark matter, with galaxies residing in their gravitational potential wells, and hot X-ray emitting gas filling the space between the galaxies, a relic of their violent formation history. While gravity is the primary architect of structure formation, the influence of dark energy must also be considered, especially on the larger scales. Dark energy is the mysterious component of the universe that is causing its expansion to accelerate. At smaller scales, like within galaxies or even galaxy clusters, gravity remains dominant, pulling matter together. However, on very large scales exceeding roughly a few 100 million light-years, the repulsive effect of dark energy starts to counteract gravity's pull. This means that dark energy effectively limits the growth of the largest possible structures. It prevents very distant galaxy clusters from merging to form even larger structures, and contributes to the accelerating expansion that will eventually carry very distant galaxies out of our observable horizon, making them causally disconnected from us. The interplay between gravity and dark energy shapes the universe's ultimate destiny, determining whether structure formation continues or eventually slows as the universe becomes more dilute. Cosmological simulations have become an indispensable tool for understanding structure formation. These embody simulations typically use supercomputers to track the gravitational interactions of millions or even billions of dark matter particles, and sometimes also include baryonic matter over cosmic timescales. By starting with the initial tiny density fluctuations observed in the CMB, these simulations can accurately reproduce the evolution of the cosmic web, the formation of dark matter halos, and the clustering of galaxies on large scales. They allow cosmologists to test different models of dark matter and dark energy, and to explore various scenarios for galaxy formation. Beyond simulations, observational probes like large-scale galaxy surveys such as the Sloan Digital Sky Survey, weak gravitational lensing which maps the distribution of dark matter by observing how it distorts the light from background galaxies, and X-ray observations of the hot gas in galaxy clusters all provide crucial data that supports and refines our understanding of how cosmic structures formed under the relentless pull of gravity. Despite these successes, several challenges and open questions remain, such as the missing satellite problem, where simulations predict more small satellite galaxies around large galaxies than are observed, and the cusp core problem regarding the central density profiles of dark matter halos. The visible universe, with its galaxies, stars, and planets, represents only a small fraction of what actually exists. For decades, astronomers and physicists have gathered overwhelming evidence pointing to the presence of a mysterious invisible substance that exerts gravitational influence but does not emit, absorb, or reflect light. This enigmatic component of our cosmos is known as dark matter. Its existence is not directly observed, but is inferred from its profound gravitational effects on the motion of visible matter and the large-scale structure of the universe. Understanding dark matter is crucial because it accounts for roughly 27% of the universe's total mass energy content, dwarfing the mere 5% contributed by ordinary baryonic matter, the stuff that makes up everything we can see and touch. The remaining 68% is dark energy, a topic for later discussion. The first hints of unseen mass emerged in the 1930s from the work of Swiss-American astronomer Fritz Zwicky. While studying the Coma cluster of galaxies, Zwicky measured the velocities of individual galaxies within the cluster. He applied the virial theorem, which relates the kinetic energy of a system to its potential energy, to estimate the total mass of the cluster. His calculations revealed a shocking discrepancy. The gravitational mass required to hold the cluster together and prevent its galaxies from flying apart at their observed speeds was far greater than the mass accounted for by the visible galaxies alone. Zwicky famously coined the term dark matter to describe this missing mass, suggesting that there must be some invisible non-luminous material within the cluster exerting gravitational pull. His findings were initially met with skepticism and were not widely accepted for several decades, partly due to the limitations of observational technology at the time and partly because the idea was so radical. Decades later, in the 1970s, the concept of dark matter gained significant traction, thanks to the pioneering work of American astronomer Vera Rubin and her colleagues. Rubin began studying the rotation curves of spiral galaxies. A rotation curve plots the orbital speed of stars or gas at different distances from the galactic center. Based on Newtonian physics and the observed distribution of visible matter in galaxies, astronomers expected that the orbital speeds of stars would decrease as their distance from the galactic center increased, especially beyond the visible edge of the luminous disk. This is similar to how the orbital speed of planets in our solar system decreases with increasing distance from the Sun, as most of the solar system's mass is concentrated in the Sun. However, Rubin and her team consistently found something entirely different. They observed that stars and gas clouds far from the galactic center were orbiting just as fast or even faster than stars closer in. These flat rotation curves indicated that there was a substantial amount of unseen mass extending far beyond the visible boundaries of the galaxy's luminous disk, creating a vast gravitational halo that kept the outer stars in their rapid orbits. This unseen mass could not be explained by ordinary matter in the form of dim stars, gas clouds, or dust, because such matter would still emit some form of radiation or absorb light, making it detectable. The evidence from galaxy rotation curves provided compelling and widespread support for Zwicky's earlier dark matter hypothesis, shifting it from a theoretical curiosity to a widely accepted scientific necessity. Beyond individual galaxies, the evidence for dark matter extends to larger scales such as galaxy clusters. Zwicky's initial observations in the Coma cluster were a testament to this. Modern observations of galaxy clusters continue to bolster the dark matter case. One powerful piece of evidence comes from gravitational lensing. According to Einstein's theory of general relativity, massive objects warp the fabric of spacetime, and light rays travelling through this warped spacetime follow curved paths. This phenomenon, known as gravitational lensing, causes the light from distant background galaxies to be distorted, magnified, or even multiply-imaged as it passes through the gravitational field of a massive foreground galaxy cluster. By precisely measuring the distortions and amplifications of these background galaxy images, astronomers can reconstruct the total mass distribution of the foreground cluster, including both its visible and invisible components. These gravitational lensing maps consistently show that the total mass of galaxy clusters is far greater than the mass of their visible galaxies and hot gas. The distribution of this inferred mass matches the gravitational wells needed to explain the observed lensing effects, strongly indicating the presence of a dominant dark matter component that extends throughout the cluster. Another line of evidence from galaxy clusters comes from X-ray observations. Galaxy clusters are not just collections of individual galaxies. They also contain vast quantities of extremely hot gas that permeates the space between the galaxies. This gas is so hot that it emits X-rays, which can be detected by X-ray telescopes in space. For this hot gas to remain confined within the cluster and not simply escape into intergalactic space, it must be held in place by a powerful gravitational force. By analysing the temperature and distribution of this X-ray emitting gas, astronomers can determine the gravitational potential well required to contain it. These calculations consistently show that the amount of visible matter in the galaxies and the X-ray gas itself is insufficient to provide the necessary gravitational confinement. An additional source of mass, a substantial amount of dark matter, is required to explain the stability and equilibrium of the hot gas in galaxy clusters. Perhaps one of the most direct and visually striking pieces of evidence for dark matter comes from the Bullet cluster. This cluster is actually two galaxy clusters that have recently passed through each other. When these two clusters collided, the ordinary baryonic matter, which includes the hot X-ray emitting gas, interacted and slowed down due to friction. However, the dark matter, which is thought to interact only very weakly with itself and with ordinary matter, passed straight through largely unimpeded. Observations of the Bullet cluster using X-ray telescopes show that the hot gas is located primarily in the centre, between the two original clusters, where it was slowed down by the collision. In contrast, gravitational lensing maps of the cluster show that the vast majority of the mass, including the dark matter, is located at the outskirts of the colliding clusters, precisely where the galaxies are and where the dark matter should have passed through without slowing down. The spatial separation between the visible X-ray gas and the inferred mass distribution provides compelling direct observational evidence for the existence of dark matter as a distinct component of the universe that behaves differently from ordinary matter. The role of dark matter in the formation of cosmic structures is absolutely critical. In the very early universe, about 38,000 years after the Big Bang, the universe was a hot, dense plasma of ordinary matter and radiation. While there were tiny density fluctuations or inhomogeneities present as observed in the cosmic microwave background, these fluctuations in ordinary matter were constantly being smoothed out by the immense pressure of photons. If ordinary matter were the only type of matter present, these fluctuations would have been largely washed away, and there would not have been enough time for the large-scale structures like galaxies and galaxy clusters to form through gravity. The universe would have remained much more uniform and featureless. However, dark matter does not interact with photons or other electromagnetic radiation. It is unaffected by the pressure of radiation. This means that the tiny density fluctuations in dark matter could begin to grow much earlier than those in ordinary matter, even before the universe became transparent. Dark matter fluctuations essentially acted as the gravitational scaffolding, or the gravitational seeds that were able to grow unchecked by radiation pressure. These overdense regions of dark matter gradually accumulated more dark matter through gravity, forming large gravitationally bound clumps called dark matter halos. These halos are invisible themselves, but they created deep gravitational potential wells across the cosmos. Once the universe cooled sufficiently for ordinary matter to form neutral atoms, a process known as recombination, which released the cosmic microwave background radiation, ordinary baryonic matter decoupled from radiation. Now, free from the smoothing effects of photon pressure, the ordinary gas could fall into the pre-existing gravitational wells created by the dark matter halos. As the gas accumulated within these dark matter halos, it became denser and eventually cooled, leading to the formation of the first stars and eventually galaxies. Dark matter provided the necessary gravitational framework and the early start for gravitational collapse, allowing the universe to transition from a relatively smooth state to the highly structured cosmic web we observe today. Without dark matter, the universe's large-scale structure would be fundamentally different, perhaps much less clumpy and structured, and it is highly unlikely that galaxies would have formed in the way they did, or even formed at all within the time frame of our universe's age. The nature of dark matter remains one of the biggest mysteries in modern physics. We know what it is not, but we do not yet know what it is. It is not ordinary baryonic matter, which includes protons, neutrons, and electrons. This is confirmed by Big Bang nucleosynthesis, which accurately predicts the abundance of light elements based on the amount of ordinary matter. If dark matter were baryonic, it would have affected these predictions. Therefore, dark matter must be non-baryonic, meaning it is made of particles that are not part of the standard model of particle physics. Current theoretical models propose various candidates for dark matter particles. The leading candidate is a class of hypothetical particles known as weakly interacting massive particles, or WIMPs. These particles would be massive and would interact very weakly with ordinary matter, primarily through gravity and possibly the weak nuclear force. Their weak interaction would explain why they are so difficult to detect, and why they do not emit or absorb light. Another popular candidate is the axion, a hypothetical extremely light particle, proposed to solve certain problems in quantum chromodynamics, the theory of the strong nuclear force. Other more exotic candidates include sterile neutrinos, primordial black holes, not formed from stellar collapse, or even entirely new fundamental forces. The properties of dark matter also play a crucial role in its ability to form structures. Cosmological simulations strongly favour what is called cold dark matter, or CDM. Cold dark matter particles are defined as moving relatively slowly, so they do not smooth out small-scale density fluctuations. If dark matter were hot, meaning its particles moved at relativistic speeds, it would have streamed out of small overdense regions, washing away small-scale density fluctuations and making it difficult for small galaxies to form. The observed abundance of dwarf galaxies and the detailed structure of galaxies are consistent with cold dark matter. This cold dark matter model combined with the cosmological constant lambda to explain dark energy forms the standard model of cosmology known as lambda CDM. Scientists are actively searching for dark matter particles through various experimental approaches. Direct detection experiments typically involve highly sensitive detectors placed deep underground in mines to shield them from cosmic rays. These detectors aim to observe the rare occasions when a dark matter particle might interact with an atomic nucleus in the detector, producing a tiny recoil that can be measured. Experiments like LuxLZ, Xenon, and Pandex are at the forefront of this search, attempting to directly detect WIMPs. Indirect detection experiments look for the products of dark matter annihilation or decay. If dark matter particles are their own antiparticles, or if they decay, they might produce detectable particles like gamma rays, neutrinos, or cosmic rays. Telescopes like the Fermi Gamma Ray Space Telescope and ground-based gamma ray observatories search for these signals from regions where dark matter is expected to be abundant, such as the galactic center or dwarf galaxies. Finally, collider experiments such as the Large Hadron Collider at CERN aim to produce dark matter particles directly by smashing known particles together at extremely high energies. If dark matter particles are produced, they would escape the detector without interacting, leaving behind a telltale signature of missing energy and momentum. Despite decades of intense search, dark matter particles have not yet been directly detected, underscoring their elusive nature. The presence and behaviour of dark matter have profound implications for our understanding of the universe. It is not just an obscure hypothetical substance, but an essential ingredient for the cosmos to look the way it does. Dark matter explains the stability of galaxies and galaxy clusters, the flat rotation curves of spiral galaxies, and the gravitational lensing effects observed around massive cosmic structures. It provided the necessary gravitational scaffolding for the early universe's tiny density fluctuations to grow into the vast cosmic web of galaxies and clusters. Without dark matter, our entire cosmological model would fall apart. It is a fundamental component of the universe, driving the formation of the very structures that allow us to exist and observe the cosmos. While its precise nature remains one of the most tantalizing mysteries in science, the evidence for its gravitational influence is overwhelming, making dark matter an indispensable part of our cosmic story. The universe is expanding, a fact firmly established by Edwin Hubble's observations in the late 1920s. For many decades, cosmologists assumed that this expansion, while ongoing, would gradually slow down due to the gravitational pull of all the matter within the universe. It was thought that gravity acting on everything would cause a deceleration, much like a ball thrown upwards slows down as gravity pulls it back. However, in the late 1990s, a groundbreaking discovery completely upended this long-held assumption. Observations of distant supernovae revealed that the universe's expansion is not slowing down, but is in fact accelerating. This astonishing finding pointed to the existence of a mysterious cosmic component with repulsive gravity, now known as dark energy. Dark energy represents approximately 68% of the universe's total mass energy content, making it the dominant component of our cosmos. Its existence and properties profoundly influence the universe's past, present, and future. The concept of a cosmological constant, or a form of energy inherent to space itself, was first introduced by Albert Einstein in 1917 when he was developing his theory of general relativity. As previously mentioned, Einstein initially added this term to his equations to force a static universe, which was the prevailing belief at the time. After Hubble's discovery of the expanding universe, Einstein famously called the cosmological constant his biggest blunder. For decades, the cosmological constant was largely discarded from mainstream cosmology. However, its ghost lingered in the background as a potential explanation for various cosmic phenomena. The reintroduction of a cosmological constant, or a similar form of dark energy, into cosmological models became essential to explain the accelerating expansion. The pivotal evidence for accelerating expansion came from independent studies of Type Ia supernovae conducted by two competing research teams in the late 1990s. These teams were the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees. Both teams were using Type Ia supernovae as standard candles to measure cosmic distances. Type Ia supernovae are powerful stellar explosions that occur when a white dwarf star in a binary system accumulates enough matter from a companion star to exceed a critical mass limit known as the Chandrasekhar limit. Because they explode at this consistent mass, their peak intrinsic luminosity, or absolute brightness, is remarkably uniform and very high, making them visible across vast cosmic distances. By comparing the observed apparent brightness of a Type Ia supernova with its known absolute brightness, astronomers can accurately determine its distance. This method provides a direct way to measure how much the universe has expanded since the light from the supernova was emitted. Both research teams observed Type Ia supernova in very distant galaxies and found an unexpected result. The distant supernovae were dimmer than they should have been if the universe's expansion was decelerating or even expanding at a constant rate. Their unexpected dimness implied that they were farther away than predicted by a decelerating universe. The only way to explain this additional distance was if the universe's expansion had been accelerating over cosmic time. This meant that the space between us and these distant supernovae had expanded more than expected during the light's journey. The stunning and independent agreement between the two teams led to the groundbreaking conclusion that the universe's expansion is accelerating. This discovery earned Perlmutter, Schmidt and Rees the Nobel Prize in Physics in 2011. Beyond Type Ia supernovae, other lines of evidence consistently support the existence and properties of dark energy. One of the most important comes from the cosmic microwave background, or CMB radiation. The CMB provides a snapshot of the universe when it was only about 38,000 years old. By analysing the precise patterns of temperature fluctuations in the CMB, particularly the locations and heights of its acoustic peaks, cosmologists can determine the overall geometry of the universe and the relative proportions of its energy components, including ordinary matter, and dark energy. The CMB data from missions like WMAP and Planck confirm that the universe is spatially flat, meaning that parallel lines remain parallel on cosmic scales. For a universe to be flat, its total energy density must be equal to a critical density. When astronomers add up the observed densities of ordinary matter and dark matter, they find that they only account for about 32% of the critical density needed for a flat universe. The remaining approximately 68% must be contributed by something else, and that something else is dark energy. The CMB data is remarkably consistent with the supernova observations, reinforcing the conclusion that dark energy is the dominant component of the universe's energy budget. The distribution of a large-scale structure in the universe also provides evidence for dark energy. Dark energy affects the growth of cosmic structures such as galaxies and galaxy clusters. If dark energy were not present, gravity would continue to pull matter together, forming progressively larger and denser structures. However, the repulsive effect of dark energy counteracts gravity on large scales, slowing down the rate at which structures grow. By studying the clustering of galaxies and the abundance of galaxy clusters at different cosmic epochs, astronomers can infer the influence of dark energy. A specific signature in the distribution of galaxies known as baryon acoustic oscillations, or BAOs, acts as a standard ruler in the cosmos. BAOs are fossilized sound waves from the early universe that imprinted a characteristic scale on the distribution of matter. By measuring this characteristic scale at different distances, astronomers can determine the universe's expansion history. Measurements of BAOs from large galaxy surveys independently confirm the accelerating expansion and are consistent with the properties of dark energy derived from supernovae and CMB data. The fundamental characteristic of dark energy that causes cosmic acceleration is its negative pressure. In general relativity, gravity is not just caused by mass, but by energy and pressure as well. Positive pressure like that of ordinary gas creates an attractive gravitational effect. However, a substance with negative pressure creates a repulsive gravitational effect, pushing space-time apart. The vacuum energy, which is a candidate for dark energy, possesses this negative pressure. Imagine if empty space itself had a constant intrinsic energy density. As the universe expands, the volume of space increases, but the energy density of this vacuum energy remains constant because new space is continuously being created with this energy. This property ensures that as the universe expands, the total amount of dark energy increases, leading to an ever stronger repulsive force that drives the acceleration. The leading theoretical explanation for dark energy is the cosmological constant, which represents the energy of empty space itself, or vacuum energy. According to quantum mechanics, even a vacuum is not truly empty, but is filled with virtual particles constantly popping in and out of existence. These quantum fluctuations should contribute to the vacuum energy. However, theoretical calculations of this vacuum energy yield an astronomically large value, many orders of magnitude greater than what is observed for dark energy. This discrepancy, known as the cosmological constant problem, or the vacuum catastrophe, is one of the biggest unsolved puzzles in physics. It suggests that our understanding of vacuum energy is incomplete, or that there is some unknown mechanism that cancels out most of this energy, leaving only the tiny but significant amount we observe as dark energy. Alternative theories propose that dark energy is not a constant but a dynamic field, whose energy density can change over time. These models are broadly grouped under the term quintessence. Quintessence theories propose the existence of a new type of scalar field that permeates the universe, similar to the Higgs field. The energy density of this field could evolve over cosmic time, potentially explaining why dark energy became dominant relatively recently in the universe's history. However, these models introduce additional complexity and require specific properties for this hypothetical field that are not yet confirmed by observations. Another set of theories attempts to explain the accelerating expansion, not by introducing a new energy component, but by modifying Einstein's theory of gravity itself on large cosmological scales. These modified gravity theories suggest that gravity behaves differently over vast distances or at very low curvatures of space-time, perhaps becoming repulsive at large scales. While intriguing, these models must be carefully constructed to remain consistent with all existing gravitational observations from the solar system to galaxy clusters. Dark energy's ultimate influence on the fate of the universe is profound. Its continued dominance will determine the long-term cosmic future. If dark energy remains a cosmological constant with a constant energy density, the universe will continue to expand at an accelerating rate indefinitely. This scenario, often referred to as the Big Freeze or heat death, would lead to a cold, empty, and extremely dilute universe. As space expands exponentially, distant galaxies would eventually recede from us faster than the speed of light, becoming causally disconnected and disappearing beyond our observable horizon. Eventually, even local galaxies might be gravitationally torn apart in an extreme version of this expansion, leaving behind a cold universe where stars eventually die out, and even black holes evaporate through Hawking radiation, leading to a state of maximum entropy. Other more speculative scenarios for the universe's fate depend on how dark energy might evolve. If dark energy's density were to increase over time, becoming even stronger and more repulsive, it could lead to a big rip. In this extreme scenario, the accelerating expansion would become so powerful that it would overcome even the forces holding atoms together, eventually ripping apart galaxies, stars, planets, and even atoms themselves. Conversely, if dark energy were to eventually dissipate or reverse its sign, it could potentially lead to a scenario where gravity eventually reasserts its dominance, causing the universe to stop expanding and eventually collapse back into a singularity, a big crunch resembling a reverse Big Bang. However, current observations strongly favour the cosmological constant scenario, suggesting a universe headed towards a big freeze. The existence of dark energy also poses a cosmic coincidence problem. Why is it that dark energy, which only became dominant relatively recently, is now of a comparable density to matter, just at the time when intelligent life has emerged to observe it? If dark energy had been dominant, much earlier structures like galaxies would not have formed. If it had only appeared much later, the universe would have spent a much longer time in a matter-dominated phase. This apparent coincidence might be a mere happenstance, or it could point to a deeper connection between the universe's properties and the emergence of observers, perhaps hinting at concepts like the anthropic principle, or a multiverse where our universe is one of many with different cosmological parameters. This problem is another key area of active research. The study of dark energy continues to be at the forefront of cosmological research. Future observatories and experiments such as the Nancy Grace Roman Space Telescope Euclid and the Vera C. Rubin Observatory are designed to make more precise measurements of dark energy's properties. By mapping the distribution of galaxies and supernovae across vast cosmic volumes, these missions aim to constrain whether dark energy is truly a constant or if its properties change over time, potentially distinguishing between the cosmological constant and quintessence models, or even ruling out some modified gravity theories. Unraveling the nature of dark energy is perhaps the biggest puzzle facing modern physics, with profound implications for our understanding of gravity, quantum mechanics, and the ultimate destiny of the universe itself. The traditional understanding of the universe before the 20th century viewed space as a fixed three-dimensional stage and time as a separate universally flowing river. Events unfolded on this stage and time ticked by uniformly for everyone everywhere. This intuitive picture, deeply embedded in our everyday experience, formed the bedrock of Newtonian physics, which successfully described motion and gravity for centuries. However, this classical framework was fundamentally challenged and ultimately transformed by the revolutionary insights of Albert Einstein, particularly his theories of special and general relativity. These theories dramatically reshaped our understanding of space-time gravity and the very fabric of reality, demonstrating that space and time are not independent entities, but are intricately interwoven into a single, four-dimensional continuum known as space-time. This unified concept lays the essential groundwork for grappling with the profound question of the universe's origin and the nature of time itself. Einstein's journey began with the special theory of relativity published in 1905. This theory deals with the relationship between space and time for objects moving at constant velocities relative to each other in the absence of gravity. It is built upon two fundamental principles that Einstein took as given based on experimental evidence and logical consistency. The first postulate is the principle of relativity, which states that the laws of physics are the same for all observers in uniform motion relative to one another. This means that if you are in a windowless room moving at a constant speed, you cannot perform any experiment to determine if you are moving or at rest. All physical laws, electricity, magnetism, mechanics, behave identically regardless of your constant velocity. This idea was not entirely new, as Galileo had hinted at it centuries before for mechanical laws. However, Einstein extended it to all laws of physics, including electromagnetism. The second and more revolutionary postulate is the principle of the constancy of the speed of light. This states that the speed of light in a vacuum, denoted by c, is the same for all observers regardless of their own motion, or the motion of the light source. This was a radical departure from classical physics, where velocities simply added and subtracted. If you threw a ball forward on a moving train, the ball's speed relative to the ground would be its speed relative to the train plus the train's speed. But for light, this does not happen. Whether you are moving towards a light source or away from it at high speed or standing still, you will always measure the speed of light to be exactly approximately 300,000 kilometers per second. This seemingly simple postulate has profound and counterintuitive consequences for the nature of space and time. The implications of these two postulates are far-reaching and challenge our everyday notions of time and distance. One of the most famous consequences is time dilation. This phenomenon means that time passes more slowly for an object that is moving relative to an observer compared to an identical object that is at rest relative to the observer. Imagine two identical clocks, one on a fast-moving spaceship and one on Earth. An observer on Earth would see the clock on the spaceship ticking more slowly than the clock on Earth. Conversely, an observer on the spaceship would see the clock on Earth ticking more slowly. This is not just an illusion, but a real physical effect that has been experimentally verified countless times, for example, with atomic clocks on airplanes, or with subatomic particles called muons that are created in the Earth's atmosphere. Muons have a very short lifetime, but when they travel at speeds close to light, their lifetime appears to be extended from our perspective, allowing them to reach the Earth's surface before decaying. Time is not absolute but relative to the observer's motion. Another startling consequence of special relativity is length contraction. This means that the length of an object measured by an observer is shorter in the direction of its motion relative to that observer compared to its length when it is at rest. If a spaceship is moving at a very high speed past Earth, an observer on Earth would measure the spaceship to be shorter in its direction of motion than its length would be if it were stationary. Again, the effect is mutual. An observer on the spaceship would measure Earth to be shorter in the direction of its motion. Like time dilation, length contraction is a real physical effect, although it only becomes noticeable at speeds approaching the speed of light. Special relativity also introduces the concept of relative simultaneity. Two events that appear to happen at the same time for one observer may not appear simultaneous for another observer who is in motion relative to the first. This means there is no universal now. The concept of past, present and future depends on the observer's frame of reference. This challenges the very notion of a single universal timeline. What is the past for one observer might still be the future for another, highlighting the interconnectedness and relativity of time and space. Perhaps the most famous outcome of special relativity is the equivalence of mass and energy encapsulated in the iconic equation E equals mc squared. This equation states that mass and energy E are interchangeable, and are simply different forms of the same fundamental entity. A tiny amount of mass can be converted into an enormous amount of energy, because c squared is a very large number. This principle underlies nuclear processes such as those in atomic bombs and nuclear power plants. It implies that mass itself is a form of energy, and that changes in a system's energy will be accompanied by changes in its mass. This equation revolutionized physics, demonstrating that mass and energy are not conserved separately, but rather their combined total is conserved. The insights from special relativity hinted that space and time were not separate but intrinsically linked. This led Hermann Minkowski, Einstein's former mathematics professor, to formalize the concept of space-time. Minkowski realized that if time and space measurements were relative to an observer's motion, then they must be parts of a single, four-dimensional entity, a unified fabric. He famously declared, "The views of space and time which I wish to lay before you have sprung from the soil of experimental physics. Hereafter, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. In this four-dimensional space-time, events are points, and the paths of objects through space-time are called world lines." While special relativity successfully described physics in the absence of gravity, it was Einstein's next great triumph, general relativity, that truly unveiled the profound nature of space-time. Einstein spent another decade grappling with the problem of incorporating gravity into his new relativistic framework. Newtonian gravity described gravity as a force that acted instantaneously across vast distances, a concept incompatible with the finite speed limit imposed by special relativity. Furthermore, Newton's theory did not explain how gravity actually worked. Einstein's breakthrough came with the realization that gravity is not a force in the traditional sense, but rather a manifestation of the curvature or warping of spacetime itself, caused by the presence of mass and energy. He published his general theory of relativity in 1915. The central idea of general relativity is captured by the equivalence principle, which states that gravity and acceleration are fundamentally indistinguishable. Imagine being in a windowless elevator. If the elevator is accelerating upwards in space, far from any gravitational source, you would feel pressed to the floor just as if you were standing in a gravitational field on Earth. Conversely, if the elevator cable broke and it was falling freely in a gravitational field, you would experience weightlessness just as if you were floating in space. This indistinguishability between acceleration and gravity led Einstein to his revolutionary insight that gravity is not a force pulling objects, but rather a consequence of the geometry of spacetime. In general relativity, spacetime is a dynamic and pliable fabric. Mass and energy cause this fabric to curve or warp. Think of a heavy bowling ball placed on a stretched rubber sheet. The bowling ball creates a dip in the sheet. If you then roll a marble across the sheet near the bowling ball, the marble will not move in a straight line, but will curve inwards towards the bowling ball, not because the bowling ball is pulling it with a force, but because the sheet itself is curved. Similarly, planets orbit the Sun, not because the Sun exerts a mystical force on them, but because the Sun's immense mass warps the spacetime around it, and the planets simply follow the shortest path, the geodesics, in this curved spacetime. The greater the mass or energy, the greater the curvature of spacetime. This explains gravity in terms of geometry rather than a force. General relativity made several groundbreaking predictions that have since been confirmed by observation and experiment. One of the earliest and most famous confirmations was the bending of light by gravity. Einstein predicted that light rays passing near a massive object like the Sun would be deflected from their straight path because the Sun's mass curves the spacetime around it. During a solar eclipse in 1919, British astronomer Arthur Eddington led an expedition that observed stars whose light passed close to the eclipsed Sun. They found that the apparent positions of these stars were shifted precisely as predicted by Einstein's theory. This dramatic confirmation propelled Einstein to international fame and solidified general relativity's standing. Another key prediction is gravitational redshift. This refers to the phenomenon where light waves lose energy, and their wavelength stretches, becoming redder as they climb out of a gravitational well. Conversely, light waves gain energy and become bluer as they fall into a gravitational well. This effect has been verified in laboratories using atomic clocks and has also been observed with light from massive stars and galaxy clusters. For example, photons escaping from the strong gravitational field of a white dwarf star lose energy and are therefore redshifted. Perhaps the most dramatic and relatively recent confirmation of general relativity is the detection of gravitational waves. These are ripples in the fabric of spacetime itself generated by extremely violent and energetic cosmic events, such as the collision of black holes or neutron stars. Einstein predicted the existence of these waves, but their direct detection proved incredibly challenging due to their tiny amplitude. After decades of technological development, the Laser Interferometer Gravitational Wave Observatory, or LIGO project, first directly detected gravitational waves in 2015, originating from the merger of two black holes. This monumental discovery opened up a whole new window for observing the universe, allowing us to study cosmic phenomena that do not emit light, providing further powerful confirmation of general relativity's accuracy. Other predictions include the precession of Mercury's orbit, which Newtonian gravity could not fully explain, and the existence of black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are extreme manifestations of space-time curvature, where mass is compressed into an incredibly small volume, creating a singularity at their core. The study of black holes and their properties is an active area of research, further testing the limits of general relativity. The profound implication of space-time as a unified four-dimensional fabric is particularly relevant when considering the origin of time. In the classical Newtonian view, time was an independent parameter that flowed uniformly regardless of anything else. But in relativity, time is intertwined with space and can be affected by motion and gravity. Time is not absolute. This means that if space-time itself has a beginning, as suggested by the Big Bang model, then time itself must have also had a beginning. It is not that the universe began in pre-existing time. Rather, time, along with space and matter energy, came into existence with the Big Bang. This conceptual shift is crucial. When we talk about before the Big Bang, it is not in the sense of a clock ticking prior to the universe's existence. If space-time itself began at the Big Bang singularity, then the concept of before loses its conventional temporal meaning. It is like asking what is north of the North Pole. The question assumes a direction that ceases to exist at that point. Similarly, asking what happened before time began assumes a temporal framework that may not have existed. This idea lays the fundamental groundwork for understanding the philosophical and scientific challenges of discussing the universe's ultimate origin, as it forces us to rethink our most basic assumptions about the nature of time itself. The concept of space-time fundamentally ties the question of the universe's beginning to the very origin of time. The understanding of space-time as a unified and dynamic entity is therefore not just an abstract mathematical construct, but a deeply physical reality confirmed by a century of experiments and observations. It is the stage upon which the cosmic drama unfolds, and its curvature is the very essence of gravity. This framework provides the essential conceptual tools to explore the universe's past, its current state, and its future fate. It prepares us for the mind-bending questions surrounding the Big Bang singularity and the potential emergence of time from a state that defies our everyday temporal intuition. The unified nature of space and time is a cornerstone of modern physics and an indispensable guide to the mysteries of cosmic origins. The question of what existed before the Big Bang is one of the most profound and perplexing inquiries in cosmology and philosophy. Our everyday intuition dictates that every event must have a cause, and that there must always be a before for any given now. However, the standard Big Bang model, which describes the universe's evolution from an extremely hot, dense state, presents a radical challenge to this intuition. If space-time itself, the very fabric of space and time as we understand it, came into existence with the Big Bang, then the concept of before the Big Bang loses its conventional meaning. It is not merely a question of what was there, but rather whether the notion of a temporal there even applies. From a purely scientific perspective, the standard Big Bang model describes the universe's expansion from an initial singularity, a point of infinite density and temperature. At this singularity, the equations of general relativity which describe gravity and space-time break down. They do not tell us what happened at the singularity or what preceded it. This breakdown signifies a limit to our current physical theories. If space-time emerged from this singularity, then there was no time in the conventional sense for anything to exist before it. It's akin to asking what is south of the South Pole. The concept of south ceases to have geographical meaning beyond that point. Similarly, before might be a concept that applies only within the universe's timeline, not outside or prior to it. This scientific boundary immediately leads to philosophical challenges. Philosophers have grappled with the concept of nothingness and causality for millennia. The idea of something arising from literally nothing The absence of even space and time seems deeply counterintuitive. For many philosophical traditions, creation is often seen as the rearrangement of pre-existing material or an emanation from a divine source, rather than an absolute coming into being from absolute non-existence. The question, why is there something rather than nothing, posed by Leibniz encapsulates this deep philosophical unease. If there was truly absolute nothingness before the Big Bang, then what caused the Big Bang to happen? What could have prompted existence itself? If there was no time for a cause to precede its effect, what could the cause be if there was no space for it to exist? In these questions highlight the limits of applying our everyday notions of causality, which operate within a temporal framework, to the origin of that framework itself. Some philosophical arguments suggest that if time had a beginning, then the concept of before is meaningless, because it implies a prior state within a temporal sequence. If time itself did not exist, then there could be no prior state. This perspective suggests that the Big Bang is not an event in time, but rather the beginning of time. Therefore, asking what happened before the Big Bang is akin to asking what is outside the universe an illegitimate question, if the universe is defined as all of space-time. This argument shifts the focus from a temporal sequence to a question of fundamental existence and the nature of being. However, many scientists and philosophers find the idea of an absolute beginning of time and space uncomfortable. They explore various theoretical models that attempt to address the singularity and perhaps push the beginning to a different conceptual realm, or even eliminate it entirely. These models often rely on the principles of quantum mechanics, which governs the universe at its smallest scales and extreme energies. Our current understanding of general relativity is a classical theory of gravity, and it does not fully account for quantum effects at the singularity. A complete theory of quantum gravity is necessary to describe the very earliest moments of the universe. One approach is to consider time as an emergent property rather than a fundamental one. In some theoretical frameworks, time as we perceive it might not exist at the most fundamental level of reality, but instead emerges from a more primitive state. For instance, in certain quantum gravity models, space-time itself might be discretized, meaning it is not continuous, but made of tiny fundamental units. In such a scenario, the smooth flow of time might only become apparent at scales much larger than these fundamental units. At the Planck scale, the earliest conceivable moment time might be so different that our familiar notions of before and after simply do not apply. It could be that time as we know it crystallized or condensed out of a pre-geometric quantum foam, a state where space and time are not yet distinct. Several prominent theories of quantum gravity offer different perspectives on the Big Bang singularity and what might have preceded it. Loop quantum gravity, or LQG, is one such candidate theory. In LQG, space-time is not continuous, but is quantized into tiny discrete loops. This theory attempts to resolve the Big Bang singularity by suggesting that it is not a point of infinite density, but rather a quantum bounce. In this scenario, instead of collapsing to an infinitely dense point, the universe reached a minimum but finite size before rebounding into expansion. This implies that our universe could be the result of the collapse of a previous universe or a previous cosmological phase. If a quantum bounce occurred, then before our Big Bang would refer to the contracting phase of a prior universe. This removes the need for an absolute beginning for existence itself, although it shifts the question to what caused the first bounce or if there is an infinite series of bounces. String theory, another leading candidate for a theory of everything, also offers intriguing possibilities. String theory posits that fundamental particles are not point-like, but rather tiny vibrating strings. It also introduces the concept of extra spatial dimensions that might be curled up and hidden from our perception. In some string theory, inspired cosmological models, particularly those involving brains, our four-dimensional universe could be a brain or a membrane existing within a higher dimensional space called the bulk. The Big Bang in such models could be the result of a collision between two or more such brains. In a brain collision scenario, before, the Big Bang would mean the state of these brains and the bulk space they inhabit before their collision. This implies a pre-existing reality, albeit one that is fundamentally different from our current universe. The collision itself would have released the enormous energy that created the matter energy and space-time we observe. The no-boundary proposal put forward by Stephen Hawking and James Hartle offers another fascinating way to think about the universe's origin. This proposal suggests that if we consider time as a complex number with both a real and an imaginary component, then at the beginning of the universe time behaved like space. In this imaginary time, the universe has no boundary, no beginning point in the conventional sense. It would be like the surface of a sphere which has no beginning or end but is finite. If one could trace the universe's history back using imaginary time, they would not encounter a singularity or a sharp beginning point. While complex and mathematically abstract, this proposal suggests that the question, what was before the Big Bang, is akin to asking, what is north of the North Pole? It is a question that simply does not apply in that specific mathematical framework. In essence, it implies that the universe spontaneously came into existence without needing a before or a cause in the traditional sense because it had no initial boundary. Cyclic universe models also attempt to address the before Big Bang question by proposing an eternal cycle of expansion and contraction or bounces. In these models, the Big Bang is not the ultimate beginning, but simply a transition point in an ongoing cosmic cycle. Our universe might expand for billions of years, eventually contracting back into a big crunch, or perhaps avoiding a singularity through a big bounce, only to re-expand into a new Big Bang. In such scenarios, before, our Big Bang simply refers to the contracting or previous phase of the cosmos. Examples include the oscillating universe model where gravity eventually pulls everything back together, and the ekpyrotic cyclic model where the collision of branes repeatedly triggers new Big Bangs. These models resolve the before question by suggesting that something always existed in some form, albeit a constantly changing one. The idea of a multiverse also impacts the concept of before time. If our universe is just one of an infinite number of universes, each potentially with its own Big Bang, then before our Big Bang could refer to the metaspace or underlying framework from which these multiple universes originated. For instance, in eternal inflation theory, inflation never truly ends in all regions of space, instead continuously creating new pocket universes. In this view, our Big Bang is just one bubble universe inflating out of an ever-inflating background space. In such a scenario, the question of before our Big Bang expands to the question of what existed before the meta-universe itself. This pushes the problem to a higher level but does not eliminate it. These various theoretical models, from quantum gravity to multiverse scenarios, all try to address the fundamental problem posed by the Big Bang singularity. They attempt to describe a state from which our universe emerged without necessarily invoking a conventional before. Some suggest that time itself is an emergent property only becoming meaningful after a certain point in cosmic evolution. Others propose that what we perceive as the Big Bang is merely a phase transition or a bounce from a pre-existing state, whether it be a previous universe, higher dimensions, or a quantum foam. The core challenge is that our human experience of time is inherently linear and unidirectional, making it incredibly difficult to conceptualize a reality where time itself has a beginning or where our conventional notions of past, present, and future simply do not apply. The absence of a definitive answer to what was before the Big Bang is a testament to the limits of our current scientific knowledge and the profound nature of reality itself. It forces us to confront the boundaries of our understanding and the limitations of our language and concepts when applied to the very origin of existence. While scientific progress continues to push back the frontiers of our knowledge, the ultimate question of why there is something rather than nothing, and what truly lies beyond or before our cosmos may remain a profound mystery, bridging the realms of science, philosophy, and pure speculation. The conceptual groundwork provided by general relativity and the concept of space-time is essential for even formulating these questions in a coherent manner, as it tells us that time itself is part of the reality that had a beginning. Therefore, the before becomes a deeply nuanced and challenging concept rather than a simple temporal predecessor. The world we experience every day operates according to rules that seem entirely logical and intuitive. Objects have definite positions and speeds. Events unfold in a predictable sequence of cause and effect. This classical view of reality, enshrined by Isaac Newton's laws of motion and gravity, served as the bedrock of scientific understanding for centuries. However, as the 20th century dawned, scientists began to probe the universe at its most fundamental scales exploring the behaviour of atoms and their constituents. What they discovered was profoundly unsettling and utterly counterintuitive. The laws governing the very small, the realm of particles and waves, were radically different from the classical rules of the macroscopic world. This new understanding became known as quantum mechanics, a theory that revolutionized physics and forced us to rethink the very nature of reality. Its principles are essential for understanding the extreme conditions of the very early universe and form the basis of quantum cosmology. The genesis of quantum mechanics can be traced to several perplexing phenomena that classical physics simply could not explain. One such puzzle was black body radiation, the way objects emit light when heated. Classical theory predicted that a hot object should emit an infinite amount of ultraviolet light, a phenomenon dubbed the ultraviolet catastrophe, which was clearly not observed in reality. In 1900, Max Planck provided a revolutionary solution. He proposed that energy is not continuous, but is emitted and absorbed in discrete packets or bundles, which he called quanta. The energy of each quantum was directly proportional to the frequency of the radiation, with the proportionality constant now known as Planck's constant, a fundamental value in quantum mechanics. This groundbreaking idea marked the birth of quantum theory, although Planck himself initially viewed it more as a mathematical trick than a fundamental aspect of reality. Another mystery was the photoelectric effect, where light shining on a metal surface can eject electrons. Classical wave theory of light predicted that the energy of the emitted electrons should depend on the intensity of the light, and that any frequency of light could eventually eject electrons if the intensity was high enough. However, experiments showed that electron ejection only occurred if the light's frequency exceeded a certain threshold, regardless of its intensity, and that the energy of the emitted electrons depended on the light's frequency, not its intensity. In 1905, Albert Einstein, building on Planck's idea, proposed that light itself consists of discrete packets of energy, called photons. Each photon has an energy proportional to its frequency. For an electron to be ejected, it must absorb a single photon, with enough energy to overcome the binding forces in the metal. If the photon's energy is below the threshold, nothing happens no matter how many photons hit the surface. This concept of light behaving as particles further solidified the idea of quantization. Perhaps the most famous and unsettling feature of quantum mechanics is wave-particle duality. This concept states that entities like electrons, protons, and even light itself do not behave exclusively as either particles or waves, but can exhibit characteristics of both, depending on how they are observed or interacted with. Light, traditionally considered a wave phenomenon, was shown by Einstein's work on the photoelectric effect to behave like particles' photons. Conversely, particles like electrons, which were classically thought of as tiny billiard balls, were shown by experiments like the double-slit experiment to exhibit wave-like behaviour. The double-slit experiment is a powerful demonstration of wave-particle duality. If you fire electrons one by one at a barrier with two narrow slits behind it, and then observe where they land on a screen, you would expect to see two distinct bands corresponding to electrons passing through one slit or the other, like tiny bullets. However, what is observed is an interference pattern, a series of alternating bright and dark bands characteristic of waves interfering with each other. This suggests that each individual electron somehow passes through both slits, simultaneously behaving like a wave. But if you then try to detect which slit the electron goes through, the interference pattern disappears and you get two distinct bands. The act of observation seems to force the electron to choose a definite path, confirming its particle nature. This profound result highlights that the quantum world is fundamentally different from our macroscopic experience, where objects always have a definite location and follow a definite path. A cornerstone of quantum mechanics is the concept of superposition. This principle states that a quantum system, such as an electron or an atom, can exist in multiple possible states simultaneously until it is measured or observed. It is as if the particle exists in all its potential states at once, a probabilistic cloud of possibilities, rather than a single definite state. Only upon measurement does the system collapse into one particular definite state. The famous thought experiment of Schrödinger's cat illustrates this idea. Imagine a cat in a sealed box with a vial of poison connected to a device that will release the poison if a single radioactive atom decays. According to quantum mechanics, until the box is opened and the atom's state is observed, the atom exists in a superposition of decayed and undecayed states. This implies that the cat itself is in a superposition of being both alive and dead simultaneously, until the act of observation forces it into one definite state. While this is a thought experiment designed to highlight the strangeness of quantum mechanics, it vividly illustrates the counterintuitive nature of superposition. Related to superposition is the probabilistic nature of quantum mechanics. Unlike classical physics, where if you know the initial conditions of a system you can predict its future state, with certainty, quantum mechanics only allows us to predict the probabilities of various outcomes. We cannot say for sure where a particular electron will be at a given time or which energy state an atom will occupy. Instead, we can calculate the probability of finding it at a certain location or in a particular state. This inherent randomness is not due to our lack of knowledge or limitations in our measuring instruments. It is a fundamental and irreducible aspect of quantum reality. The mathematical framework of quantum mechanics uses wave functions to describe the state of a particle or system. The square of the amplitude of the wave function at any point gives the probability of finding the particle at that point. This probabilistic interpretation, known as the Born rule, is central to making predictions in quantum mechanics. Perhaps the most famous principle that sets quantum mechanics apart from classical physics is Werner Heisenberg's uncertainty principle, formulated in 1927. This principle states that it is impossible to simultaneously know with perfect precision certain pairs of complementary properties of a particle. The most common example is position and momentum. If you precisely measure the position of a particle, you necessarily introduce uncertainty into its momentum and vice versa. Similarly, there is an uncertainty relationship between energy and time. The more precisely you measure the energy of a system, the less precisely you can know the time for which it had that energy and vice versa. This is not a limitation of our measuring devices, but a fundamental property of nature itself. It implies that at the quantum level, reality is inherently fuzzy and indeterminate. We cannot simultaneously pinpoint every property of a particle as we might a classical object. The act of measurement in quantum mechanics is a complex and still debated topic, known as the measurement problem. When a quantum system in a superposition of states is measured, it appears to instantaneously collapse into one of those definite states. What precisely constitutes a measurement, and how this collapse occurs, is a deep conceptual challenge. Does consciousness play a role? Does interaction with a classical measuring apparatus cause the collapse? Various interpretations of quantum mechanics, such as the Copenhagen interpretation, the many worlds interpretation and others, offer different ways to understand this phenomenon, but none have achieved universal consensus. Regardless of the interpretation, the practical consequence is that the outcome of a quantum measurement is inherently probabilistic. Quantum mechanics also introduced the concept of quantum entanglement. When two or more particles become entangled, their fates are linked in such a way that they share a single quantum state. Measuring a property of one entangled particle instantaneously determines the corresponding property of the other particle, no matter how far apart they are. This seems to violate the classical notion that information cannot travel faster than light, but it does not allow for faster than light communication. Entanglement highlights the non-local nature of quantum reality, where particles can be intimately connected across vast distances. The principles of quantum mechanics extend beyond individual particles to quantum fields. In modern quantum field theory, every fundamental particle is understood as an excitation or a vibration of an underlying quantum field that permeates all of space. For example, there is an electron field, a photon field, a quark field, and so on. Particles are not distinct little balls, but rather localized excitations of these fields. The quantum vacuum, the lowest energy state of these fields, is not empty, but is filled with the potential for particles to emerge from it. This concept of quantum fields is crucial for understanding phenomena like vacuum fluctuations. The implications of quantum mechanics are profound for our understanding of the universe, especially its earliest moments. Classical physics and Einstein's general relativity, which describes gravity at large scales, predict a singularity at the beginning of the Big Bang, a point of infinite density and temperature where space-time breaks down. However, at such extreme conditions where matter and energy are compressed to unimaginably small scales, quantum effects would dominate. General relativity, a classical theory is simply inadequate to describe the universe at the Planck epoch, the first 10 to the power of minus 43 seconds. A theory of quantum gravity which would unify general relativity with quantum mechanics is needed to fully understand what happened at or before the Big Bang singularity. Concepts like superposition uncertainty in quantum fields are fundamental to quantum cosmology, which attempts to apply quantum mechanics to the entire universe. For instance, theories about the universe spontaneously appearing from a quantum vacuum, or the idea of the universe existing in a superposition of different possible states before measurements of the cosmic microwave background narrowed down its properties, all rely heavily on quantum principles. The inherent probabilistic nature of quantum mechanics also suggests that the initial conditions of the universe might not have been uniquely determined, but rather emerged from a range of possibilities. Understanding this quantum reality with its wave-particle duality, superposition, uncertainty and probabilistic outcomes is therefore an essential prerequisite for exploring the most speculative and fundamental questions about the universe's origin and its earliest evolution. It opens up a universe that is far stranger, more dynamic and less deterministic than our everyday experience suggests. When we think of empty space, we often imagine a void where nothing exists, a vast expanse devoid of matter, energy or even light. In classical physics, a vacuum is precisely that, the absence of all particles and fields. However, the profound insights of quantum mechanics paint a radically different picture of emptiness. In the quantum realm, a vacuum is far from inert and lifeless. Instead, it is a vibrant, bubbling sea of activity teeming with what are known as vacuum fluctuations, where particles momentarily pop into and out of existence. This concept of the quantum vacuum being a dynamic entity, rather than absolute nothingness, has profound implications for our understanding of reality, and particularly for speculative theories about the universe's origin. The fundamental reason for this ceaseless activity in the quantum vacuum lies in Werner Heisenberg's uncertainty principle, specifically the energy-time uncertainty relation. This principle states that you cannot simultaneously know with perfect precision both the energy of a system and the time for which it possessed that energy. There is an inherent fuzziness in nature that prevents such absolute certainty. This means that for very short periods of time there can be a temporary violation of energy conservation. Energy can be borrowed from the vacuum for a brief moment as long as it is paid back within a time frame allowed by the uncertainty principle. The more energy borrowed, the shorter the time it can exist. This is the mechanism that allows for the spontaneous appearance and disappearance of virtual particles from the vacuum. These ephemeral particles that wink into and out of existence are called virtual particles. They are not real in the sense of stable, propagating particles that can be directly observed or detected over long periods. Instead, they are transient excitations of quantum fields. According to quantum field theory, every fundamental particle in the universe, electrons, quarks, photons, is an excitation or a ripple in an underlying quantum field that permeates all of space. The vacuum state is simply the lowest energy state of all these quantum fields, a state where there are no observable stable particles. However, even in this lowest energy state, the fields themselves are always fluctuating. These fluctuations are the virtual particles. Virtual particles almost always appear in particle-antiparticle pairs. For instance, an electron and its antiparticle, a positron, might spontaneously emerge from the vacuum, exist for an incredibly short time, and then annihilate each other, converting their combined mass back into energy or photons. Similarly, quark-antiquark pairs or virtual photons can emerge. These interactions are so rapid that they cannot be directly observed, but their effects are measurable and have been experimentally verified. One of the most striking pieces of experimental evidence for the reality of vacuum fluctuations is the Casimir effect. In 1948, Dutch physicist Hendrik Casimir predicted that if two uncharged parallel metallic plates are placed extremely close together in a vacuum, they will experience a tiny but measurable attractive force pulling them towards each other. This counterintuitive force arises because the space between the plates restricts the possible wavelengths of virtual photons that can exist there. Only virtual photons with wavelengths that fit neatly between the plates can exist in the gap. Outside the plates, however, There are no such restrictions, so a wider range of virtual photon wavelengths is possible. This difference in the allowed quantum fluctuations creates a net force. The pressure exerted by the virtual photons outside the plates is greater than the pressure exerted by the virtual photons inside the plates, resulting in an attractive force pushing the plates together. The Casimir effect has been precisely measured in laboratory experiments, providing compelling evidence for the physical reality of vacuum fluctuations and the inherent energy of the quantum vacuum. Another crucial piece of evidence comes from the Lamb shift observed in the hydrogen atom. In classical electrodynamics and even early quantum models, the 2s and 2p energy levels of the hydrogen atom were predicted to have exactly the same energy. However, in 1947, Willis Lamb and Robert Rutherford discovered a tiny but definite shift in the energy of the 2s level relative to the 2p level. This small energy difference could not be explained by existing theories. It was later explained by quantum electrodynamics QED, which showed that the electron in the hydrogen atom constantly interacts with virtual photons that pop into and out of existence in the surrounding quantum vacuum. These interactions slightly shift the electron's energy levels, causing the Lamb shift. This phenomenon provides direct evidence that the quantum vacuum is not empty, but is filled with a dynamic sea of virtual particles constantly interacting with real particles. Spontaneous emission is yet another phenomenon explained by vacuum fluctuations. If an atom is in an excited energy state, classical physics predicts that it should remain in that state indefinitely, unless it is perturbed by an external electromagnetic field. However, atoms in excited states spontaneously emit photons and decay to lower energy states, even in what appears to be empty space. This process is initiated by the interaction of the atom's electrons with the fluctuating electromagnetic field of the quantum vacuum. The virtual photons in the vacuum stimulate the excited electron to drop to a lower energy level, releasing a real photon. This constant interaction with the quantum vacuum prevents atoms from remaining in excited states forever, and explains the natural decay of excited atoms. The concept of the quantum vacuum being filled with activity fundamentally changes our understanding of nothing. In classical terms, nothing means absolute emptiness. In quantum terms, empty space is never truly empty. It is the lowest possible energy state of the universe, but it is inherently dynamic and contains latent energy and potential. This lowest energy state is often referred to as the 0-point energy, because it represents the minimum energy present even at absolute zero temperature when all classical motion ceases. The existence of this 0-point energy implies that even in the absence of observable matter or radiation, the quantum vacuum possesses an intrinsic energy density. This concept has profound implications for cosmology, particularly in the context of the universe's origin. The idea that the universe could have emerged from nothing is recontextualized by the quantum vacuum. If nothing is interpreted as the quantum vacuum rather than an absolute philosophical void, then the universe is not necessarily created from absolute non-existence. Instead, it could have emerged from a highly energetic and dynamic quantum state that has inherent properties and the potential for existence. This is a crucial distinction. The universe originating from a quantum vacuum is not the same as it originating from a state of literally no being whatsoever. The quantum vacuum is not nothing, but a fundamental something that is constantly bubbling with virtual particles and fluctuations. This understanding is central to some speculative theories about the universe's origin. One such idea is that the Big Bang itself could have been a gigantic quantum fluctuation in a pre-existing quantum vacuum. In this scenario, a tiny quantum fluctuation in the vacuum could have grown unstable and expanded rapidly due to a process like inflation giving rise to the entire universe we observe. This doesn't mean the universe appeared from absolute void, but from a pre-existing quantum substratum or a meta-vacuum, which itself is far from empty. Such a quantum fluctuation would not violate energy conservation in the long term, because the total energy of the universe is thought to be zero, or very close to zero, with the positive energy of matter and radiation being balanced by the negative gravitational potential energy. Furthermore, quantum fluctuations are believed to have played a crucial role in providing the initial seeds for structure formation in the universe. The theory of cosmic inflation proposes a period of extremely rapid expansion in the very early universe. During this inflationary epoch, tiny quantum fluctuations that existed at subatomic scales were stretched to macroscopic cosmological scales. These stretched quantum fluctuations became the primordial density variations, or inhomogeneities, in the early universe, which are observed as the faint temperature anisotropies in the cosmic microwave background radiation. These tiny overdense and underdense regions then grew through gravity over billions of years, forming the large-scale structures like galaxies and galaxy clusters we see today. So the very fabric of the cosmic web, the distribution of matter in the universe, originated from the fundamental fuzziness and activity of the quantum vacuum during inflation. The concept of a false vacuum is also relevant in this context. In some inflationary models, the early universe is thought to have existed in a false vacuum state. This false vacuum is a quantum state that is not the lowest possible energy state, but is stable for a period. It possesses a very high energy density similar to a cosmological constant. When this false vacuum eventually became unstable, it decayed or tunneled to a lower energy state, a true vacuum, releasing its enormous energy and triggering the Big Bang expansion and the creation of matter and radiation. In this view, the universe did not appear from absolute nothingness, but from the decay of a high-energy quantum vacuum state that existed prior to the hot Big Bang. The Hawking-Hartle no-boundary proposal also touches upon the quantum nature of the universe's origin. While highly mathematical, this proposal suggests that the universe did not have a definite beginning in the traditional sense, but rather spontaneously arose from a quantum state without a boundary or a singularity. It is a quantum mechanical description of the universe's origin, where the very concept of space-time emerges from a quantum foam without needing an initial temporal before. This implies a universe that essentially creates itself from quantum laws without external intervention or a pre-existing time. The implications of vacuum fluctuations and the quantum nature of the vacuum are profound for cosmology. They suggest that the nothing before the Big Bang was not an absolute void, but a highly energetic and dynamic quantum state with inherent properties and the potential for existence. This shifts the fundamental question from how did something come from literally nothing to how did our specific universe emerge from the complexities of the quantum vacuum. It implies that the universe's origin might be governed by the same quantum laws that dictate the behavior of particles at the subatomic level, continuously pushing the boundaries of our understanding of existence itself. The quantum vacuum, far from being empty, is a vibrant foundation for reality. Modern physics rests on two towering pillars of understanding, each remarkably successful in its own domain but fundamentally incompatible with each other. On one side stands Albert Einstein's general theory of relativity, which describes gravity as the curvature of space-time and governs the universe on large cosmological scales, from stars and galaxies to the very expansion of the cosmos. On the other side is quantum mechanics, the theory that describes the behavior of matter and energy at the smallest subatomic scales, dictating the world of particles and forces like electromagnetism and the nuclear forces. Both theories have been extensively verified by countless experiments and observations, but they employ entirely different conceptual frameworks and mathematical languages. The quest for quantum gravity is the ambitious endeavour to reconcile these two fundamental theories into a single coherent framework, a theory that can describe the entire universe from its largest structures to its smallest constituents and unravel the mysteries of its ultimate origin. General relativity, which Einstein published in 1915, revolutionized our understanding of gravity. It abandoned the Newtonian idea of gravity as an instantaneous force acting between masses and replaced it with a geometric description. In general relativity, mass and energy warp the fabric of space-time, and what we perceive as gravity is simply objects following the shortest paths in this curved space-time. The theory has been spectacularly successful in explaining a wide range of phenomena. It accurately predicts the precise orbits of planets, including the subtle precession of Mercury's orbit, which Newtonian gravity could not fully account for. It predicted the bending of light by massive objects, a phenomenon famously confirmed during a solar eclipse. General relativity also predicted the existence of black holes regions of space-time, where gravity is so strong that nothing, not even light, can escape. Its most recent triumph was the direct detection of gravitational waves ripples in space-time itself, caused by catastrophic cosmic events like the collision of black holes a century after Einstein first predicted them. General relativity is a classical theory, meaning it describes phenomena in a continuous deterministic way, without involving the probabilistic and quantized nature of the quantum world. Its domain is the macroscopic universe, where gravity is the dominant force. In stark contrast, quantum mechanics, which developed concurrently with general relativity in the early 20th century, focuses on the microscopic world of atoms and subatomic particles. It introduced revolutionary and often counterintuitive concepts such as wave-particle duality, where particles can behave like waves, and vice versa, superposition, where a particle can exist in multiple states simultaneously until measured, and the uncertainty principle, which states that certain pairs of properties like position and momentum cannot be known with perfect precision at the same time. Quantum mechanics is fundamentally probabilistic. It predicts the likelihood of certain outcomes rather than definite results. This theory has been incredibly successful in explaining the behavior of atoms, the emission of light, the structure of materials, and the interactions of elementary particles. The standard model of particle physics, which describes the electromagnetic weak and strong nuclear forces and all known elementary particles except for the graviton, is a highly successful quantum field theory built upon the principles of quantum mechanics. Its predictions have been confirmed with astonishing precision in particle accelerators around the world. The fundamental incompatibility between general relativity and quantum mechanics arises from their differing descriptions of reality. General relativity treats space-time as a smooth, continuous and flexible fabric that can be curved and warped by mass and energy. Quantum mechanics, on the other hand, describes energy and matter in discrete quantized packets. When physicists attempt to apply the quantization procedures of quantum mechanics to the gravitational field, which is what general relativity describes, they run into insurmountable mathematical difficulties leading to infinities that cannot be removed in a consistent way. The gravitational force is incredibly weak at the scales where quantum effects become dominant, far weaker than the electromagnetic or nuclear forces. This weakness makes it extremely difficult to observe quantum gravitational effects directly. While photons mediate the electromagnetic force, and gluons mediate the strong force, the hypothetical particle that would mediate the gravitational force is called the graviton. However, a quantum theory of gravity that successfully incorporates gravitons and their interactions with other particles remains elusive. The quest for quantum gravity is not merely an academic exercise. It is absolutely necessary to resolve some of the most profound outstanding mysteries in physics and cosmology. One of the most compelling reasons is the Big Bang singularity. General relativity predicts that the universe began from a point of infinite density and temperature, where space-time curvature becomes infinite. At this singularity, the equations of general relativity break down completely, and our current laws of physics cease to apply. They cannot describe what happened at the Big Bang, or what, if anything, existed before it. A theory of quantum gravity is essential to understand this initial moment, perhaps resolving the singularity and providing a coherent description of the very early universe where all matter and energy were compressed into an unimaginably tiny volume, and quantum effects of gravity would have been dominant. Such a theory might reveal that the Big Bang was not an absolute beginning, but a transition from a prior state, perhaps a quantum bounce from a contracting universe, or an emergence from a state where space and time as we know them did not yet exist. Similarly, quantum gravity is needed to understand the singularities predicted inside black holes. General relativity predicts that at the heart of a black hole, matter collapses to an infinitely dense point, a singularity where again its equations fail. A theory of quantum gravity is required to describe the physics inside black holes at these extreme conditions, and to address fundamental puzzles like the black hole information paradox, which questions whether information about matter falling into a black hole is permanently lost, or if it is somehow preserved. A quantum theory of gravity might reveal that black hole singularities are also resolved, perhaps replaced by a finite dense region, or a wormhole connecting to another part of space-time. Beyond these singularities, the quest for quantum gravity is driven by the grand vision of unifying all fundamental forces of nature. The standard model of particle physics successfully describes the strong, weak and electromagnetic forces, but it excludes gravity. Physicists dream of a theory of everything, a single elegant framework that can describe all forces and particles in the universe as different manifestations of a single underlying reality. Such a theory would provide a deeper and more complete understanding of how the universe works, and might also offer explanations for the precise values of fundamental physical constants, which currently appear arbitrary. It would be the ultimate intellectual triumph, unifying all of physics under one coherent roof. Another fundamental reason for quantum gravity lies in the very nature of space-time itself. If energy and matter are quantized as quantum mechanics tells us, then it seems logical that the fabric of space-time, which is warped by energy and matter, should also exhibit quantum properties. At incredibly small scales, known as the Planck scale, space-time might not be smooth and continuous as in general relativity, but rather lumpy, foamy or granular. It might consist of discrete units or quanta of space and time themselves. The Planck length, approximately 10 to the power of minus 35 meters, is the scale at which quantum gravitational effects are expected to become significant. Below this scale, our familiar notions of continuous space and time may break down entirely. A theory of quantum gravity would provide insights into the microstructure of space-time at these extreme scales. Developing a theory of quantum gravity is arguably the biggest challenge in modern theoretical physics. One of the primary difficulties is the complete lack of experimental data from the quantum gravity regime. The Planck scale is unimaginably small, and the energies required to probe such scales are astronomically high, far beyond the capabilities of any conceivable particle accelerator on Earth. This means that physicists do not have empirical guideposts to test and refine their theoretical models directly. They must rely heavily on mathematical consistency, logical coherence, and the ability of a theory to unify existing knowledge and make predictions that might one day be testable, even if indirectly. The extreme mathematical complexity involved in trying to combine the intricacies of general relativity with the probabilistic nature of quantum mechanics also poses a formidable barrier. Despite these immense challenges, several ambitious theoretical approaches are being pursued to formulate a theory of quantum gravity. The two most prominent contenders are string theory and loop quantum gravity, which will be discussed in more detail in subsequent sections. Other approaches include causal dynamical triangulations, which build space-time from fundamental geometric building blocks, non-commutative geometry, which explores the idea that space-time might not be described by ordinary coordinates, and various types of quantum cosmology models that apply quantum principles directly to the entire universe. Each approach has its own strengths, weaknesses, and unique conceptual framework for thinking about the fundamental nature of reality. The search for quantum gravity is not just about combining two theories, it is about pushing the boundaries of human understanding into realms where our everyday intuition about space-time and causality breaks down. It is a quest for the ultimate laws that govern the universe's origin and its most fundamental structure, a pursuit driven by the enduring human desire to understand the entirety of existence. Among the leading contenders in the quest for a theory of quantum gravity loop, quantum gravity, or LQG, stands out as a distinct and compelling approach, while other theories like string theory aim to unify all fundamental forces including gravity by proposing a new fundamental constituent of matter and energy. LQG focuses specifically on quantizing spacetime itself. Its core philosophy is to apply the principles of quantum mechanics directly to Einstein's general theory of relativity in a rigorous and non-perturbative way, leading to a granular or atomic picture of space and time at the smallest scales. It offers a powerful framework for addressing the Big Bang singularity and the nature of space and time at the universe's origin. The foundational principles of loop quantum gravity begin with a reformulation of general relativity. Instead of working directly with space-time as a smooth, continuous manifold, LQG re-expresses Einstein's equations using a mathematical language that is more amenable to quantum treatment. This involves transforming the gravitational field into a set of variables known as Ashtekar variables, which resemble the electric and magnetic fields used in electromagnetism. This reformulation allows the gravitational field to be treated in a way that is more analogous to how other forces are handled in quantum field theory, making it easier to apply standard quantization procedures. A key aspect of this approach is its background independence. Unlike some other quantum gravity theories, LQG does not assume the existence of a fixed pre-existing spacetime background. Instead, spacetime itself emerges as a dynamic and quantum entity, consistent with the spirit of general relativity, where spacetime is not merely a stage, but an active participant shaped by matter and energy. One of the most profound and central predictions of loop quantum gravity is the quantization of space itself. In classical physics, space is assumed to be infinitely divisible. You can always imagine dividing a length into smaller and smaller parts without limit. However, in LQG, this is not the case. The theory predicts that space is not continuous, but rather composed of tiny, discrete, irreducible units, or atoms of space. These fundamental units are extremely small, on the order of the Planck length approximately 10 to the power of minus 35 meters, below which space cannot be further subdivided. This means that area and volume also come in discrete quantized packets. There is a minimum possible area and a minimum possible volume that can exist in the universe. It is akin to pixels on a digital image, or atoms making up a substance. From this perspective, space is not a smooth backdrop but a network of interconnected quantum excitations. The mathematical structures that represent these quantized units of space in LQG are called spin networks. A spin network is a graph-like structure where the lines represent fundamental loops, or edges, of excited gravitational field, and the nodes where these lines meet represent fundamental units of volume. Each edge and node carries a quantum number, a spin quantum number, that specifies the quantized area and volume respectively. These spin networks evolve over time to form structures called spin foams, which represent the quantized fabric of spacetime evolving from one moment to the next. The geometry of spacetime at the Planck scale is described not by a smooth manifold, but by these discrete quantum graphs. The resolution of the Big Bang singularity is one of the most significant triumphs claimed by loop quantum gravity. In general relativity, the Big Bang is predicted to be a point of infinite density and infinite spacetime curvature, where our current laws of physics break down. LQG, however, provides a mechanism to avoid this singularity. According to LQG, as the universe contracts and its density increases, the quantum nature of spacetime becomes dominant. Instead of collapsing to an infinitely dense point, the universe reaches a state of maximum but finite density and curvature. At this point, the repulsive effects of quantum gravity become so strong that they overcome the attractive force of classical gravity, causing the universe to bounce and re-expand. This is known as the quantum bounce, or big bounce, rather than a big bang from nothing. This quantum bounce implies that our universe did not necessarily originate from an absolute beginning of nothingness, but could have emerged from the collapse of a previous universe or a prior cosmological phase. In this view, the universe has undergone an eternal cycle of contraction and expansion, with a bounce replacing the singularity. This scenario provides a continuous cosmological evolution, avoiding the conceptual difficulties of a true beginning of time and existence from an infinitely dense point. The quantum bounce mechanism also offers a potential solution to the information paradox in black holes, suggesting that the singularity inside a black hole is also resolved with matter either rebounding or passing through to another region of space-time rather than being lost forever. The nature of time itself is also profoundly reinterpreted in loop quantum gravity. In LQG, time is not an external parameter or a universal clock that ticks independently of the universe. Instead, time is seen as an emergent property arising from the dynamics of the spin network. It is defined by the changes and evolutions within the fundamental quantum geometric structures. This approach helps to address the problem of time in quantum gravity, which arises when attempting to quantize a theory like general relativity, where time is treated as a coordinate that can be dynamically warped. In LQG, time becomes relational, meaning it is defined by the relationships between the various components of the universe, rather than being an absolute background against which events unfold. This concept implies that at the very fundamental scales of space-time where the quantum bounce occurs, the familiar notion of a smoothly flowing continuous time may not apply. A significant challenge and also a defining characteristic of loop quantum gravity is its relationship with other fundamental forces and the standard model of particle physics. LQG is primarily a theory of quantum gravity. It aims to quantize space-time and gravity directly, but it does not inherently include the other fundamental forces like electromagnetism, or the strong and weak nuclear forces, or the particles described by the Standard Model. This means that LQG is not a theory of everything, in the same sense that string theory often claims to be. While efforts are underway to incorporate matter and gauge fields into the LQG framework, this remains a complex and ongoing area of research. The hope is that a unified picture would eventually emerge, perhaps with the other forces and particles being built upon the quantum geometric structure provided by LQG. The mathematical framework of loop quantum gravity is highly sophisticated, involving concepts from differential geometry and quantum field theory. It utilizes a canonical quantization approach where the gravitational field is broken down into its fundamental components and then quantized. Key mathematical objects in LQG include holonomies, which measure the curvature of spacetime along loops, and fluxes, which measure the area of surfaces. These mathematical constructs are what ultimately give rise to the discrete nature of space and the spin network formalism. Loop quantum gravity boasts several strengths. Its background independence is a major advantage, aligning with the spirit of general relativity. It is a non-perturbative theory, meaning it does not rely on approximations that break down at high energies, unlike earlier attempts to quantize gravity. Most importantly, it offers a concrete mechanism to resolve the Big Bang and black hole singularities, replacing them with finite curvature events like the quantum bounce. It also makes specific predictions such as the quantization of area and volume, which are testable in principle even if currently beyond our technological reach. However, LQG also faces significant challenges. The most critical challenge is the lack of experimental verification. The predictions of LQG, such as the discrete nature of space and time, occur at the Planck scale energies far beyond our current experimental capabilities. Indirect tests are being explored, for instance, searching for tiny deviations from light speed or effects on cosmic ray propagation that might be caused by a granular spacetime, but definitive evidence remains elusive. Another conceptual challenge is the recovery of classical general relativity at macroscopic scales. While LQG aims to be a full quantum theory of gravity, demonstrating how it smoothly transitions to the familiar continuous spacetime of Einstein's theory, at large scales is a complex task. The incorporation of matter and other forces, as mentioned, remains an ongoing area of research. Despite these challenges, loop quantum gravity remains a powerful and intriguing candidate for a theory of quantum gravity, providing a unique perspective on the fundamental nature of spacetime and the origin of our universe. In 1981, astronomers spotted something they couldn't explain. While mapping the universe, they stumbled upon a massive patch of almost nothing. No bright galaxies, no star-filled clusters, just darkness. They had discovered the Boots Void, an unimaginably vast region nearly 300 million light-years wide, and yet almost completely empty. Ever since, it's been one of the strangest mysteries in the cosmos. What could create such a gaping hole in the universe, and what does it mean for everything we think we know about space? Before we start today's journey, let us know where in the world you're watching from, and what time it is for you right now. Post it in the comments below and settle in for a cosmic ride to discover the biggest void in the universe. When most people think of the universe, they tend to picture something dazzling and crowded with stars, an enormous glowing sky filled with swirling galaxies, shining suns, and bright clouds of colourful gas and dust. Our own galaxy, the Milky Way, seems full of life and light, bursting with stars and planets. And beyond it, we imagine countless other galaxies, some spinning like giant pinwheels, others soft and oval-shaped, all lighting up the darkness with the energy of their billions of stars. When we look at the night sky on a clear evening, we see just a small glimpse of this breathtaking view, a sky dotted with tiny specks of light. These stars hint at something vast, rich, and full of wonder. From the fiery birthplaces of stars to dramatic galaxy crashes that set off bursts of light, space seems to be alive with activity. And it truly is. The universe holds an unimaginable number of stars and galaxies, far more than we can count. But this picture, as beautiful as it is, only shows part of the story. There's something just as important, yet far less talked about. Most of the universe is almost completely empty. While we often imagine space packed with shining objects, The truth is that those bright galaxies and glowing stars are scattered through an immense ocean of emptiness. For every glowing cluster, there are unimaginably vast stretches of darkness. These are the quietest regions of space, where even the fastest beams of light take millions or even billions of years to cross the distances. The amount of matter in these regions is so low, it's as if you took all the sand from every beach on Earth and spread it through a space larger than the entire solar system, and still found it mostly empty. And these quiet spaces aren't small gaps here and there. They are enormous. They're known as cosmic voids, massive bubbles in the universe where galaxies are scarce, sometimes completely absent. In these places, the bright chatter of stars and galaxies fades into a deep silence. A silence not just of sound, since sound can't travel in space anyway, but of light, heat, and gravity. To really understand these voids, we have to change the way we picture the universe. Instead of seeing it as a star-filled sky, imagine something more like a sponge. The galaxies and clusters are the dense knots and threads of the sponge, where most of the matter gathers, but the rest, the hollow parts, are the voids, and they make up a huge portion of space. These aren't just empty like the space between planets in our solar system, which still contains dust, solar wind, and light. These voids are empty on a scale that's hard to imagine. If you place the entire Milky Way inside one, it would be like dropping a single grain of sand into a massive stadium. It would be barely noticeable. Its closest neighbour might be billions of light years away. Even these empty regions are not totally devoid of matter. There are still a few lone atoms, maybe a hydrogen particle drifting here or there, and the faint glow of the cosmic microwave background, a leftover whisper from the Big Bang that happened almost 14 billion years ago. But compared to the rest of the universe, these areas are incredibly barren. A man-made vacuum chamber on Earth, designed to be as empty as possible, would be considered crowded compared to the space inside a cosmic void. In the parts of space where galaxies gather, there may be hundreds or even thousands of them, packed relatively close together. These are the galaxy clusters, connected by thin filaments where galaxies stretch like beads on a string. But inside the deepest parts of the voids, you may find only a handful of galaxies, or none at all. The rare galaxies that exist there are faint, isolated wanderers drifting alone through a black sea. Light in these places is scarce. It is like trying to light up an entire city using a single candle. But the presence of these huge empty spaces is not a mistake. They are not flaws in the universe. They are part of its design. When the universe began, it wasn't perfectly smooth. There were tiny differences in the way matter and energy were spread out. Some spots were slightly denser, others slightly emptier. Over billions of years, gravity, the invisible force that pulls everything together, started working on these small differences. In places where there was a little more matter, gravity pulled in even more. These became the stars, the galaxies, the clusters we see today. In places where there was a little less matter, there was less for gravity to pull in. So those areas didn't grow. They got stretched out and emptied as matter moved toward the denser regions. The universe itself was expanding, pulling everything apart even more, and making the voids larger and emptier. This slow, powerful process, gravity pulling in, space expanding out, sculpted the universe into the sponge-like shape we see today, a network of bright, busy clusters surrounded by vast, quiet voids. So, while the stars and galaxies get most of the attention, it's the emptiness between them that shapes the universe. The silent voids may not sparkle or shine, but they are just as important in the grand design of everything we see. The next time you look up at the night sky and marvel at the stars, remember? Behind that twinkling curtain is a vast and quiet darkness, stretching farther than the mind can grasp, the true hidden architecture of the cosmos. The mystery of these vast, silent regions goes far beyond their lack of stars or galaxies. What truly fascinates scientists is what this emptiness tells us about the invisible forces shaping the universe. Why isn't the cosmos evenly filled with galaxies like a smooth soup? Why do we find giant clusters of matter in some places, while other areas are nearly deserted? The answer lies in the invisible hands of gravity, dark matter, and dark energy. Three powerful forces that guide how matter moves and clumps together across billions of light years. In these quiet voids, there's a true physical silence. There are no newborn stars bursting to life, No galaxies whirling in dramatic dances, no powerful black holes blazing with energy at the centres of galaxies. Most of the galaxies that do exist in these regions are far apart and lonely. They don't get pulled or jostled by nearby neighbours, which means they live quieter, slower lives. Without the push and pull of frequent collisions or interactions, these galaxies might evolve differently, perhaps holding onto their gas longer or forming fewer stars over time. The idea of a completely empty space, a vacuum, has fascinated people for centuries, but cosmic voids stretch this idea to an extreme. They're not just places with a little less matter, they are enormous natural gaps in the cosmic fabric, many hundreds of millions of light-years wide. They're among the most empty places in existence, and they force us to rethink what nothingness really means. They challenge our instincts about how matter should be spread out in the universe. If you were somehow transported to the heart of one of these giant voids, far from any bright galaxy or strong gravity, the view would be eerie and unforgettable. The sky would not be full of stars or streaked with the glow of the Milky Way. Instead, it might look nearly pitch black, with only a faint star here or a dim smudge of a faraway galaxy there, barely visible even through powerful telescopes. The closest bright object could be so far away that its light has travelled for hundreds of millions of years just to reach your eyes. You wouldn't be seeing a lively, glowing present. You'd be peeking into a ghostly cosmic past. That chilling visual emptiness contributes to what scientists call the cosmic silence. A quiet so complete, so absolute, it feels like it has its own presence. But this silence is not only about what you see, or don't see, it's also about gravity. Gravity does reach across all of space, but it weakens with distance. And in these voids, the nearest massive objects are so far away that their pull is barely felt. The matter that does exist in these voids is left mostly undisturbed, floating freely as the universe expands. In fact, because of the strange push of dark energy, these already empty regions are expanding even faster than the rest of space. The temperature in these cosmic cavities is just a few degrees above absolute zero. That's minus 459 degrees Fahrenheit. There are no stars nearby to warm things up, no clouds of gas to compress and heat. Only the faint glow left over from the Big Bang, the cosmic microwave background, adds a whisper of warmth. It's a place of extreme cold, darkness, and stillness, where the silence is almost frozen into space itself. Yet, despite how empty they seem, these cosmic voids are treasure troves for scientists. Because they contain so little ordinary matter, they allow researchers to study dark energy more clearly. In crowded areas of space, gravity from stars and galaxies can interfere with how dark energy acts. But in these wide, quiet voids, there is almost nothing to block or confuse the effects of dark energy. This makes them perfect places to study how this strange force might be pushing the universe apart. By examining the size, shape, and growth of voids over time, scientists hope to uncover new clues about one of the biggest mysteries in all of physics. So, even though they look like nothing, these voids are far from meaningless. Their vast stillness actually points us toward the deepest truths about the universe, how it formed, how it evolves, and what invisible forces are guiding it. These cosmic gaps are not just holes in space, they are windows into the universe's hidden design, full of silent stories and subtle clues. For thousands of years, people looked up at the night sky and saw only what their eyes could take in, tiny pinpricks of light scattered across the darkness. Our early understanding of the universe was limited to what we could see without tools, just stars shining above us. But everything began to change when the first telescopes were built. Suddenly, new worlds and fainter stars appeared. Over time, we discovered that our home, the Milky Way galaxy, was just one of many. The universe, once thought to be small and simple, kept growing larger in our minds. By the middle of the 20th century, astronomers had begun to understand just how massive the universe truly is. They believed it was filled with galaxies more or less evenly spread throughout space, like dots sprinkled across a huge sheet. It was a neat and elegant picture, one that made sense at the time. But then, something unexpected happened. A discovery came along that completely changed that picture. It showed that the universe wasn't evenly filled with galaxies after all. In fact, it revealed that there were enormous patches of space, giant holes, where galaxies were almost completely missing. This discovery opened a whole new chapter in our understanding of how the universe is built. And at the heart of that revelation was the identification of a cosmic giant, the Bootes void. This remarkable discovery was made in the early years of the 1980s by a group of astronomers led by Robert Kirshner. His team included August Umler Jr., Paul Schechter, and Stephen Schechtman. Together, they were working on a large project to study how galaxies are spread out across space. But this wasn't a matter of just looking through a telescope and counting stars. To truly map the universe, they needed to figure out not only where galaxies appeared in the sky, but also how far away they were from Earth. This extra dimension, distance, would help them create a kind of three-dimensional map, showing how galaxies cluster, stretch into long filaments, and leave behind vast empty areas. To do this, they used a powerful tool called redshift. Redshift works a bit like how sound changes when a police siren moves away from you. The sound gets lower because the waves are stretched out. With light, something similar happens. When a galaxy moves away from us, the light it gives off is stretched out, shifting toward the red part of the spectrum. The more stretched it is, the faster the galaxy is moving away, and the farther away it must be. This idea goes back to the early 20th century, when the astronomer Edwin Hubble discovered that nearly every galaxy is moving away from us. He also found that galaxies farther away move faster. This connection between speed and distance, now known as Hubble's law, allowed scientists to calculate how far off a galaxy is just by measuring its redshift. So, using redshift, Kirshner and his team observed thousands of galaxies. They pointed their telescopes at a particular area of the sky and gathered the faint light coming from very distant galaxies. Then, they broke this light into a rainbow of colours, called a spectrum, to look for specific patterns. These patterns, like a fingerprint, told them what elements were in each galaxy, and more importantly, how much the light had been stretched. With this information, they calculated how far each galaxy was. As they collected more and more data, they gradually built up a detailed three-dimensional picture of galaxy locations in that region of the universe. But as they kept mapping the galaxies, they noticed something strange. In one part of the sky, specifically in the direction of the constellation Bootes, there were almost no galaxies at all. This wasn't because their instruments failed or because the region was hidden by dust. Their telescopes were working fine, and they were still seeing galaxies nearby and far beyond that area. But right in the middle, there was a giant stretch of space that was shockingly empty. It looked like a huge bubble in the cosmos, a spherical zone hundreds of millions of light years across with barely anything inside. By the year 1987, after years of hard work and careful study, they formally announced their findings in a major scientific paper. They named this huge empty space the Bootes void, after the constellation in whose direction it lies. The Bootes void turned out to be one of the largest cosmic structures ever found. Early estimates showed that it was about 250 million light-years in diameter. To grasp just how large that is, consider this. Our entire Milky Way galaxy is only about 100,000 light-years across. That means you could fit thousands of Milky Way-sized galaxies inside the Bootes void, and yet, this entire region holds only a handful of them. The discovery was a turning point. It showed that the universe is not just filled with stars and galaxies scattered like sugar in tea. Instead, the universe is full of structure, dense clusters and long filaments of galaxies that surround vast, empty regions like the Bootes void. This led scientists to think about the universe in a new way. Rather than being uniform, the cosmos appears to be shaped like a gigantic web. Galaxies are strung along threads, and these threads twist and wind through enormous bubbles of nothingness. This is what scientists now call the cosmic web. The Bootes void, one of its most striking features, helped reveal this hidden architecture of the universe. It showed that even in the vastness of space there are patterns, beautiful, strange, and sometimes haunting, in the way matter is spread. The scientific world responded with a mix of amazement and excitement when the Bootes void was discovered. It wasn't just the size of the void that stunned researchers, it was what it meant for our understanding of the universe. Before this, many of the simpler models of the cosmos had assumed that matter was spread out more or less evenly, like butter on a slice of bread. But this discovery changed everything. Here was a gigantic region of space, stretching hundreds of millions of light years across, that was almost completely empty. That kind of emptiness didn't fit the neat, balanced picture many scientists had in mind. This unexpected finding sparked a wave of new research. Scientists began to take a closer look at the earliest moments of the universe, trying to figure out how such an enormous empty region could have formed. Questions about the roles of dark matter and dark energy, those invisible forces that shape the structure and fate of the universe, became even more urgent. Researchers wanted to know if these mysterious components could help explain why some parts of the universe are filled with clusters of galaxies, while others, like the Booty's void, are eerily silent. The discovery also showed how powerful and important large-scale redshift surveys could be. Before this, most astronomers had focused their attention on individual galaxies or small groups of them. But the Booty's void made it clear that to truly grasp the universe's structure, scientists needed to map far larger stretches of space. It was a shift in thinking. The universe wasn't just a scattered collection of stars and galaxies. It was a vast, interconnected system, full of patterns, areas of great density and areas of near-total emptiness. In the years following the discovery, astronomers continued to scan the skies with better tools and more advanced redshift surveys. These later observations confirmed that the Booty's void was very real. They also revealed other similar voids, some smaller, but still significant in size. Surprisingly, scientists even spotted a few lonely galaxies inside the Booty's void. These rare galaxies were not completely surrounded by nothingness, but floated like tiny islands in a cosmic sea. Their isolation makes them incredibly valuable to scientists, because they offer a rare chance to study how galaxies evolve on their own, far away from the usual gravitational tug-of-war found in crowded regions of space. The techniques and tools developed during the study of the Booty's void have since become essential in the effort to map the universe. Thanks to this breakthrough, scientists have discovered countless other structures, some densely packed with galaxies, others almost completely empty. The Booty's void became more than just a strange dark patch in the sky. It became a symbol of scientific progress, a reminder of how much we still have to learn, and how much the universe can surprise us when we dare to look deeper. Its discovery in the early years of the 1980s did not just reveal a hole in space. It revealed a hidden part of the universe's design, something far more complex and mysterious than anyone had guessed. It showed us that the cosmos is not evenly filled, but shaped by both brilliant bursts of matter and enormous whispering voids. The Booty's void reminds us that sometimes it's in the quietest, emptiest places that the universe speaks the loudest truths. The universe is unimaginably vast, a realm so immense that the usual ways we measure distance, like kilometers or miles, quickly become useless. In our everyday lives, we think in terms of distances we can walk, drive, or fly. But in the grand theatre of the cosmos, such units are far too small to make sense. When scientists talk about galaxies, or even more gigantic structures made of many galaxies, they need something far bigger. That's where the light year comes in. A light year is the distance that light, which moves faster than anything else we know, can travel in the span of one Earth year. Light moves at a breathtaking speed of about 300,000 kilometers every second. Over the course of a year, that adds up to about 9,460,000,000,000 kilometers. Just imagine that. A single light year equals nearly 10 trillion kilometers. We need this enormous unit because the universe is so huge that even something as fast as light takes a long time to get from one place to another. But even with light years, the numbers involved in describing the cosmos quickly grow so large they seem almost impossible to picture. Our brains are wired to understand a trip across town, a road across a country, or maybe even a flight across the globe. But how do we grasp a journey that would take light millions of years? This brings us to one of the most mind-blowing features ever discovered in the universe, the Booty's void. This isn't just a large gap in space. It's a colossal hole in the structure of the universe, a place so empty and so vast that it stretches the limits of human imagination. When astronomers first mapped it out, they estimated it to be about 250 million light-years wide. Pause and let that number settle in. 250 million years is how long it would take light to cross from one side of the void to the other. To give some context, Earth itself is only about 4,500,000,000 years old. That means light has to travel for more than 5% of Earth's entire lifetime just to get across the Booty's void. That alone gives you an idea of how enormous this space is, not just large, but truly gargantuan, even by cosmic standards. And keep in mind, this isn't just a flat gap like a hole in a sheet of paper. It's a three-dimensional sphere, an almost perfectly round bubble of nothingness inside the universe. To understand just how immense this void is, let's compare it to something we know a little better, our home galaxy, the Milky Way. The Milky Way is a stunning spiral galaxy filled with between 100 billion and 400 billion stars, not to mention vast clouds of gas and dust, and a supermassive black hole sitting quietly at its centre. From one end to the other, the Milky Way stretches about 100,000 light-years. Now, if the Bootes void is 250 million light-years wide, and the Milky Way is 100,000 light-years across, then it would take 2,500 Milky Ways lined up end to end just to span the diameter of the Bootes void. Picture that, 2,500 galaxies, each filled with billions of stars all arranged in a line just to bridge this one massive emptiness. That image makes the sheer emptiness of the Bootes void even more astonishing. If you place the entire Milky Way galaxy right in the centre of it, our whole cosmic neighbourhood would be nothing more than a tiny speck, swallowed by a sea of darkness. From the edge of such a lonely Milky Way in the middle of the void, if you looked out into space, the night sky would look heartbreakingly empty. You wouldn't see the familiar arch of stars that make up our galaxy. You might not even see any nearby galaxies at all. The closest galaxy could be hundreds of millions of light-years away, so far that it might appear as just the faintest ghostly blur, if it were visible at all, even through the most powerful telescope. In such a place, the sense of cosmic isolation would be overwhelming. There would be no nearby galactic neighbours, no gravitational dances between galaxies, no explosions of supernovae from nearby stars lighting up the skies. Just cold, silent darkness. The Bootes void would live up to its name perfectly. It would truly be a void, a vast and nearly perfect example of cosmic loneliness. The gaps between galaxies in this region are not just a little larger than usual. They are so wide that the normal idea of galactic neighbourhoods simply doesn't apply anymore. This isn't a slightly empty region. It's a place that has been drained of galaxies over billions of years. Let's step back even further and consider a larger view of our cosmic surroundings. The Milky Way isn't alone. It belongs to a family of galaxies called the Local Group. This small cluster includes our Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 dwarf galaxies, all tied together by gravity. From one side to the other, the Local Group spans about 10 million light-years. That sounds like a lot, but again, it's tiny compared to the Bootes void. If you tried to stretch local groups across the width of the Bootes void, you could fit about 25 of them in a row. This tells us that the Bootes void is not just empty when compared to a single galaxy. It's empty even when compared to clusters of galaxies. In the Local Group, galaxies interact with each other, tugging and twisting through gravity, forming stars and triggering bursts of activity. But inside the Bootes void, such interactions are almost non-existent simply because there are so few galaxies around. This is the true scale of cosmic emptiness. It's not just that there's less stuff in the Bootes void, it's that the entire architecture of galaxies and clusters that make up the universe seems to have skipped over this region. Whatever processes shaped the large-scale structure of the cosmos left this particular area astonishingly blank. The Bootes void stands as a monument to the enormous, mysterious, and sometimes lonely nature of the universe, a vast invisible chasm hidden behind the glittering veil of stars that we see when we look up at the night sky. To truly understand just how gigantic the Bootes void is, we can compare it to other colossal structures in the universe, structures made up of galaxies bundled together, like galaxy clusters and even bigger ones called superclusters. A galaxy cluster is like a cosmic city, packed with hundreds or even thousands of galaxies. All of these galaxies are held together by gravity, forming a dense and massive structure. These clusters can stretch across distances from around 3 million to 30 million light-years. One well-known example is the Virgo cluster, which lies relatively close to us in cosmic terms. The Virgo cluster spans about 10 million light-years across, and our own local group of galaxies is slowly drifting in its direction. Now, here's the incredible part. Even a galaxy cluster as large as the Virgo cluster would look tiny when placed inside the Bootes void. You could line up 10, 50, or even 100 of these giant clusters side by side and still not completely fill the width of the Bootes void. It's like putting a row of skyscrapers across the Grand Canyon. No matter how tall they are, the canyon swallows them in scale. The difference in density is striking. A galaxy cluster is like a busy, crowded metropolis, while the Bootes void is like an endless desert with almost nothing in sight. But the universe doesn't stop at galaxy clusters. It builds even larger formations called superclusters. A supercluster is an enormous web of galaxy clusters and smaller galaxy groups all loosely connected by gravity. These are the largest known structures in the universe, forming vast filaments and cosmic highways of galaxies that can stretch for hundreds of millions of light years. One such structure is the Laniakea supercluster, which includes our own Milky Way galaxy. Laniakea spans about 500 million light years, an unimaginably vast distance. Now, the Bootes void has a diameter of about 250 million light years, which is about half the size of Laniakea, but still bigger than many other famous superclusters. This means that the Bootes void isn't just bigger than single galaxies or small galaxy groups, it is bigger than some of the grandest galactic structures in the entire universe. This fact alone makes the Bootes void stand out as something truly extraordinary. It's not just an empty gap between galaxies, it's a vast cosmic absence that matches the scale of the universe's largest and most complex structures. The universe is not evenly filled with galaxies like raisins in a cake. Instead, it is more like a sponge, with thick galaxy-rich areas separated by enormous empty bubbles. The Bootes void is one of the most massive of those bubbles, and here's where things get even more mind-blowing. The Bootes void isn't just wide, it's a three-dimensional sphere, like a bubble floating in space. That means it has volume, not just area. To understand how empty this bubble truly is, let's think in terms of volume. The volume of a sphere depends on the cube of its radius. The Bootes void has a radius of about 125 million light-years. If we compare that to our Milky Way galaxy, which has a rough radius of about 50,000 light-years and is shaped more like a flat disk, the difference becomes staggering. Even if we imagine the Milky Way as a perfect sphere just to make the math easier, the Bootes void would still be billions of times larger in volume. For every Milky Way-sized sphere, the Bootes void could hold billions of them. It's like comparing a single grain of sand to an entire mountain range. And remember, this enormous space isn't packed with billions of galaxies. It's nearly empty. That's what makes a void different from just a gap between galaxies. It's an enormous space where galaxies are missing from an entire volume, not just from a patch of sky. Now imagine trying to travel across this enormous emptiness. Even if we had a spaceship that could fly at 1/10 the speed of light, which is far beyond our current technology, it would still take more than 2.5 billion years to travel from one side of the Bootes void to the other. For comparison, life on Earth has existed for about 3.5 billion years, so this journey would take almost as long as the entire history of life on our planet. But in reality, our fastest spacecraft, like the Voyager probes, travel at speeds of only tens of kilometers per second. At that speed, crossing the Bootes void would take far, far longer than the entire current age of the universe, which is around 13.8 billion years. The idea of travelling such a distance is beyond what we can even grasp. Even communication would be incredibly difficult. Light, which is the fastest thing in the universe, would take hundreds of millions of years to travel across the void. If someone were inside the Bootes void trying to send a signal to another galaxy, it would take longer than human civilization has existed for that signal to arrive. Anyone living inside the Bootes void, if such a place could support life, would be completely alone. The nearest galaxies would be tens of millions of light years away, and the only thing visible in the sky might be faint, ancient starlight from galaxies so far away that their light took hundreds of millions of years to arrive. The loneliness would be unimaginable. But when scientists call the Bootes void a void or an empty space, they don't mean it's completely empty like a vacuum. In the cosmic sense, empty just means that there is a lot less stuff there than in other parts of the universe. Even in the deepest parts of the Bootes void, there are still some hydrogen atoms drifting around, the occasional photon of light from the cosmic microwave background, and of course, dark matter, which we cannot see but know is there. Still, compared to the average density of matter in the universe, usually a few atoms per cubic meter, the Bootes void might have less than 1 atom per cubic meter, maybe much less. That makes it one of the most underdense regions ever discovered. And yet, even in this emptiness, astronomers have found a few lonely galaxies, maybe around 60 of them, floating inside the Bootes void. These galaxies are incredibly isolated, separated from each other by tens of millions of light years. In any other part of the universe, that would be a huge distance, but in the Bootes void, it's the norm. This incredible emptiness is not just an odd curiosity. It tells us something profound about the way the universe is structured. It is not evenly filled with galaxies. It is not smooth. It is clumpy, uneven, and full of surprises, filled with bright, rich regions of light, but also with vast, silent stretches of darkness. The Bootes void is one of those silent stretches, and by studying it, we are forced to change how we think about the universe. We see that the cosmos is not only a place of shining stars and swirling galaxies, but also of deep silence and magnificent emptiness. To understand where the Bootes void is located in the vastness of the universe, we need to think about something called cosmic geography, the way the universe is arranged on a grand scale. Just like Earth has its own structure with continents, oceans, mountains, and valleys, the universe also has a kind of architecture, only on an unimaginably larger scale. The stars and galaxies are not just scattered randomly in all directions. Instead, they form an enormous interconnected pattern often called the cosmic web. This cosmic web is made up of huge, delicate strands, which scientists call filaments. These filaments are packed with galaxies, like beads on a thread, stretching for hundreds of millions of light years. Where many filaments come together, they form massive intersections or nodes where galaxies crowd together in dense clumps. But between these threads and intersections lie vast, dark and empty regions. These enormous spaces are called cosmic voids, and they are like the valleys of the universe, huge areas where there are very few galaxies, stars, or even much matter at all. One of the biggest and most famous of these empty regions is the Bootes void. It is a massive, nearly empty bubble in the cosmic web, and understanding where it is means first understanding where we are. Let's begin our cosmic journey right here, on Earth. Earth is one of 8 planets that orbit around the Sun, which is a middle-aged star. But our Sun is not alone. It is just one of hundreds of billions of stars that make up our Milky Way galaxy. The Milky Way is a beautiful spiral-shaped collection of stars, dust and gas that stretches about 100,000 light-years from one end to the other. Our Sun is located about 27,000 light-years from the centre of this spiral, tucked into one of its spiral arms. But the Milky Way itself is not alone either. It is part of a small group of galaxies called the Local Group. This group includes the Milky Way, our closest large neighbour the Andromeda Galaxy, and about 50 smaller dwarf galaxies. The Local Group spans a region about 10 million light-years across. Now, the Local Group is being slowly pulled toward a much bigger gathering of galaxies called the Virgo Cluster, which is about 55 million light-years away from us. And both the Local Group and the Virgo Cluster belong to a much grander region of space called the Laniakea Supercluster. This supercluster is a huge gravitationally connected region of the universe that spans roughly 500 million light-years. It's like our cosmic continent, a vast area filled with galaxies, clusters and filaments, all held together by gravity. So, our full cosmic address would be Earth, Solar System, Milky Way, Local Group, Virgo Cluster, Laniakea Supercluster. Once we understand where we are in the universe, we can then look out into the distance to find the Bootes void. From our point of view on Earth, it appears in the direction of a constellation called Bootes, also known as the Herdsman. Now, constellations are just patterns of stars that look like they are grouped together in the night sky, but in reality these stars can be very far apart in 3-dimensional space. So when we say that the Bootes void is in the direction of Bootes, we mean that if you aim a telescope toward that area of the sky, and then measure how far away the galaxies are, you'll come across a huge and astonishing emptiness, a gigantic 3-dimensional spherical region where almost nothing exists. It's not just a dark patch of sky, but a massive bubble-like hole in the fabric of the universe. The centre of the Bootes void is estimated to be about 700 million light-years away from Earth. That means the light coming from its centre began travelling toward us 700 million years ago, a time when life on Earth was still mostly in the ocean and complex creatures were just starting to appear. So when we look at the Bootes Void, we're not only looking far away in space, but also far back in time. This giant, silent region stands as one of the most mysterious and fascinating features in the grand design of the universe. The Bootes Void is not something we can find just beyond the edges of our galaxy. In fact, it lies unimaginably far away, far beyond our local galactic neighbourhood, even beyond the boundaries of our massive home supercluster, known as Laniakea. To reach even the closest edge of the Bootes Void, one would have to travel several 100 million light-years through space. That makes it an incredibly distant feature in the vast landscape of the cosmos. If we could lay out a gigantic map of the universe with Earth roughly at the centre, the Bootes Void would appear as a huge, dark, empty bubble, located far away from us, far beyond not just the Milky Way galaxy, but even beyond the entire supercluster we belong to. It is a structure of the far universe, not something nearby or local. The Bootes Void is a perfect example of what scientists call a cosmic void. These voids are enormous, empty regions that help shape the large-scale structure of the universe. To picture this structure, imagine a giant sponge or a web of soap bubbles. The parts of the universe that glow with stars and galaxies, the galaxy clusters and superclusters, gather along the outer layers of these bubbles. These glowing threads and walls are called filaments, and they're where matter has clumped together over billions of years, pulled in by gravity. But the spaces in between, the hollow parts of the sponge, are the voids. These are vast stretches of space where very few galaxies exist. The Bootes Void is one of the biggest and clearest of these empty spaces. Imagine, for a moment, a vast highway system in space. The filaments are like busy cosmic highways, packed with the hustle and bustle of galaxies racing along them. Now imagine a massive, abandoned roundabout or empty plaza in the middle of these roads. That's the Bootes Void. It's like a forgotten district in the heart of the universe, a place where very little happens, but which still plays a vital role in the overall structure. The Bootes Void shows us that matter in the universe is not spread out evenly, but instead arranged into an elaborate foamy design. All around the Bootes Void, astronomers have spotted some of the universe's largest structures. While the void itself is eerily empty, it is encircled by denser regions of the cosmic web, like a hollow in a sponge surrounded by thick walls. For instance, parts of the Hercules supercluster and the Corona Borealis supercluster are located nearby, though still hundreds of millions of light-years away. These mighty collections of galaxies act like the rocky shores that define the edges of a cosmic ocean. And that's exactly what the Bootes Void is. A gigantic ocean of emptiness, separating the continent-sized superclusters of galaxies. Over billions of years, the gravity from these surrounding structures has slowly pulled matter toward them, draining the Bootes Void and making it even emptier. As the universe expands, this process continues, stretching the void even larger. So, the Bootes Void is not just an empty place. It's a major part of how the universe is organized, marking the vast open areas between the bright, crowded regions of galaxies. To better understand this, let's compare it to something more familiar, a map of Earth. On such a map, continents represent places where land, like galaxies and stars, is found in abundance. The oceans, wide and mostly empty of land, represent the cosmic voids. The Bootes Void is like one of the largest oceans on this cosmic Earth, an enormous basin of emptiness, sitting between the land masses of galaxy-filled regions. Just as a ship travelling through the middle of the Pacific Ocean is unlikely to spot any land, a galaxy wandering through the heart of the Bootes Void would find itself alone in a vast sea of darkness. This comparison helps us see the Bootes Void not as a random patch of nothing, but as an important part of the universe's grand design. Though many other cosmic voids have been discovered, ranging in size from around 10 million to several 100 million light-years across, the Bootes Void remains one of the most famous. It was among the first truly massive voids ever found, and when astronomers first detected it, its sheer size was shocking. This helped make it a standard example, a kind of model void used to help understand others like it. It may not be the only one of its kind, but it stands out because of its clarity and how dramatically it revealed just how empty some parts of the universe can be. Its place in the cosmic web is typical for large voids, surrounded by bright filaments of galaxies and glowing clusters that form the scaffolding of the universe. By studying how the Bootes void fits into this grand pattern, astronomers can test their ideas about how the universe has evolved. For example, by looking at how galaxies are arranged along the void's edges and how the void itself has grown over time, scientists can learn more about the mysterious force called dark energy. This invisible energy is believed to be stretching space itself, helping to enlarge these empty regions. So, the Bootes void is more than just an empty patch. It is a key feature of the cosmic landscape. Its location, its shape, and its relationship to the surrounding galaxy-filled filaments give astronomers valuable clues about the invisible forces shaping our universe. It stands as a quiet but powerful witness to the dynamic processes that have carved the universe into a web of light and shadow, of matter and emptiness, over billions upon billions of years. Gravity is often called the weakest of the four fundamental forces in nature. That may sound surprising, especially when we think about how it seems to control everything from falling apples to the movements of planets. But despite being weak compared to other forces like electromagnetism or the strong nuclear force, gravity has quietly shaped the largest and most magnificent structures in the entire universe. Over the course of billions of years, gravity has been at work, pulling things together slowly, patiently, and relentlessly. It has taken clouds of a loose gas and turned them into glowing stars. It has pulled those stars into swirling galaxies. It has then gathered those galaxies into even bigger structures, clusters, superclusters, and long, thread-like filaments that form the grand structure of the cosmos. This intricate pattern, which astronomers call the cosmic web, stretches across the universe like a vast, invisible spiderweb. But gravity doesn't just build up things, it also tears things apart, or rather clears them out. Strangely enough, gravity is also responsible for creating enormous empty regions of space, known as cosmic voids. These are vast, dark areas where very few galaxies exist. A famous example is the Bootes void, a cosmic desert that is so huge and so empty, it's hard to believe such a place exists. So, gravity is not only the force that gathers matter into dense cosmic cities, but it's also the one that clears out the enormous wildernesses between them. In this way, gravity acts as a cosmic sculptor, shaping the universe by both pulling matter together and creating vast emptiness between those gatherings. At its most basic level, gravity is just a pull between two things that have mass or energy. The more massive something is, the stronger its pull, and the closer two objects are, the stronger the gravitational force between them. This rule was first discovered by Isaac Newton in the late 17th century, and later improved upon by Albert Einstein in the early 20th century through his theory of general relativity. This simple but powerful force is what causes an apple to fall to the ground. But it's also what makes galaxies spin and drift apart over billions of light years. After the Big Bang, about 13.8 billion years ago, the universe was extremely hot, incredibly dense, and almost perfectly smooth. But almost is the key word. There were tiny bumps, very slight differences in density, like gentle ripples in a calm sea. Imagine this early universe as a smooth ocean, with very tiny rises and dips. In the areas where there was just a little more matter, gravity was a little bit stronger. That stronger pull slowly began to gather more matter toward those areas, and as more matter collected, gravity grew stronger, attracting even more matter. This snowball effect, where tiny lumps grow larger and larger, is called gravitational instability. These slightly denser spots eventually grew into the first building blocks of structure in the universe. Over millions and then billions of years, they became galaxies, clusters, and the long filaments of the cosmic web. But what about the places that started off with less matter? There, gravity was weaker. As the denser areas began pulling in more material, they essentially stole matter from their emptier neighbours. The low-density regions couldn't hold on to their sparse material, and it slowly flowed away. These regions became emptier and emptier over time. Gravity, in trying to gather things together in some places, was also draining matter from others. That's how the great cosmic voids formed, like the Bootes void, an enormous empty area that was left behind as matter was pulled away by its denser surroundings. Now, to truly understand how all of this happened, we need to talk about something mysterious: dark matter. Dark matter is a type of matter that doesn't give off light, doesn't reflect it, and doesn't absorb it. In fact, it doesn't interact with light at all, which is why we can't see it directly. But we know it's there because of how it affects the things we can see. Dark matter makes up about 85% of all matter in the universe. That means the stars, planets, gas, dust, everything we see makes up less than 15%. The rest is invisible, but its gravity is very real. When the universe was still young, those tiny density ripples were mainly ripples in dark matter. These little clumps of invisible matter became deep gravitational wells that pulled in both dark matter and regular matter. Ordinary gas and dust fell into these invisible pits, cooled down, and eventually formed stars and galaxies. Without these dark matter clumps, regular matter wouldn't have been able to gather fast enough to form anything meaningful. The universe would have remained mostly smooth, with no galaxies, no stars, and likely no life. So, the cosmic web, this giant lacy pattern of filaments, clusters, and empty regions, is really a dark matter structure. The long filaments are dark matter highways, drawing galaxies along their length. The clusters are giant, heavy knots of dark matter that act like galactic hubs. And the voids, like boots, are places where even the dark matter is sparse. The galaxies we can see, those glowing dots in telescope images, are just tiny lights sitting on top of a much bigger invisible structure made of dark matter. The reason the Booty's void is so empty is likely because it started out with very little dark matter, and since it didn't have enough gravity to attract and hold on to matter, it gradually lost even more material to nearby, denser regions. Over billions of years, it became a vast and lonely part of the cosmos. If we zoom into smaller scales, we see that the same rules of gravity apply. Inside giant clouds of gas, gravity pulls atoms together, forming stars. Those stars pull on each other, creating star clusters. On a larger scale, billions of stars and clouds of gas and dust are pulled together into galaxies, like our own Milky Way. Even the graceful spiral shape of our galaxy is shaped by gravity, all of it held together by a surrounding halo of dark matter. As we look at even bigger parts of the universe, gravity keeps on doing its quiet but powerful work. It's not just stars and planets that are pulled together. Entire galaxies, like our Milky Way and its neighbour Andromeda, also feel each other's pull. Over time, these galaxies are drawn toward one another and come together to form small groups, such as the one we live in, called the local group. But it doesn't stop there. These galaxy groups are themselves pulled toward even larger clumps of matter. Many of them come together to form galaxy clusters, huge gatherings that can hold hundreds or even thousands of galaxies. The gravity in these clusters is so strong that it tugs on galaxies nearby, pulling them inward toward the crowded centre. Even more fascinating, these massive clusters are often joined by long, thin threads made up of galaxies. These threads are called filaments, and they stretch across space like the strands of a cosmic spider web. Galaxies move along these filaments, following the invisible paths carved out by gravity, flowing toward the biggest and heaviest clusters. Altogether, this enormous network of clusters and filaments forms what scientists call the cosmic web, a vast web-like structure stretching across the universe. This is where gravity has been especially successful, gathering matter into dense connected shapes and slowing down the natural expansion of space in these areas. But not all of space is filled with galaxies and clusters. There are also the voids, giant, dark, and nearly empty parts of the universe. These are the opposite of the filaments. As gravity pulls matter into the cosmic web, it leaves behind huge stretches of nothingness. One of the most famous of these empty regions is the Booty's void. The Booty's void is unbelievably large and incredibly empty. It was born as a slightly less dense region in the early universe, a place with less dark matter than surrounding areas. Over the course of billions of years, gravity acted like a cosmic vacuum. The stronger gravity from the surrounding filaments and clusters slowly pulled matter away from this underdense region, making the Booty's void even emptier. It's as if space itself was drained, leaving behind a hollow shell. Inside this immense emptiness, only a few galaxies remain. These are often called lonely galaxies. They either formed from the small patches of leftover matter within the void, or they were simply too isolated and too tiny to be pulled out by the gravitational tug of nearby structures. Their lonely existence is living proof of just how powerful gravity can be. It literally cleared out everything around them and left them stranded in the dark. Now, one of the most important things to understand about gravity is that it works very slowly. Its effect is not immediate. It takes a very, very long time to shape the universe. In fact, the universe itself has been evolving for about 13.8 billion years since the moment of the Big Bang. In the beginning, the universe wasn't perfectly smooth. Some areas had just a little more matter than others. These tiny differences in density, barely noticeable at first, were enough for gravity to get to work. Over billions of years, gravity pulled on the slightly denser areas, causing them to grow. Slowly but surely, these regions became galaxies, clusters, and filaments. At the same time, the less dense regions, the voids, were emptied out even more. Gravity may be the weakest of the four fundamental forces in nature, but its slow, steady, and patient pull has completely reshaped the cosmos. It turned tiny wrinkles in the early universe into enormous structures that can hold themselves together, even as space itself continues to expand. And in doing so, gravity not only built the bright and shining parts of the universe, but also carved out the vast and silent darkness between them. The universe often brings to mind a breathtaking picture, one filled with shining stars scattered across a velvet black sky, countless galaxies spinning like glowing whirlpools, and majestic clouds of gas called nebulae lit up by the birth of newborn stars. We picture a cosmos that is alive and full of motion, bursting with colour, energy, and activity in every direction. In this picture, grand spiral galaxies like our own Milky Way hold hundreds of billions of stars, many of them surrounded by planets, moons, and possibly even life. This beautiful, energetic vision is certainly real, but it only tells one side of the cosmic story. There is another side, one that is quiet, cold, and profoundly empty. For every bright cluster of stars or galaxies, there are enormous regions of space where there is almost nothing, places where the fabric of the universe itself seems stretched thin. These are the vast, dark deserts of the cosmos, and one of the most mysterious and extreme of them is known as the Bootes Void. The Bootes Void is not just a space that is less full, it is staggeringly empty by cosmic standards. Scientists use the word sparse to describe it, but in truth, that word barely captures how empty it really is. Even the best vacuum chambers created on Earth, which are considered extremely empty, still contain millions of atoms in every cubic meter. In comparison, the average density of the entire universe is already extremely low, only about 1 hydrogen atom per cubic meter when you spread all the matter and energy evenly across space. That's a level of emptiness hard to imagine. The air you're breathing right now contains trillions upon trillions of atoms in each cubic centimeter. And remember, a cubic meter holds 1,000,000 cubic centimeters. Now, imagine a region of space that is even emptier than that tiny average. This is exactly what scientists found in the Bootes Void. In the heart of this vast dark area, the amount of ordinary matter, like atoms, stars, and galaxies, can be 10 times lower than the already thin cosmic average. In other words, there may be far less than 1 atom per cubic meter, perhaps just a few lonely atoms floating in a space as large as a building, or even as big as an entire city block. This is not just empty, it is emptier than anything we can create or easily comprehend. What truly stands out about this sparseness is not just the lack of atoms, but the near total absence of luminous matter, the kind that shines and gives off light. Galaxies, stars, glowing gas clouds, all the things we usually associate with the universe are incredibly rare in the Bootes Void. In a region of space that might normally hold hundreds or even thousands of galaxies, the Bootes Void might contain only a handful. These are not just galaxies that are farther apart. They are galaxies that exist in near isolation, like islands in a vast, dark sea. If you could somehow find yourself inside the Bootes Void and look up at the sky, the scene would be eerily dark. Instead of a glittering sky filled with starlight, you might see only a few faint smudges of light. Distant galaxies so far away that they would appear as dim, lonely specks, separated by hundreds of millions of light years. There would be no glowing nebulae, no fiery stellar nurseries, and no brilliant galactic collisions lighting up the darkness. The silence would not just be one of sound, it would be a silence of light. This deep emptiness is not a random accident. It is the result of how matter was arranged in the very earliest moments of the universe's history. Over 13 billion years ago, when the universe was still young, it was not perfectly smooth. There were tiny differences in the density of matter. Some areas were just slightly thicker than others. The denser spots pulled in more material through the force of gravity, growing into the long filaments and huge galaxy clusters we see today. But the less dense regions had the opposite fate. As the universe continued to expand, these slightly underfilled areas were stretched further and further, causing even more matter to drift away toward denser regions. Over billions of years, this process carved out the great voids, giant cosmic hollows like the Bootes void. Even though these places seem utterly empty, they are not completely without matter. One of the most important and mysterious forms of matter in the universe, dark matter, is still present inside these voids, although it too is more thinly spread than in other regions. Dark matter doesn't shine or reflect light, and we can't see it directly. But we know it's there because of its gravitational pull. It helps shape the overall structure of the universe, even in these nearly empty places. Its behaviour is also affected by those early tiny differences in density, so even voids like Bootes carry the imprint of the universe's earliest moments. More mysterious still is something called dark energy. Unlike dark matter, which pulls things together, dark energy pushes space itself apart. It is believed to be responsible for the fact that the expansion of the universe is speeding up. Scientists think that dark energy is evenly spread throughout all of space, filling galaxies, clusters, and yes, even the voids. In fact, voids like the Bootes void may be the best places to study dark energy, because there is so little matter to interfere with its effects. In these silent, vast regions, the influence of dark energy can become more visible, more noticeable, and more measurable. So when scientists call a place in the universe sparse, they mean something far beyond what we normally think of as empty. They are describing regions where the ingredients of everything, stars, planets, atoms, light, are so rare and scattered that even calling them places seems strange. These voids are reminders that the universe, though filled with brilliance and wonder, is also shaped by silence and darkness. They are the deep shadows behind the glowing lights, the vast hollows that give the cosmic web its structure. And the Bootes void, one of the largest and most haunting of them all, stands as a quiet monument to the powerful forces that shaped everything we see. Inside a vast and nearly empty region of space like the Bootes void, the gravitational environment is completely different from what we see in crowded areas like galaxy clusters. In a galaxy cluster, there are hundreds or even thousands of galaxies packed closely together. These galaxies are always pulling on each other with their gravity. Sometimes they swing past one another, sometimes they tug and twist each other into new shapes, and occasionally they even crash into one another and merge. These powerful gravitational interactions help shape how galaxies grow and change. They affect the birth of new stars, the shape of the galaxies, and how gas is spread out inside them. But inside the Bootes void, things are much quieter and lonelier. Only a few galaxies exist in this enormous stretch of space, and they are so far apart that their gravity barely reaches each other. The nearest big groups of galaxies are located hundreds of millions of light years away. That's an unimaginable distance, so far that their gravitational pull on the galaxies inside the void is extremely weak, almost like a whisper in the dark. This means that the galaxies and matter floating inside the void mostly feel a gentle tug from the faint dark matter scattered through the void, and a tiny pull from the very distant galaxy filaments on the outer edges. Because of this deep isolation, the galaxies within the Bootes void are not disturbed by outside forces. They are free to drift with the universe's overall expansion, spreading out even more slowly and peacefully than their counterparts in crowded areas. They evolve in a calmer, quieter way, untouched by the chaos and violence of galactic collisions or nearby gravitational chaos. It's a place of stillness in a universe that is often wild and loud with activity. But it's important to understand that cosmic voids like the Bootes void are not just the usual empty spaces we find between galaxies. Even in a galaxy cluster or a galaxy filament, the space between galaxies is mostly empty, but not entirely. Those intergalactic regions, even though thin and vast, are still relatively close to dense parts of the universe, and they often contain a very faint fog of gas known as the intergalactic medium. This gas can even be heated by nearby galaxies that are actively forming stars or by powerful black holes at their centres. Cosmic voids are something else entirely. They represent emptiness on a much greater level. They are not just empty spaces between a few galaxies. They are enormous zones that stretch between entire superclusters of galaxies. In these voids, there are fewer galaxies, fewer stars, fewer black holes, and almost no powerful sources of energy. The intergalactic medium here is even thinner and colder than in other places because there's barely anything to heat it up. The lack of gravity, matter, and energy sources defines these regions and sets them apart from the rest of the universe. Voids are like vast deserts in the cosmic landscape, not just quiet, but almost completely abandoned by the usual building blocks of galaxies. The extreme emptiness of the Bootes void, and of other similar voids, makes them incredibly difficult to study. Because there are so few stars and galaxies inside them, very little light comes from these areas. Astronomers have to use some of the most powerful telescopes in the world, and they must observe these regions for many hours or even days to collect the tiny amounts of light that do exist. The galaxies inside the voids are so rare and so faint that studying them takes extraordinary effort and patience. Yet this very emptiness is what makes the Bootes void so scientifically valuable. In places where there is almost no ordinary matter, we can better understand the influence of something else: dark energy. Dark energy is a mysterious force that scientists believe fills all of space and is pushing the universe to expand faster and faster. In crowded parts of the universe, it is difficult to separate the effects of gravity from the effects of dark energy. But in the peaceful, low-gravity environments of voids, dark energy can be studied more clearly. By looking at how quickly voids like the Bootes void are expanding and how matter is spread out inside them, scientists can collect important clues about how the universe is growing and changing over time. They can test different theories about what dark energy is, how it works, and why the expansion of the universe is speeding up. In the middle of one of the most empty and silent places in the universe, the Bootes void, something surprisingly beautiful and strange exists: a small group of lonely galaxies. Even though this region is known for its deep darkness and lack of stars and glowing matter, it is not completely empty. Hidden inside this enormous cosmic desert are a few galaxies scattered across its vastness. Astronomers call them void galaxies, or lonely galaxies, because they live in almost total isolation, far away from the crowded places where most other galaxies can be found. These galaxies are like tiny boats drifting in an endless dark ocean, so far from any neighbours that they seem to float alone in space. In most parts of the universe, galaxies live in busy environments. They pull on each other with gravity, sometimes crashing together or merging to form new shapes. But inside the Bootes void, these lonely galaxies have no such interactions. They exist in peace, undisturbed by the usual cosmic drama. This gives scientists a rare and special opportunity. They can study how galaxies grow and change when they are left entirely on their own, without the push and pull of nearby galactic neighbours. When astronomers first discovered the Bootes void in the year 1981, they believed it was almost completely empty. Early surveys showed little more than a dark stretch of sky. But over time, as technology improved and telescopes became more powerful, researchers began to notice faint traces of light, signals from a few distant galaxies hiding in the darkness. Today, scientists estimate that about 60 galaxies have been identified within the Bootes void. Considering how massive this area is, that number is shockingly small. To understand just how empty the Bootes void is, let us make a comparison. If galaxies were spread out evenly across the universe, then a region the size of the Bootes void should contain thousands, or even tens of thousands of galaxies, especially ones the size of our Milky Way. Instead, there are only about 60. These few galaxies are not clustered together. Instead, they are spread far apart, often separated by 10 million or even 20 million light-years from one another. Imagine standing on a planet in one of these galaxies and looking up at the night sky. You would see almost nothing, just a few faint patches of distant light, like whispers in the dark. The glowing threads of the cosmic web, the large-scale structure of the universe, would be almost invisible, tiny pinpricks of light scattered across a nearly black sky. Because these galaxies live in such a quiet and empty place, they are quite different from those in busy galactic neighbourhoods. One of the most noticeable differences is in their shapes. In crowded galaxy clusters, galaxies often bump into each other or pass close enough to feel strong gravitational forces. These encounters can rip away gas, squash or stretch a galaxy's shape, or even cause sudden explosions of starbirth. But in the Booty's void, these lonely galaxies are rarely disturbed. They don't get pulled or pushed around, and they almost never crash into anything. Because of this, many of them still have their original shapes. Most are faint spirals or irregular galaxies that look more untouched, like relics from an earlier time in the universe. Their structure is mostly controlled by what happens inside them, rather than by outside forces. Another important difference is how they form stars. To make new stars, a galaxy needs large supplies of cold gas and dust. In crowded places, this gas can be stripped away by hot intergalactic material or stolen during galactic collisions. When that happens, the galaxy can no longer make new stars and begins to age. These galaxies are often called red and dead, because they stop shining with the blue light of young stars and instead glow dimly with older, redder stars. But the lonely galaxies of the Boot's void do not face this problem. Since there are no nearby galaxies and no dense gas clouds to strip away their material, they can keep their star-making fuel for a very long time. As a result, these void galaxies tend to have slower, steadier star formation. They are like quiet workshops, slowly crafting new stars without interruption. Many appear bluer than galaxies and clusters, showing that they still have young stars being born. This calm, ongoing star formation gives scientists a window into what galaxies might look like if they were left to evolve naturally over billions of years without the chaos of galactic collisions or tidal forces. However, studying these lonely galaxies is not easy. First, they are incredibly far away from Earth, and because they are not forming huge numbers of bright new stars, they appear very dim. The light they send out takes hundreds of millions of years to reach us, and by the time it gets here, it is faint and hard to detect. To study them properly, astronomers need to use some of the world's most powerful telescopes, both on Earth and in space, and keep the cameras pointed at one spot for many hours, sometimes even days. Getting time on these telescopes is very competitive, so each chance to observe one of these galaxies is precious. Second, their isolation makes them harder to study in other ways. In normal galaxies that live in clusters or along the filaments of the cosmic web, astronomers can use nearby bright galaxies to help with measurements or to observe things like gravitational lensing. But in the Booty's void, there are no helpful neighbours. Each lonely galaxy must be studied on its own, using only the faint light it produces. There's also a problem with how few of these galaxies we have actually found. With only about 60 known galaxies in the Boot's void, it's hard to know if they represent all types of void galaxies, or just the ones we're able to see with our current instruments. It's very possible that there are many more faint small galaxies hiding in the darkness that we simply haven't found yet. This means that our current list might be biased toward the larger and brighter ones, leaving out an entire population of smaller or more mysterious void dwellers. Still, scientists continue to carefully collect data. They study the redshifts of these galaxies to figure out how far away they are and exactly where they sit inside the Booty's void. They examine their light using spectrographs to learn about what they're made of, how fast stars are forming inside them, and how their material moves. Every observation adds a little more to our understanding. Even though it can be difficult to study them, galaxies that live alone, far from the crowded neighbourhoods of the universe, hold incredible value for science. These solitary galaxies, often drifting in enormous cosmic voids, offer rare clues that help astronomers answer some of the biggest questions about how galaxies are born, grow, and change over time. Think of these lonely galaxies as the universe's version of a control group in an experiment. Most galaxies are packed close together in busy areas like clusters or along cosmic filaments, where they constantly interact with each other, pushing, pulling, colliding, and even merging. But lonely galaxies, isolated in vast, quiet regions of space, live without much outside interference. By comparing what happens inside these isolated galaxies to those in crowded areas, scientists can start to figure out which changes come from a galaxy's own inner workings and which are caused by its surroundings. For example, suppose there's a galaxy in a dense cluster that has stopped making new stars because it has lost all its gas. Then imagine another galaxy, about the same size and age, sitting quietly inside a cosmic void. If that lonely galaxy still has its gas and is still forming stars, the difference suggests that something in the crowded cluster, like a force called Ram pressure stripping, which blows gas out of galaxies, may be responsible. In this way, astronomers can better understand the different paths galaxies take, depending on where they live. Over billions of years, these environmental effects can shape a galaxy's future in dramatic ways. But that's not all. Because lonely galaxies have spent most of their lives in peace, without bumping into their neighbours or merging with them, they may have kept more of the original features they had when they first formed. This makes them like ancient time capsules, preserving clues from the very beginning of the universe. By studying them, scientists may learn what galaxies were like in the earliest times, especially in areas where matter was sparse. Looking ahead, the future of studying these cosmic recluses is incredibly exciting. New generations of telescopes, both in space and on the ground, are opening up the universe in ways we could only dream of before. One of the most powerful of these is the James Webb Space Telescope. This telescope, which looks at the universe in infrared light, is so sensitive that it can spot very faint and very distant galaxies that older telescopes simply couldn't see. It was launched in the year 2021 and has already begun transforming our view of the cosmos. Meanwhile, enormous new ground-based telescopes, fitted with cutting-edge technologies like adaptive optics and extremely sensitive detectors, are also on the way. These observatories will help astronomers discover many more lonely galaxies, even the smaller and dimmer ones that are now hidden from our view. With larger samples to study, scientists will be able to look more closely at how these galaxies store gas, how they form stars, and what their inner structures look like. Altogether, this will help paint a clearer, fuller picture of how galaxies grow and survive when they're truly on their own. Perhaps most fascinating of all is imagining what the universe might look like from inside one of these lonely galaxies. Imagine a distant planet, orbiting a star in such a quiet corner of the cosmos. If intelligent life were to develop there, their night sky would be completely different from ours. On Earth, we look up and see a sky filled with stars, planets, and the glowing band of the Milky Way stretching across the heavens. But for beings in a lonely galaxy, maybe one floating inside the vast emptiness of the Bootes void, the view would be far more empty. The Milky Way would be so distant that it wouldn't be visible at all. Their night sky would be mostly black, with only a few stars from their own galaxy scattered across it. With powerful telescopes, they might spot the faintest twinkles from other isolated galaxies, hundreds of millions of light years away, but these would be tiny, barely visible points of light. For such beings, the universe might feel like a lonely, desolate place. They might believe that their galaxy was the only one in existence, never knowing about the vast web of billions of galaxies stretching far beyond their reach. Their understanding of the cosmos would be shaped entirely by the quiet, empty world they saw around them. For much of human history, our understanding of the universe was quite limited. In the beginning, we could only see individual stars twinkling in the night sky. Later on, we discovered that those stars were not just scattered randomly, but were part of much larger systems called galaxies. For a time, even galaxies themselves were thought to be floating aimlessly through the vast emptiness of space, like tiny specks of dust drifting through a dark, silent room. But as time went on, our telescopes became more advanced and powerful. Scientists also developed better tools to measure distances across the universe with incredible precision, and what they uncovered completely changed the way we look at the cosmos. Instead of finding a random jumble of galaxies, they revealed something truly breathtaking, an enormous, organized, and interconnected structure stretching across the entire universe. This incredible arrangement, made of galaxies, invisible dark matter and mysterious forces, is called the cosmic web. To picture it, imagine a gigantic spider web, not flat but three-dimensional, spanning distances so vast that our minds can barely grasp them. The galaxies are not sprinkled evenly throughout space like sugar in a bowl. Instead, they gather along long, thin threads of this web, lighting up the cosmic structure like tiny lanterns. Where the threads cross and knot together, galaxies clump in large groups, forming what could be described as enormous cities of stars. And in between these glowing strands are the dark, empty spaces, the great cosmic voids, like the holes in a sponge or the spaces between tree branches in a forest at night. Now, this grand web cannot be captured in a single photograph. It's too big and too complex. Instead, scientists have had to piece it together slowly by mapping the locations of millions upon millions of galaxies one at a time. Every galaxy becomes a tiny dot on an immense cosmic chart. When enough dots are connected in 3 dimensions, a pattern emerges, a web-like structure that shows how galaxies are distributed across the universe. This map is one of the most beautiful and profound discoveries in the history of astronomy. The cosmic web is made up of 3 main parts, each with its own special role in shaping the universe. The first and most visible parts of the cosmic web are the filaments. These are long, thread-like structures that stretch across the universe like the arms of a great galactic octopus. Each filament can extend for hundreds of millions of light years, so long that even light, travelling at over 299,000 kilometers per second, would take hundreds of millions of years to cross from one end to the other. Galaxies are not randomly placed within these filaments. They are strung along them like glowing beads on a necklace. Our own home, the Milky Way galaxy, is nestled inside one of these filaments, located in a relatively quiet part of the cosmic web. These filaments serve as the highways of the universe, channels through which galaxies and matter flow toward denser regions. But these highways aren't straight or smooth. They twist, bend, and branch, shaped by the invisible pull of gravity over billions of years. Along their lengths, galaxies gather into smaller clusters and groups, constantly in motion, tugged toward the larger structures nearby. These filaments form the skeleton of the universe, the hidden framework upon which galaxies are built, shaped, and moved. The discovery of these vast, glowing threads helped astronomers understand that the universe is not chaotic, but carefully structured. Seeing how these filaments stretch across space gave us new insight into how galaxies came to be where they are. The next major part of the cosmic web are the clusters, also called nodes. These are the places where several filaments come together, like the intersections of highways or the knots in a spider web. And just like a busy city where roads meet, galaxy clusters are full of activity. Galaxy clusters are the heaviest and most crowded places in the universe. They can contain hundreds, sometimes thousands of galaxies, along with huge clouds of hot gas that shine brightly in X-rays, and enormous amounts of invisible dark matter. These clusters are held together by their own powerful gravity, forming the largest known structures that are bound by gravity. One famous example is our own local group, which includes the Milky Way. This small group of galaxies is part of a much larger structure called the Laniakea supercluster, a vast region full of galaxy clusters like shining jewels in the sky. Inside these clusters, galaxies are close enough to constantly interact. Sometimes they crash into one another, sometimes they pull gas from their neighbours, or even merge entirely. These interactions cause galaxies to grow, change shape, and evolve quickly. The gravitational pull of a galaxy cluster is so strong that it draws in other galaxies from the filaments around it, like a city drawing people in from the countryside. These clusters are the most crowded and lively parts of the cosmic web, and their existence balances perfectly with the quiet emptiness of the voids. And now, we come to the most mysterious and haunting parts of the cosmic web, the voids. These are the enormous, nearly empty spaces that lie between the filaments and clusters. They are the silent oceans of the universe, where galaxies are few and far between. One of the most famous examples is the Bootes void, a colossal bubble of near-nothingness. It is so large that light would take hundreds of millions of years to cross from one side to the other. In these regions, there are hardly any galaxies at all, sometimes fewer than 1/10 the number found in average parts of the universe. They are not completely empty. There may still be stray atoms or the occasional lonely galaxy drifting through. But compared to the bustling filaments and clusters, these voids are deserts of space. What's even more fascinating is that these voids are growing larger over time. As the universe expands and gravity pulls matter toward the denser parts of the web, the voids stretch and become emptier. The galaxies that once might have existed inside them have been drawn away, leaving behind vast cosmic silence. Inside a void, a single galaxy might exist in total isolation. No neighbours, no nearby clusters, no bright companions. These lonely places help scientists understand just how unevenly matter is spread across the universe, and why some galaxies are shaped by interaction, while others live undisturbed lives for billions of years. Together, the filaments, clusters, and voids form the grand structure of everything we know, the cosmic web. It is a universe-sized network that has taken billions of years to grow into its current form. Galaxies are not scattered like confetti in a storm. They are carefully woven into a cosmic tapestry, shaped by gravity, dark matter, and time. The mystery of how gigantic empty regions, like the Bootes void, fit into the grand structure of the universe is not just a side question. It is at the very heart of how the universe is built. These voids are not random patches of nothingness scattered around by chance. Instead, they are essential parts of a much larger, carefully woven pattern called the cosmic web. To picture this better, imagine stretching a large piece of rubber fabric. As you pull on one part of it, the area you're stretching becomes denser, while other parts become thinner and emptier. Something very similar happened in the early universe. As gravity began pulling matter together into long, thread-like structures called filaments, and into dense collections called galaxy clusters, other regions were left behind, emptier, thinner, and more spacious. These leftover regions are the voids. The Bootes void is one of the most stunning examples of this process. It is an enormous region in space where very little matter gathered, due to the specific starting conditions of the universe, combined with the powerful effects of gravity and the never-ending expansion of space. You can think of it like a giant bubble in a foamy sponge. This bubble is surrounded by walls, not solid, visible barriers, but rather zones where galaxies have clumped together in greater numbers. These walls mark the edges of the void and are made of the very filaments that form the skeleton of the cosmic web. So, the Bootes void is not floating outside the universe's structure. It is part of it. In fact, it plays a crucial role in showing us how matter is spread out unevenly on the largest scales imaginable. It is a massive hole in the sponge-like layout of the cosmos. The filaments and clusters are the dense, spongy parts, while the voids are the empty pockets. This strange but beautiful cosmic foam is how the universe organizes itself. To understand where the Bootes void fits in, it helps to know where we are. Our home galaxy, the Milky Way, belongs to a small collection of galaxies called the Local Group. This group, in turn, is part of an even larger structure known as the Laniakea supercluster, which stretches across a huge region of space like a vast continent of galaxies. We do not live in a void. Our galaxy is tucked inside a fairly crowded part of the cosmic web, a filament that is slowly being pulled toward a denser, more massive region near the centre of the Laniakea supercluster. The Bootes void lies far beyond this neighbourhood. It is located hundreds of millions of light-years away, more than 300 million light-years in fact. It sits in a very different part of the cosmic map. Compared to the busy cities of galaxies we live in, the Bootes void is more like a lonely desert, a reminder of just how varied and enormous the universe really is. From bustling galactic highways to silent cosmic wastelands, the universe holds every kind of environment imaginable. By knowing where we are, we get a clearer view of just how vast and diverse the cosmic landscape truly is, and how important these voids are in the big picture. Now, this grand cosmic web is not just an idea dreamed up by scientists. It has been observed and confirmed using some of the most advanced tools in astronomy. Thanks to powerful telescopes and huge surveys that measure something called redshift, astronomers have been able to carefully map the three-dimensional locations of millions of galaxies. Redshift helps them figure out how far away each galaxy is, based on how its light stretches as it travels through the expanding universe. By combining all of these distance measurements, scientists have built detailed three-dimensional maps of the universe. And when these maps are put together, something incredible appears. The cosmic web comes into view as clear as a picture. Filaments show up as long chains of galaxies linking together like cosmic bridges. Clusters shine brightly where those chains intersect, and in between, huge dark spaces appear where galaxies are almost entirely missing. These are the voids. The Bootes void was one of the very first and most striking examples ever found. Its sheer size and emptiness helped prove that the universe is not evenly filled with matter, but instead arranged in a complex web-like pattern. It was a major piece of evidence that showed scientists that voids, filaments, and clusters all fit together to create a vast cosmic design. Today, With even better telescopes and more advanced surveys, these maps are becoming sharper and deeper, revealing the cosmic web in more detail than ever before. They continue to confirm what scientists predicted, that voids are not accidental gaps. They are vital parts of how the universe is built. The universe we see today is filled with an astonishing variety of structures. From the tiniest building blocks of matter, atoms, to massive galaxy clusters stretching across millions of light years, everything is arranged in patterns that are both beautiful and complex. But the universe didn't always look this way. If we travel back in time to the very beginning, right after the Big Bang, over 13 billion years ago, we find a universe that was shockingly different. It was unimaginably hot, extremely dense, and, most importantly, almost perfectly smooth. Picture an enormous pot of perfectly blended cosmic soup, with matter and energy mixed together so evenly that no part stood out. There were no stars, no galaxies, no clusters, no empty gaps, just a glowing fog of particles and light, all spread out in nearly the same way everywhere. Yet today, when we gaze into space, we see a universe filled with shining galaxies gathered into long, twisting filaments, while between them lie vast, dark voids, immense empty regions like the famous Bootes void, which spans hundreds of millions of light years. How did we get from that smooth, hot soup to the rich, lumpy, web-like structure we see today? This question lies at the heart of modern cosmology. The answer, as incredible as it may seem, begins with unimaginably tiny differences that existed right from the start. Differences so small they were almost invisible, but they were enough. Over billions of years, with the help of gravity and the continuous stretching of space, these tiny variations grew into the mighty cosmic structures of today. The great empty voids, including the Bootes void, are not just random gaps. They are natural consequences of this long cosmic journey. Let's begin this story at the very earliest moments, when the universe was still younger than a fraction of a second. Although the early universe was almost completely smooth, it wasn't perfectly so. Thanks to quantum mechanics, the science that describes the strange behavior of things at the tiniest scales, we know that there must have been tiny bumps and dips in the distribution of matter and energy, even in this smooth soup. These slight fluctuations in density and temperature, far too small to notice with the naked eye, were like gentle ripples on an otherwise still pond. These ripples weren't created by accident. Scientists believe they came from quantum events that took place when the universe was smaller than a single atom. Then came an event known as cosmic inflation, a sudden, dramatic expansion that took place in less than a trillionth of a second. This expansion stretched those microscopic ripples across the universe, turning them into the seeds from which everything else would grow. In some places, there was just a tiny bit more matter than average. In others, there was a tiny bit less. And from these almost invisible differences, the structure of the entire cosmos began to take shape. The force that began shaping the universe using those tiny differences was gravity, the invisible pull that draws things with mass together. Even though the density differences were incredibly small, gravity started working on them right away. In areas with slightly more matter, gravity's pull was a little stronger, and it began pulling in even more matter from nearby regions. These slightly denser spots grew heavier and more crowded over time. Meanwhile, areas with a little less matter experienced weaker gravity. As nearby matter was pulled away toward denser regions, the less dense spots became even emptier. It's a bit like a snowball effect, but with matter being unevenly gathered. The rich, in terms of matter, got richer, while the poor got poorer. Gravity acted like a cosmic vacuum cleaner, sucking material away from the underfilled areas and piling it up in the regions that already had more. Slowly, over billions of years, this process made the dense regions denser and the empty ones emptier, forming clusters of galaxies on one hand and vast empty voids on the other. This process has a name: gravitational instability. It's a key idea in understanding how the universe's structures grow. You can think of it like a delicate house of cards. A small shake, a little tremor, is all it takes to set off a collapse. In the case of the cosmos, those small tremors were the early fluctuations in density. Over time, gravity magnified them. Regions with more matter began to collapse inward, drawing in gas and the mysterious substance known as dark matter. These became the glowing threads and knots of the cosmic web, the filaments of galaxies and giant clusters we see scattered throughout the universe today. At the same time, the less dense areas began to expand faster than the rest of the universe. As gravity pulled material away from them toward the growing dense regions, they lost more and more of their contents. These regions, emptied out by the gravitational hunger of their neighbours, became the cosmic voids. They are not just leftover spaces, they are vital parts of how the universe organised itself. The entire structure of the universe emerged from this simple but powerful process of gravity sorting matter into crowded and empty zones. But there's another major character in this grand story, one we cannot see directly. It's called dark matter. Unlike ordinary matter, dark matter doesn't shine, reflect, or block light. It doesn't interact with electromagnetic forces, which means telescopes can't detect it the way they do stars or gas clouds. But we know dark matter is there because of the way its gravity shapes the motion of galaxies and the structure of space itself. Scientists estimate that dark matter makes up about 85% of all the matter in the universe. That means for every bit of regular matter, like the stuff that forms you, the Earth, the stars, and everything we can see, there's more than 5 times as much dark matter. In the early universe, it was these slightly denser patches of dark matter that first began to clump together. Their gravity pulled in even more dark matter and then drew in ordinary matter as well. These early clumps acted like invisible scaffolding, frameworks on which galaxies and clusters could form and grow. And just as dark matter helped build the dense parts of the universe, it also shaped the empty ones. Areas with less dark matter ended up becoming the voids. Although these voids still contain some dark matter, they have much less of it than the denser filaments and clusters. The presence, or absence, of dark matter played a central role in deciding where galaxies would form and where empty spaces would be left behind. In this way, dark matter quietly set the stage for the grand cosmic drama, directing where light would shine and where darkness would remain. So, the vast emptiness of the Bootes void, and others like it, is not a cosmic accident. It is the natural result of billions of years of subtle differences growing under the influence of gravity, guided by the invisible hand of dark matter and shaped by the expansion of space itself. From the tiniest ripples in a sea of fire, the universe built everything: bright galaxies, majestic clusters, and the dark, silent spaces in between. Besides the pull of gravity, there is another powerful force that plays a major role in shaping the empty spaces of the universe. This force is the ongoing expansion of the cosmos itself. The universe is not still or frozen in place. Ever since the Big Bang, which happened more than 13 billion years ago, space has been stretching outward in all directions. This means that the distance between galaxies is steadily increasing, and the universe keeps getting bigger with time. This cosmic expansion plays 2 different roles depending on the scale you're looking at. On smaller scales, like inside galaxies or within galaxy clusters, gravity is strong enough to hold things together. Even as space stretches, gravity keeps stars, gas, and dark matter clumped into these dense regions. But on much larger scales, such as the vast reaches between galaxy clusters, the expansion of space becomes the stronger force. And here's where the story of the great voids truly begins. In the earliest days of the universe, some regions had just a little bit less matter than others. These slightly emptier areas are what would one day become cosmic voids. As space expanded, these underdense regions stretched faster than the denser ones. The small amount of matter inside them was pulled farther and farther apart, making them even more empty over time. This thinning out of matter due to the universe's expansion is called cosmic dilution. You can picture it like inflating a balloon with tiny dots drawn on it. As the balloon grows, the dots move farther from one another. The dots that started far apart end up even more distant as the balloon continues to inflate. This is exactly what happens inside voids. The stretching of space keeps pushing the few particles inside them away from each other, making the voids grow larger and emptier as time goes on. These voids are not just curious blank spots. They are a natural result of how space itself behaves. The formation of these enormous empty regions, along with the filaments and clusters of galaxies that surround them, is part of a grand cosmic design called the cosmic web. But this vast and beautiful structure didn't form overnight. It took billions upon billions of years. To figure out how it all came together, scientists use incredibly advanced computer simulations. These simulations act like miniature digital versions of the universe. They begin with the conditions believed to exist shortly after the Big Bang: tiny ripples in the density of matter, the mix of ordinary matter and invisible dark matter, and the ever-expanding space. Then, by letting the simulation evolve over billions of years, scientists watch as gravity and expansion interact with these ingredients. Slowly but surely, they see something amazing emerge: long strands of matter called filaments, crowded regions full of galaxies called clusters, and vast open areas almost completely empty, the voids. What's remarkable is that the structures these simulations produce look strikingly similar to what astronomers see when they look into the real night sky. A particularly striking example is the Bootes void. This gigantic and lonely region is one of the emptiest known parts of the universe. Its sheer size and deep emptiness make it stand out, but it's not an accident or a mystery. Simulations show that such voids naturally form when the universe evolves under the laws of physics we already understand, especially when we include the effects of dark matter and dark energy, the invisible forces shaping the cosmos. These simulations are more than just cool visual tools. They let scientists test their ideas. For example, they can change the amount of dark matter or the strength of dark energy in their models to see how the structure of the universe would look different. This helps researchers understand not just what the universe looks like today, but why it looks that way, and what rules were in play from the very beginning. But computer models alone are not enough. Observations of real cosmic voids like the Bootes void are just as important. Astronomers carefully measure the positions of galaxies, figure out how far away they are, and study the rare galaxies that live inside these quiet regions. This data allows scientists to test whether their simulations are accurate. When they see that real voids behave just like the ones in their models, it gives them strong confidence that their understanding of cosmic structure is on the right track. The Bootes void, in particular, stands as one of the most compelling pieces of evidence. Its vast emptiness and massive size are not strange or unexpected. In fact, they are exactly what we would predict if the laws of physics, such as gravity and cosmic expansion, were acting on tiny early universe ripples over billions of years. When we look up at the night sky or peer into the universe through powerful telescopes, what we see is only a tiny part of what's really out there. We see shining stars, swirling galaxies, glowing clouds of gas, and all the things made of what scientists call ordinary matter. This ordinary matter is made up of atoms, like hydrogen, helium, and heavier elements. It's the same stuff that forms planets, people, oceans, trees, and even the air we breathe. And it's the only kind of matter our telescopes can directly detect because it interacts with light. It either reflects it, absorbs it, or gives it off. But here's the astonishing truth revealed by modern cosmology, which is the science of studying the universe as a whole. All of that visible matter, the glowing stars, the galaxies, and everything we can see, is just a small slice of the universe's total matter. Most of the matter in the cosmos is something completely invisible, something mysterious, and yet incredibly powerful. It's called dark matter, and it plays a huge role in shaping the universe. Even though we can't see dark matter, we know it's there. It doesn't shine, reflect, or block light. It doesn't interact with light at all, which is why it's called dark. It's like a ghost that doesn't leave a visual trace. But we can observe its powerful pull on the things we can see. Galaxies, for instance, spin much faster than they should if they were made only of ordinary matter. This tells us that something invisible, something much heavier than all the stars and gas we can detect, is holding them together with its gravity. We also see the light from faraway galaxies bend around invisible mass, a phenomenon called gravitational lensing. This bending only makes sense if there's far more mass than we can see. And perhaps most dramatically, we see the universe forming a giant cosmic web, a huge tangled structure of filaments, clusters, and vast empty regions called voids. None of this could have formed the way it did without dark matter. Scientists estimate that about 85% of all the matter in the universe is dark matter. That means that for every one handful of normal matter, there are about 5 or 6 handfuls of this unseen stuff. It is the main sculptor of the large-scale structure of the universe. The story of how this cosmic structure came to be began shortly after the Big Bang, which happened around 13.8 billion years ago. At that time, the universe was extremely hot, incredibly dense, and mostly smooth. But it wasn't perfectly smooth. There were tiny, barely noticeable differences in how much matter was packed into different regions. Some spots had just a little more matter, while others had slightly less. These tiny differences are believed to have come from quantum fluctuations, tiny ripples, in the universe's earliest moments. What's important is that these early ripples were present in both ordinary matter and dark matter. But because dark matter made up most of the mass, its gravity had a much stronger effect. Where there was a bit more dark matter, its gravity pulled in even more matter. Where there was less, it couldn't pull as effectively. These small differences in dark matter density were the starting points, the seeds, of everything we see today: galaxies, clusters, filaments, and even the empty spaces in between. Over billions of years, gravity began to do its quiet, persistent work. In places where there was a little more dark matter, gravity slowly pulled in more and more material from the surroundings. This process is called gravitational instability. Small clumps of dark matter grew larger and heavier as they gathered more matter around them. Eventually, these clumps formed invisible dark matter halos, like deep gravity wells or invisible mountains, where ordinary matter like gas and dust collected. As that ordinary matter gathered, it cooled down, clumped together, and formed the very first stars and galaxies. The galaxies we see today are still nestled inside those enormous dark matter halos, held there by gravity. Think of the dark matter as the hidden skeleton or scaffolding of the universe. It's what gives galaxies their structure, and what pulls them together into larger formations like galaxy clusters and long filaments that stretch across space. Without dark matter, the universe would be a very different place. The ordinary matter alone wouldn't have had enough gravity to overcome the powerful force of cosmic expansion. Instead of forming stars and galaxies, the matter might have stayed spread out, forming a thin soup of gas, with no bright galaxies or grand structures at all. But dark matter didn't just help form galaxies. It also played a crucial, though less obvious role in creating the universe's vast empty regions, called voids, like the enormous Booty's void. Just as there were spots with slightly more dark matter, there were also regions with slightly less. These places had weaker gravity. So, as matter was being pulled into the denser areas, it was drained out of the underdense ones. Picture this like a cosmic drainage system. The regions with more dark matter acted like gravitational sinks, pulling in material from their surroundings. Meanwhile, the regions with less dark matter were gradually emptied out, as they couldn't hold on to their matter strongly enough. Over time, matter flowed away from these underdense areas and collected in the growing clusters and filaments. This flow of matter sculpted the cosmic web, carving out the vast, dark voids between the glowing galaxies. The Boots void, one of the largest known voids, is a powerful example of this. It likely began as a region with a significantly lower concentration of dark matter than average. Over billions of years, as gravity pulled matter toward the richer, denser areas, this part of the universe was left behind, almost emptied of both dark matter and ordinary matter. Today, it stretches across space as a colossal, hauntingly empty region, a silent monument to the quiet, invisible forces that shaped our cosmos. So, while we cannot see dark matter, it is absolutely essential. It is the silent architect of the universe, the hidden hand that built the galaxies, stretched the filaments, and carved out the voids. Without it, the universe we know, the beautiful, complex web of stars and galaxies, would never have come to be. Even in the deepest and loneliest parts of the universe, like the enormous Booty's void, dark matter has not completely vanished. It is still there, quietly lurking in the shadows, but in much smaller amounts than what we usually find across the universe. While the Booty's void may seem like a vast and empty space, it is not totally hollow. It is simply far more thinly spread out, especially when it comes to dark matter. In places like galaxy clusters or cosmic filaments, the long thread-like structures that connect galaxies, dark matter tends to gather and clump together more tightly. This creates strong gravitational fields that can pull in galaxies' gas and other matter. But inside a void, the dark matter is more spread out and much less dense. This means that the pull of gravity in such areas is weaker and more gentle. This has a big effect on the rare, lonely galaxies that happen to live inside the Bootes void. These galaxies are like islands floating in a quiet sea. They are not surrounded by thick clouds of dark matter like galaxies in busy clusters, nor are they tugged around by the powerful gravity of nearby cosmic structures. Instead, they evolve in peaceful isolation, far from the bustling traffic of the cosmic web. Even though they are alone, these galaxies still have their own small halos of dark matter. These halos act like invisible glue, holding their stars and gas together. Without this dark matter, the galaxies would likely fall apart. Still, the space around them remains calm, gravitationally speaking. It is as if these galaxies exist in a cosmic wilderness, where the usual noise and tugging of gravity is quieted down to a faint whisper. And yet, the presence of dark matter, even in such sparse areas, reminds us that no part of the universe is ever truly untouched by its influence. This unseen material continues to shape the cosmos, even in the most subtle and far-reaching ways. It stretches across the universe like an invisible web, connecting everything with threads of gravity. We can also see the importance of dark matter when we look at the structure of the universe on the larger scales. The cosmic web, with its bright clusters, long filaments, and vast empty voids, is not just made of visible galaxies. All of it is built upon an enormous hidden framework of dark matter. The galaxies we see with our telescopes are just the glowing tips of a much larger invisible iceberg. In contrast, the voids are like cosmic valleys, where this dark matter web is either extremely thin or almost absent. Computer models that simulate how the universe grew after the Big Bang, an event that happened over 13 billion years ago, show us something fascinating. These simulations only match what we observe in real space if we include dark matter in the calculations. When scientists try to simulate the universe using only ordinary matter, like atoms and gas, the results are too flat and uniform. The rich texture of filaments, clusters, and voids simply does not appear. This strong match between what computers predict, when dark matter is included, and what telescopes observe gives scientists some of the most powerful proof that dark matter is real. It shows that this mysterious stuff is not just a theory. It is a vital part of the universe's history and structure. Without it, the universe would not look the way it does. Even the Bootes void itself, a gigantic, almost empty bubble of space that spans hundreds of millions of light years, stands as a silent witness to the influence of dark matter. It shows that dark matter does not only gather and build things up, it also has the power to create vast hollow spaces by pulling matter away, leaving behind darkness and quiet. In this way, dark matter is like a hidden artist, painting the universe not only with bright strokes of stars and galaxies, but also with the wide, shadowy brushstrokes of emptiness. By studying these enormous cosmic voids, astronomers are able to learn more about this mysterious invisible force. Through them, we begin to understand how dark matter shaped the grand design of the universe, both the places where light gathers and the places where it fades into silence. Just as dark matter quietly shapes the structure of the universe by pulling things together with its invisible gravity, there is another mysterious force that works in the opposite direction. This strange energy is known as dark energy, and instead of pulling, it pushes, it stretches space itself. While dark matter gathers things together like a cosmic glue, dark energy acts more like a cosmic wind, blowing everything farther and farther apart. Its influence is especially noticeable in the vast empty spaces of the universe, the cosmic voids, such as the famous Bootes void. Even though we cannot see dark energy, its presence is felt across the entire universe. It fills every corner of space, even in places where there is almost no matter at all. And it plays a major role in how fast the universe is expanding. In fact, it is the main driver of that expansion. While dark matter helps form galaxies and galaxy clusters by pulling matter together with its strong gravitational grip, dark energy stretches the fabric of the universe, causing the space between galaxies, and especially the emptier regions, to grow faster and faster over time. This unexpected and mysterious force was only discovered a few decades ago, and it changed how scientists think about the universe. Before its discovery, astronomers believed that the universe's expansion, which began with the Big Bang around 13.8 billion years ago, should be slowing down because of the gravitational pull of all the matter within it, just like a ball tossed into the air eventually slows and falls back down. But then something astonishing happened in the late 1990s. Two separate teams of astronomers were studying faraway supernovae, which are powerful explosions of dying stars. These explosions serve as standard candles, objects whose brightness we already understand very well. By comparing how bright they appear from Earth, astronomers can figure out how far away they are. They also measured the redshift of the light from these supernovae, which tells us how fast the galaxies that host them are moving away from us. The scientists expected to find that the expansion of the universe was gradually slowing down, but instead they found something shocking. Those distant supernovae were dimmer than expected, which meant they were farther away than they should have been. This surprising result revealed that the expansion of the universe is not slowing down at all, it's actually speeding up. The universe was accelerating. This discovery shook the scientific world and led to a revolutionary idea. There must be a strange, invisible force, what we now call dark energy, pushing the universe apart faster and faster. Unlike dark matter, which gathers in clumps, forming galaxies, clusters, and the great cosmic web, dark energy does not clump at all. Instead, it is smoothly and evenly spread out through the entire universe. Whether you look deep inside a dense galaxy cluster or far out into the emptiest void, you'll find that the amount of dark energy is roughly the same. It fills space like an invisible mist, always there, always exerting its gentle push. This push acts like a kind of anti-gravity. It doesn't pull things together, it pushes them apart. And as the universe expands and becomes more spread out, the influence of dark energy becomes stronger compared to gravity, which gets weaker over larger distances. That means the more time passes, the more powerful dark energy becomes in shaping the future of the cosmos. This has a huge impact on how the large-scale structure of the universe changes, especially in the cosmic voids. In crowded places like galaxy clusters and the long filaments of galaxies, gravity is very strong. The pull from all that mass can resist dark energy's push. These dense regions stay together and even grow by pulling in more matter, with galaxies merging and interacting. Here, dark energy's effects are still present, but they are overpowered by gravity. But in voids, the story is completely different. Voids are enormous regions of space with very little matter, both ordinary matter like stars and gas, and dark matter. Because there is so little material, the gravitational pull in voids is extremely weak. And where gravity is weak, dark energy takes over. It's like trying to stretch a rubber sheet. The spots with knots or weights resist the stretch, but the empty spots stretch easily. Voids, being empty parts of the universe, are the places where dark energy can work most effectively. In fact, voids are expanding even faster than the rest of the universe. While the universe as a whole is growing larger with time, the voids are growing even more quickly. They are becoming bigger, emptier, and darker as dark energy pushes the remaining bits of matter farther apart. This makes voids some of the best natural laboratories for studying dark energy, because the usual interference from gravity is much weaker there. Astronomers can learn a lot about dark energy by observing voids very carefully, measuring how fast they are expanding, how their shapes evolve over time, and how the few lonely galaxies inside them behave. If dark energy is truly constant and unchanging, as suggested by Albert Einstein's idea of the cosmological constant, then voids should expand in a smooth, predictable way. But if dark energy varies over time or across space, then the patterns of void expansion might be very different. So by watching voids and studying their growth, scientists can test important ideas about what dark energy really is and how it might shape the ultimate fate of the universe. One of the best-known voids, the Bootes void, is especially important. It is one of the largest voids ever discovered and has been studied in great detail. Because it is so vast and so empty, it offers a rare and powerful opportunity to see dark energy at work, pushing, stretching, and reshaping the cosmos in silence. As time marches on, a strange and powerful force known as dark energy continues to shape the fate of the universe. This mysterious energy, which pushes space itself apart, is causing the expansion of the universe to speed up more and more as the ages pass. And this acceleration isn't just a small detail. It has enormous consequences for the future of everything we see in the cosmos, including the great empty regions known as cosmic voids. In the far future, as dark energy keeps dominating over gravity, the expansion of the universe will become so rapid that galaxies not tied together by gravity, like those in separate galaxy clusters, will begin to drift apart faster than ever before. They will move away from each other at such great speeds that eventually they will cross a point of no return, a limit beyond which their light can no longer reach us. Bit by bit, they will disappear from view, slipping beyond what we call the observable horizon. It will be as if they are vanishing into the darkness. Right now, galaxies are woven together in a vast and beautiful structure called the cosmic web, a gigantic network made up of long, thread-like filaments of galaxies and clusters. But as the universe stretches and stretches, these cosmic threads will become thinner and more fragile. Over time, the bonds between clusters will weaken, and then they will snap all together. The great web will unravel. The voids, those enormous, already mostly empty regions, will become even more desolate. Over the course of billions and eventually trillions of years, space will grow so wide and so empty that each galaxy, or small group of galaxies still bound together by gravity, will become like a lonely island floating in a dark, silent sea. They will no longer be able to see or communicate with any others, because the light from those distant galaxies will be stretched so much by the expanding space that it will become completely invisible. Its wavelength pulled so far it can no longer be detected. In that distant age, galaxies will age and fade, stars will die, and all around them, the voids will grow even larger and quieter. These vast dark regions will stand as the final symbol of an ever-accelerating universe. Giant oceans of emptiness, where only cold, stretched-out space remains, separating the last flickering lights of dying galaxies that may never know they were once part of a grand cosmic web. Trying to measure something as enormous and empty as the Bootes void might sound like trying to weigh a shadow or catch the wind in your hands. It's not at all like measuring a table with a ruler or calculating the size of a planet with satellites. The Bootes void is a colossal hole in the universe, a region so vast and so empty that it's defined not by what is there, but by what's missing, a large number of galaxies. So, how do astronomers, those tireless explorers of the cosmos, measure something that is mostly made of nothing? The answer lies in clever thinking, incredibly powerful telescopes, and a deep understanding of how light travels through space. It's like solving a mystery by gathering tiny clues scattered across the vast darkness. Scientists don't look directly at the void itself. They collect data from the few lonely galaxies hiding inside it, or from the galaxies surrounding its immense edges. Step by step, they piece together a map of this cosmic emptiness, using faint rays of ancient light that have taken millions, even billions, of years to reach us. This entire effort is a shining example of human curiosity and ingenuity, how science can paint a picture of the grand universe even with only the faintest whispers of light. The most important technique for measuring and mapping such cosmic gaps, like the Bootes void, is something called a galaxy redshift survey. Think of it like this. Imagine you're standing in a thick, foggy forest. You can't see the whole forest, only the trees. To truly understand the shape of the forest, you need to figure out where each tree is, not just side to side, but also how far away each one is from you. That way you can build a full three-dimensional image. In astronomy, galaxies are like those trees. We can see where they are in the sky, like dots on a flat map. But to understand the real shape of the universe, we need to know how far away each galaxy is. Only then can we build a three-dimensional map, one that shows not just galaxies, but also the enormous empty spaces between them. This mapping process starts with very powerful telescopes. These aren't just giant versions of the telescopes you might use in your backyard. They are highly advanced tools built to collect the faintest glimmers of light coming from galaxies unimaginably far away. Some of the biggest and best ground-based telescopes are found in places with clear and dark skies like the dry deserts of Chile, home to the European Southern Observatory's Very Large Telescope, or VLT, or atop the tall mountains of Hawaii, where the Keck Observatory stands. These telescopes have mirrors that are many meters wide, designed to soak in as much light as possible during long observing sessions. But that's not all. Space telescopes like the famous Hubble Space Telescope and the more recent and powerful James Webb Space Telescope also play a vital role. Floating high above Earth's atmosphere, these space telescopes are free from the blurring effects of air and weather. They act like giant cosmic buckets, scooping up ancient light that has travelled across the universe for hundreds of millions or even billions of years. Once a telescope captures the light from a distant galaxy, that light is passed through a special tool called a spectrograph. A spectrograph is like a very advanced prism. It splits the light into its different colours, much like how sunlight becomes a rainbow after shining through raindrops. But instead of just creating a pretty arc of colours, the spectrograph reveals a detailed barcode-like pattern, a spectrum full of dark and bright lines. These lines are extremely important. They are the unique fingerprints of the elements that exist in the galaxy. Every element in the universe, like hydrogen, helium, or oxygen, leaves a distinct mark on light. For example, hydrogen, which is the most common element in space, always shows up with the same exact pattern. When astronomers look at the spectrum of a faraway galaxy, they search for these familiar fingerprints. Now comes the crucial part. If a galaxy were not moving relative to us, the lines would appear exactly where we expect them to be. But the universe is expanding. This means nearly all distant galaxies are moving away from us. When a light source moves away, the light waves stretch out, just like the sound of a train whistle drops in pitch as it speeds away. As light waves stretch, their colour shifts toward the red end of the spectrum. This stretching of light is known as redshift. The more the light is stretched, the more redshifted it becomes, and the faster the galaxy is moving away. Astronomers can measure exactly how much the lines in the spectrum have shifted, and from that, they can calculate the galaxy's speed and distance. Thanks to the work of astronomer Edwin Hubble, we know that the farther away a galaxy is, the faster it appears to be moving away. This rule is known as Hubble's law, and it gives us a cosmic measuring stick. In other words, redshift tells us how far away a galaxy really is. By measuring the redshift of thousands, even millions of galaxies, astronomers can build a huge three-dimensional map of the universe. This map shows where galaxies are thickly clustered together in long filaments, where they form massive superclusters, and most importantly where they are not. Those vast and eerie empty regions like the Booty's Void. To figure out the size and shape of Booty's Void, astronomers must gather an immense amount of information, especially something called redshift data, from not just thousands, but often millions of galaxies spread across huge sections of the sky. But this is no quick task. It takes years of hard, patient work and the efforts of many scientists. Giant sky surveys, such as the Sloan Digital Sky Survey, often called SDSS, and the 2-degree Field Galaxy Redshift Survey, known as 2DFGRS, were designed for this exact purpose. These are massive scientific projects that involve dedicated teams of researchers working over long periods of time, sometimes decades. They scan large parts of the night sky methodically, collecting light from hundreds or even thousands of galaxies at once. They do this using special instruments that break down the light from each galaxy into its component colours. This is called taking a spectrum. From the spectrum of a galaxy, scientists can figure out two very important things. First, they find out exactly where the galaxy is in the sky, its two-dimensional location. Second, they measure how much the galaxy's light has been stretched, or redshifted, as the universe expands. This redshift tells us how far away the galaxy is. When you combine the position and the redshift of millions of galaxies, you get something incredible, a three-dimensional map of the universe. On this map, each galaxy becomes a tiny glowing dot, and when you look at all those dots together, a grand structure starts to emerge. You see long, thread-like strands of galaxies, called filaments, spanning across space. At the points where several filaments intersect, you find dense clumps of galaxies called clusters. But most fascinating of all are the vast gaping regions where galaxies are missing. These are the voids, and among them, the Booty's Void stands out as one of the largest and emptiest ever found. But finding a void like the Booty's Void is not as simple as spotting a black hole or a planet. There is no solid edge or clear line that marks where it begins or ends. Instead, astronomers rely on sophisticated computer programs and mathematical methods to detect these strange regions. They look for places in their galaxy maps where the number of galaxies suddenly drops far below what is expected. It's not just about spotting a gap, it's about measuring just how empty that gap really is. To imagine this, think of plotting every galaxy as a small dot on a computer screen. In most parts of the universe, the screen would be filled with dots, some packed tightly together, others more spread out. But in a cosmic void, you would see huge blank spaces with very few or no dots at all. The Bootes void shows up on these maps as one of the most dramatic examples of emptiness, a vast cosmic bubble where galaxies are incredibly scarce. Scientists can even calculate just how empty it is by comparing its galaxy density to the average density of the universe. This measurement is called the density contrast, and in the case of the Bootes void, this contrast is extremely high. That means it is not just a little empty, it is one of the most underpopulated regions ever discovered in space. To better understand the size and shape of such voids, astronomers use a clever technique called percolation analysis. This method is a bit like watching how water flows through a sponge. Just as water finds its way through all the tiny holes and tunnels in the sponge, this analysis helps scientists see how large empty spaces in the universe are connected. The boundaries of these voids are not sharp. They don't have walls. Instead, the emptiness gradually fades into the surrounding filaments and galaxy clusters. So, the Bootes void is not a perfect sphere. It is more like a huge bubble, shaped by the gravity of the dense cosmic structures around it. It is as if matter has been pulled away from this central region and clumped together to form the walls of the cosmic web. One of the most fascinating challenges in studying the Bootes void is looking at the rare galaxies that actually live inside it. These are sometimes called lonely galaxies, because they exist in isolation, far from the crowded, bustling neighbourhoods where most galaxies live. Their existence proves something important. The Bootes void is not completely empty, it is just incredibly sparse. But these lonely galaxies are very hard to observe. They're extremely far away and often very faint, since they are not forming stars as actively as galaxies in denser regions. To study them, astronomers need to use powerful telescopes and observe for long periods of time to collect enough light. When they measure the redshift of these galaxies, they can confirm that the galaxies truly lie within the Bootes void and are not just lying in front of or behind it by chance. And by studying their shapes, the rate at which they form stars, and the amount of gas they contain, scientists can learn how galaxies behave in these peaceful, gravitationally quiet environments. These isolated galaxies are like natural experiments. They help us understand what happens when a galaxy grows up all alone, untouched by the gravitational battles that happen in crowded cosmic neighbourhoods. Looking ahead, the future of void studies is very exciting. New technologies are being developed that will allow astronomers to map the universe even more clearly. Upcoming galaxy surveys will be able to see fainter and more distant galaxies than ever before. They will cover much wider parts of the sky and detect millions of galaxies, helping us refine our three-dimensional maps of the cosmos. Some of these new instruments can observe light not just in the visible spectrum but also in the infrared. This is important because infrared light can pass through cosmic dust, revealing galaxies that were previously hidden. These tools may even uncover more lonely galaxies hiding inside the Bootes void. In addition, advanced computer programs and artificial intelligence are being created to sort through the enormous mountains of data these surveys will produce. These tools will help scientists quickly find and study the complex patterns in the universe, including voids and filaments. Even the faint whispers of the cosmic microwave background, the ancient light left over from the Big Bang, can help tell us more about voids. As this light travels across the universe, it passes through different cosmic landscapes. When it moves through a huge void like Bootes, its path is slightly altered, creating a tiny cold spot in the cosmic background. This faint effect is known as the integrated Sachs-Wolf effect. Though incredibly subtle and difficult to detect, these cold spots can give scientists yet another clue about the presence of large voids, confirming their influence on the universe's structure. So, measuring the Bootes void is not as simple as pointing a telescope and taking a picture. It is more like solving a vast cosmic puzzle. Astronomers must gather the faintest light from millions of galaxies, carefully measure how far away they are, and then use powerful mathematics and computer models to see the universe's grand design. The result is a beautiful, sponge-like structure filled with threads of galaxies, glowing clusters, and enormous mysterious holes like the Booty's void. Imagine you're standing beside a railway track on a quiet day. In the distance, you hear the sound of a train horn. As the train rushes toward you, the horn seems to get higher and sharper in pitch. But as soon as the train speeds past you and moves away, that same horn suddenly sounds lower and deeper. This shift in the sound's pitch isn't just your imagination. It's a real physical effect called the Doppler effect. It happens because the movement of the train changes the way the sound waves reach your ears. When the train comes closer, the sound waves get squeezed together, like ripples in a pond when something fast moves across it. The waves arrive more frequently, with shorter distances between them. This is called a shorter wavelength, and we hear a higher pitch. When the train moves away, the waves are stretched out, creating longer wavelengths, and we hear a lower pitch. This everyday experience with sound is just a small glimpse of something much bigger and more powerful happening in the universe. A similar effect applies not just to sound, but also to light, and this version plays a major role in how astronomers explore the vast reaches of space. Instead of hearing the change, scientists see the change in light. This version of the Doppler effect is known as redshift, and it is one of the most important tools astronomers use to figure out how far away galaxies are and how fast the universe is expanding. It even helps us study huge empty regions in space, like the enormous Booty's void. To really understand redshift, let's first think about light itself. Light travels in waves, similar to how ripples spread out in water. Each wave has a wavelength, which is the distance between the peaks of two waves. The color of light depends on this wavelength. For example, red light has longer wavelengths, while blue light has shorter ones. The full range of wavelengths, from extremely long ones like radio waves to extremely short ones like gamma rays, is called the electromagnetic spectrum. Our eyes can only see a small slice of this spectrum. This visible slice contains all the colors of the rainbow, from red, with the longest visible wavelengths, to violet with the shortest. But most light in the universe is invisible to us, and astronomers need special instruments to detect it. Now, imagine applying the Doppler effect to light waves instead of sound. When a light-emitting object, like a star or a galaxy, is moving away from us, the light it sends out gets stretched during its journey. The longer these waves become, the more they shift toward the red end of the visible spectrum. This is what we call redshift. On the other hand, if something is moving toward us, its light waves get compressed, the wavelengths become shorter, and the light shifts toward the blue end of the spectrum. That's called blue shift. In most cases, especially when we're looking at very distant galaxies, we see redshift, because almost all of them are moving away from us. This isn't just because the galaxies themselves are speeding through space. In fact, something even more fascinating is happening. Space itself is expanding. Think of this using a balloon. Imagine drawing tiny dots all over a deflated balloon. As you blow it up, the surface stretches and all the dots move farther apart from each other. But notice, they're not sliding across the surface. They're staying where they are, and it's the balloon's surface that's doing the stretching. This is similar to what's happening in the universe. Galaxies aren't really flying away like rockets. Instead, the fabric of space between them is growing larger. As this space stretches, the light traveling through it also gets stretched, just like the balloon's surface. This stretching of light due to the expansion of the universe is called cosmological redshift, and it's what we mostly observe when looking at galaxies that are billions of light years away. The more distant the galaxy, the longer its light has been travelling, and the more space has stretched in that time. That means we see a greater redshift the farther away something is. This idea is directly tied to the universe's steady growth since the Big Bang, which happened around 13.8 billion years ago. But how do astronomers measure this redshift? They use a device called a spectrograph, which is connected to a telescope. When the telescope captures light from a distant galaxy, the spectrograph breaks that light into its separate colours, creating a spectrum much like a rainbow. Within this spectrum, astronomers search for specific spectral lines, special patterns that act like barcodes for different chemical elements. Take hydrogen, for example. It is the most common element in the universe, and it produces a very specific pattern of lines when it emits or absorbs light. Scientists already know exactly what this hydrogen barcode looks like from experiments here on Earth. Now, when they observe the same pattern in a distant galaxy, those spectral lines will appear shifted toward the red part of the spectrum if the galaxy is moving away. It's like hearing a familiar song being played, but every note is slightly lower. The pattern is still there, but it's been moved, and the amount by which these lines have shifted gives astronomers a number they call the redshift parameter, written as the letter Z. The larger the Z value, the more the light is stretched, and that tells us the galaxy is moving away faster and is farther away in the cosmos. Some galaxies show redshifts so large that their light has been travelling for over 10 billion years before reaching Earth. That means we're not just seeing them far away, we're seeing them as they were billions of years ago, providing a time-travelling glimpse into the early universe. In the late 1920s, an American astronomer named Edwin Hubble made a discovery that forever changed how we understand the universe. By carefully studying the light from distant galaxies, Hubble noticed something astonishing. Almost every galaxy beyond our local group was moving away from us. And even more surprising, the farther away a galaxy was, the faster it seemed to be speeding off into the distance. This incredible observation became known as Hubble's law. It revealed a simple but powerful truth. A galaxy's speed of recession, how quickly it moves away from us, is directly linked to how far away it is. In other words, if one galaxy is twice as far away as another, it will also be moving away twice as fast, and its light will be stretched out, or redshifted, twice as much. This idea was revolutionary. Before Hubble's discovery, measuring how far away a galaxy was felt like trying to measure the ocean with a teacup. Slow, uncertain, and nearly impossible at great distances. But now, thanks to redshift, astronomers had a reliable cosmic ruler. They could look at the light from a galaxy, measure how much it was redshifted, and figure out how far away it was. No tape measure needed. Redshift had become the most powerful tool for measuring distances in the vast universe beyond our nearby galactic neighbours. But redshift doesn't just help us figure out distance, it also acts like a time machine. That's because light, even though it moves extremely fast, about 300,000 kilometers per second, still takes time to travel. So when we look at a faraway galaxy, we're not seeing it as it is right now. We're seeing it as it was when the light first left it, millions or even billions of years ago. For example, if a galaxy has a redshift of 1, that means its light has been travelling for around 7 to 8 billion years before reaching our telescopes. That shows us the galaxy as it looked when the universe was only about half as old as it is today. Now imagine galaxies with even higher redshifts, say 8 or 10. These are some of the most distant galaxies ever seen, and their light has been travelling across space for more than 13 billion years. We see them not as mature, majestic galaxies, but as tiny glowing seeds of what would eventually become the galaxies of today. These high redshift galaxies give us a direct window into the early universe, only a few 100 million years after the Big Bang, when the first stars and galaxies were just beginning to form. So redshift is not just a ruler, it's also a record of time, allowing astronomers to look back into the past, to witness the birth and evolution of galaxies over billions of years. But there's even more. Redshift is absolutely essential for mapping out the true shape and structure of the universe. Without it, our maps of space would be like looking at a world map with all the buildings squashed into a single flat picture. No way to tell which are near, which are far, or where the empty spaces are. You might know a building exists, but not whether it's a towering skyscraper or a tiny shed hiding behind it. Redshift adds that missing third dimension, depth. With it, astronomers can take a flat image of the sky and turn it into a three-dimensional model of the cosmic web, a vast network of filaments, clusters, and giant empty areas known as cosmic voids. On these 3D redshift maps, the universe reveals its structure. Filaments look like long, glowing strings of galaxies stretched out across space. At the intersections of these strings are galaxy clusters, bright crowded knots of stars and galaxies, and in between them lie the great empty spaces, the cosmic voids. One of the most famous of these is the Bootes void. It was discovered when astronomers noticed something odd, a big blank area in their redshift data. They were scanning a region of the sky in the direction of the constellation Bootes when they found that, over a certain range of redshifts and therefore distances, there were far fewer galaxies than expected. It was as if someone had carved a giant invisible hole into the universe. This eerie absence turned out to be the Bootes void, a colossal cosmic cavern so large and empty it still amazes scientists to this day. Thanks to redshift, astronomers could pinpoint the edges of this void, trace its shape, and measure its size, helping us better understand how galaxies and empty spaces are arranged across the universe. Now, redshift is incredibly useful, but it's not completely straightforward. Galaxies don't just drift along quietly with the expansion of the universe. Sometimes they have their own quirky motions, known as peculiar velocities. These are extra movements caused by nearby gravitational pulls, especially in crowded places like galaxy clusters. Because of this, a nearby galaxy might appear a little more redshifted, or even blue-shifted, moving toward us, depending on how it's moving locally. But for galaxies that are very far away, these small individual motions hardly matter. In those distant realms, the expansion of the universe itself is the overwhelming factor that stretches the light, and redshift becomes a clean, reliable measure of how far away something is. That's why astronomers use it with great confidence to map the structure of the cosmos. Our journey to understand the universe begins right where we are, on the planet we call Earth. Earth is not floating alone in space. It travels in a steady orbit around a glowing ball of fire we know as the Sun. But even the Sun is not unique. It is just one among hundreds of billions of stars that live within a much larger community, a grand spiral-shaped galaxy called the Milky Way. The Milky Way is like a cosmic city made of stars, swirling clouds of gas and fine dust, all arranged in a magnificent spiral pattern. From one end of this galaxy to the other, it stretches across a distance of about 100,000 light-years. That means if a beam of light were to travel from one edge of the Milky Way to the opposite side, it would take 100,000 years to make the journey. That is how incredibly huge our galaxy is. For many centuries, people believed the Milky Way was the whole universe. It was all we could see in the night sky, a glowing band stretching from horizon to horizon. Our tools were limited, and our ideas about space were still young. But as our telescopes improved and our understanding of the heavens deepened, a great realization dawned. The Milky Way is not the entire universe. It is just one galaxy among many, countless others scattered across the cosmos in all directions. To fully understand something as mysterious and enormous as the Bootes void, a vast, nearly empty region of space, we must take several giant steps away from our galaxy and explore the larger and larger structures that make up the universe. The Bootes void is not just a blank patch in space. It plays an important role in shaping the universe's large-scale architecture. It marks the emptier regions that lie between cosmic structures and reminds us that the universe is not smooth and even, but wildly uneven, filled with clumps of galaxies and vast gaps of almost nothing at all. The first step beyond the Milky Way takes us into our galactic neighborhood, which scientists call the local group. This group is like a small family of galaxies bound together by gravity. It includes our Milky Way, the Andromeda Galaxy, which is even bigger than our own, and the Triangulum Galaxy, along with around 50 smaller dwarf galaxies. Altogether, the local group stretches across a region roughly 10 million light-years wide. You can think of it like a small town in the universe. The Milky Way and Andromeda are the big cities, while the dwarf galaxies are the quiet little villages. These galaxies sometimes interact with each other, and in the distant future, billions of years from now, Andromeda and the Milky Way are expected to collide and merge into one giant galaxy. But even the local group is just a small part of something much larger. When we look farther out, we find massive gatherings of galaxies called galaxy clusters. These are the true giants among cosmic structures, collections of hundreds or even thousands of galaxies, all held together by their combined gravitational pull. These galaxy clusters are like bustling cities in space, each one teeming with galactic inhabitants. Galaxy clusters can be enormous, stretching across distances from several million to tens of millions of light-years. A nearby example is the Virgo cluster, which is slowly pulling our local group toward it. The Virgo cluster contains over 1,000 galaxies and spans roughly 10 million light-years. Then there's the Coma cluster, which is even larger and more crowded, containing thousands of galaxies packed close together. But it's not just galaxies that make up these clusters. Between the galaxies lies a vast ocean of hot gas, so heated that it shines in powerful X-rays. Even more mysteriously, most of a cluster's mass is not made of stars or gas. It is made of dark matter, a strange and invisible substance that cannot be seen but exerts a strong gravitational pull. Without dark matter, the gravity of the galaxies alone would not be strong enough to hold these massive clusters together. Galaxy clusters form in the densest parts of the young universe. Gravity pulled matter together, forming these dense knots that attracted more and more galaxies over billions of years. Even now, galaxy clusters continue to grow as more galaxies fall into them, along thin, thread-like streams of matter called filaments. Beyond galaxy clusters lies an even more impressive layer of structure, the superclusters. These are not simple collections of galaxies or clusters. They are enormous networks of many galaxy groups, clusters, and individual galaxies stretched out like tangled threads across hundreds of millions of light years. Our own local group, the Virgo cluster, and many other nearby clusters are all part of a gigantic supercluster known as Laniakea, a Hawaiian word meaning immense heaven. The Laniakea supercluster stretches across about 500 million light years and contains the mass of more than 100,000 galaxies the size of the Milky Way. All of the galaxies inside Laniakea are slowly drifting inward, pulled by the gravity of a mysterious region known as the Great Attractor, an invisible force tugging on everything within the supercluster. But Laniakea is not the only supercluster in the universe. Others, such as the Perseus-Pisces supercluster, the Coma supercluster, and the Hercules supercluster, also span vast distances. These superclusters are like the glowing continents of the universe, where matter has gathered into the brightest and densest parts of the cosmic landscape. They are not tightly bound like clusters are, but they do share a common flow, a gentle, gravitational pull that connects their many parts. All these structures, galaxies, clusters, and superclusters, are part of something even bigger and more breathtaking, the cosmic web. This is the grand architecture of the universe, the ultimate map of matter on the largest scale we can observe. The cosmic web stretches across the entire observable universe, forming an intricate network that resembles a vast three-dimensional spider web or a sponge with endless tunnels and threads. The cosmic web is made up of three main parts. First, there are the filaments, long thread-like chains of galaxies that can stretch for hundreds of millions of light years. Next are the nodes, or clusters, which sit at the intersections of these filaments, where matter is densest and galaxies gather in great numbers. And finally, there are the voids, enormous regions of space with very few galaxies, like great cosmic deserts lying between the bustling galactic highways. Superclusters, like Laniakea, make up the brightest and most massive parts of the filaments and nodes. These are the spots where gravity has pulled matter together most strongly. And in between these glowing strands lie the voids, such as the Bootes void, which help define the shape and structure of the universe by showing us where matter is absent. So, where exactly does the Bootes void belong in the grand structure of the universe? To understand this, we need to zoom out, far beyond planets, stars, galaxies, and even clusters of galaxies. The Bootes void is not a galaxy. It is not part of a small group of galaxies, nor is it a massive galaxy cluster, or even one of the giant superclusters that hold many clusters together. In fact, it is the complete opposite of all those things. The Bootes void is one of the largest and most dramatic examples of what scientists call a cosmic void. Cosmic voids are vast, empty regions in the universe, regions where there is very little matter, very few galaxies, and almost no activity. These voids make up one of the three main building blocks of the cosmic web, which is the huge interconnected structure that forms the universe on the largest scales. While galaxies, clusters, and superclusters form the threads and knots of this web, voids are the enormous empty spaces in between. The Bootes void is like a gigantic bubble of nothingness. It stretches across a staggering distance, roughly 250 million light-years from one side to the other. That's larger than many entire superclusters, although a few of the very biggest superclusters can still be bigger. Still, the sheer scale of the Bootes void highlights just how empty and vast it truly is. While a supercluster is a massive pileup of matter, the Bootes void is a massive absence of matter. If the universe were a map of continents and oceans, the continents would be the dense filaments and superclusters, while the Bootes void would be one of the most enormous oceans of emptiness in between. It acts like a huge buffer zone, sitting quietly between the bustling continents of galaxies. It is not just an empty space chosen at random, it is an emptiness carved out by gravity itself. Over billions of years, the gravity of the surrounding structures slowly pulled matter away from the centre of the void, making it even emptier than it once was. Because of this, the Boots void plays an important role in shaping the cosmic web. It helps define the edges of the largest structures in the universe. Its position is not just a curiosity, it's a clue to how the entire universe is arranged. The void reminds us that the universe is not filled evenly with matter. Instead, matter is gathered in thick clumps, and between those clumps lie vast, silent gaps like the Boots void. Understanding where the Boots void fits in this cosmic puzzle helps us better understand the universe itself, from our tiny planet to the farthest reaches of space. It teaches us about how galaxies form, how gravity works over vast distances, and how the universe grows and changes over time. The very pattern of the universe, this grand web of filaments, clusters and voids, was shaped by two powerful forces: gravity, which pulls matter together, and the expansion of space, which pushes everything apart. The Boots void, because of its enormous size and incredible emptiness, gives astronomers a special place to study these forces in action. Since it has so little matter, the effects of gravity are weak there, which means it's a great place to observe the mysterious force known as dark energy, the force that is making the universe expand faster and faster. By studying places like the Boots void, far beyond our galaxy, and even beyond the largest galaxy clusters, we begin to see the universe not just as a place full of stars and galaxies, but also as a place of vast, quiet, breathtaking emptiness. This emptiness is not meaningless. It is part of the design, helping shape the universe just as much as the matter does. And in this beautiful, delicate balance between fullness and emptiness, we find a deeper, more awe-inspiring understanding of the cosmos. The universe is not packed solid with galaxies, clusters and superclusters. Mixed in with those are vast stretches of almost nothing. These regions are known as cosmic voids, huge areas of space where there are very few galaxies and very little ordinary matter. Though we often focus on the bright parts of the universe, the galaxies, the stars and the glowing clouds of gas, the empty parts are just as important. They are key pieces of the puzzle that make up the cosmic web, the universe's enormous sponge-like structure. While the Boots void stands out because of how gigantic it is and how early it was discovered, it is not alone. Many other voids exist across the universe. Each one of these empty places helps scientists understand how the universe is put together and how it has changed over time. By studying other voids, researchers can see that the Boots void is part of a larger pattern, not a strange exception. These studies reveal the hidden forces that shape the universe and explain how such gigantic empty spaces could come to exist in the first place. Cosmic voids share some common traits. First and foremost, they are places where there are far fewer galaxies and much less matter than in the average parts of the universe. They are not completely empty. Some particles and a few galaxies are still inside them, but their overall content is extremely thin. In fact, the amount of regular matter inside a typical void might be only 1/10, or even less, of what you'd find elsewhere in the universe. Voids can be tens of millions to hundreds of millions of light years across. Some are so large that they form bubble-like holes in the cosmic web. Though mostly free of stars and gas, voids still contain dark matter, although in small amounts. More importantly, they are filled with dark energy, a mysterious force that pushes the universe apart. Dark energy is spread out evenly across space, and inside voids, where gravity is weak, its effect becomes more noticeable. As a result, voids slowly grow larger over time, as dark energy pushes matter farther away from the centre. Even inside these giant quiet regions, a few lonely galaxies can still be found. These isolated galaxies live far from their neighbours, and often evolve differently than those in crowded clusters. Because they are not shaped by frequent interactions or mergers, they can offer unique clues about galaxy evolution. Although voids have some things in common, they are not all the same. They vary widely in shape, size and structure. Some, like the Boots void, are gigantic. The Boots void is about 250 million light-years wide, making it one of the biggest voids ever found. Others are smaller, perhaps only 50 or 100 million light-years across. The size of a void often depends on its surroundings. Larger voids are usually found between bigger superclusters of galaxies. Their shapes are rarely neat or spherical. Instead, they tend to be stretched out, lumpy, or twisted, shaped over billions of years by the way gravity has pulled matter away from their centers. Some voids are fairly isolated, while others connect with neighboring voids to form huge empty regions, almost like tunnels or caves in the structure of the universe. These differences in size and shape tell scientists a lot about how the universe started and how gravity and dark energy have sculpted it over time. They offer valuable clues about the very early conditions of the cosmos and help refine our models of how galaxies formed and moved. One of the closest voids to Earth is called the local void. Unlike the Bootes void, which is far away, the local void lies right next to our own galactic neighborhood. It separates our local group of galaxies, which includes both the Milky Way and the Andromeda Galaxy, from other nearby galaxy clusters. This nearby void doesn't just sit quietly in space, it actually affects how our group of galaxies moves. Because it contains so little matter, the local void does not pull on us with much gravitational force. Meanwhile, denser regions like the Virgo cluster do pull on us more strongly. As a result, we are slowly moving away from the local void and toward these more crowded areas. This motion is part of what astronomers call our peculiar velocity, the way our galaxy moves through space beyond the basic expansion of the universe. The local void is not as huge as the Bootes void, but it is still very large, stretching perhaps 100 to 150 million light-years across. And because it is so close to us, it plays an important role in our understanding of how empty space affects motion in the universe. Another vast and nearly empty region is known as the northern local supervoid, also called the sculptor void. This void is much larger than the local void and is roughly spherical in shape. It measures about 300 million light-years in diameter and lies not far from our own local group. Though it has not gained as much attention as the Bootes void, it is another clear example of the universe's sponge-like layout, full of both filled and empty regions. Studying this supervoid helps astronomers better understand how voids are arranged across the cosmos and how they influence the movements of nearby galaxies. Perhaps the most fascinating and mysterious void being studied today is the Eridanus supervoid. This particular void might help explain a strange feature in the cosmic microwave background, or CMB, the ancient light left over from the Big Bang, which is spread across the entire sky. Although the CMB is mostly the same everywhere, it has small temperature differences in different areas. One region, known as the CMB cold spot, is unusually cold, colder than scientists would expect. One leading idea is that a gigantic cosmic void lies in that direction. If true, this Eridanus supervoid could be around 1 billion light-years across, possibly making it even larger than the Bootes void. The theory is that as light from the Big Bang passed through this enormous empty region, it lost a tiny bit of energy, making the cold spot appear cooler than the surrounding areas. Scientists are still studying this region carefully, using galaxy surveys and three-dimensional maps to see whether this supervoid is real and how large it actually is. If it exists, the Eridanus supervoid would be one of the largest structures ever discovered, and an incredible example of how even the emptiest places in the universe can shape what we see, all the way back to the beginning of time. All cosmic voids, whether we are talking about the local void close to our own Milky Way, the enormous Bootes void, or the mysterious and still debated Eridanus supervoid, have a lot in common. These vast, nearly empty regions of space were shaped by the same forces that built the entire universe. In the very beginning, just after the Big Bang, the universe was filled with tiny ripples. Some places were a little denser, while others were a bit emptier. The areas that started off slightly emptier didn't attract much matter. Instead, gravity pulled matter away from them and into the denser regions, which grew into galaxies, clusters, and the long filaments that form the cosmic web. As billions of years passed, the universe kept expanding, stretching everything farther apart. In the voids, where there was already very little matter, this expansion was even more dramatic. On top of that, an invisible force known as dark energy started to dominate. It acts like a kind of anti-gravity, pushing the universe to expand faster and faster, and where there's not much matter, like in voids, dark energy has the upper hand. This makes these already empty regions grow even emptier. Even so, voids are not completely deserted. Scattered within them are lonely galaxies, individual islands of stars that formed far away from the crowded cities of galaxies we see in clusters. These isolated galaxies are especially interesting to astronomers because they show how galaxies grow and change when they're left all alone, far from the influence of other galaxies. So in the big picture, all voids, big or small, are the result of the same cosmic recipe. They are part of the universe's large-scale structure, a web-like pattern where matter clumps together in some places and is nearly absent in others. Voids are not random gaps. They are physical evidence of how gravity, dark matter and dark energy work together on the largest possible scales. But despite these similarities, not all voids are exactly the same. One of the biggest differences is simply their size. The Bootes void, for example, is absolutely gigantic. It stands out as one of the largest known voids in the entire universe. Its enormous scale shocked astronomers when it was first discovered in the year 1981. While many other voids are much smaller, the Bootes void's vastness makes it special. Another difference lies in how empty each void is. While all voids have fewer galaxies than average, some are just a bit underdense, while others, like Bootes, are almost entirely empty. This difference depends on how they formed and what the surrounding environment is like. The Bootes void is also unique because the few galaxies it does contain are extremely isolated. Perhaps the most isolated galaxies we know of. These lonely wanderers are truly cut off from the rest of the universe, floating in silence across hundreds of millions of light-years of darkness. The Bootes void also holds a special place in the history of astronomy. It was one of the first giant voids ever discovered, and gave scientists their first dramatic clue that the universe was not just filled with stars and galaxies, but also with vast spaces of almost nothing. Its discovery helped confirm the idea of the cosmic web, a huge interconnected pattern where matter forms long strands and empty bubbles. This realization marked a turning point, pushing astronomers to start mapping out the full structure of the universe and search for other voids like it. Studying multiple voids across the universe is incredibly important. By comparing them, looking at how many there are, how big they tend to be, how empty they are, and where they are located, scientists can test their theories about how the universe formed and grew. If the models we use to understand the cosmos can't explain voids properly, then those models need to be improved. Voids, especially the most extreme ones like the Bootes void, or the cold spot in the cosmic microwave background, are powerful tools for learning more about dark energy. By observing how fast these empty regions expand and how the few galaxies inside them evolve, scientists gather important clues about what dark energy is and how it works. Voids are also key to understanding how a galaxy's environment affects its life. Galaxies in crowded places like clusters interact with their neighbours all the time, through gravity, collisions and bursts of radiation. But galaxies and voids live a quiet, lonely life. Comparing the two helps us understand how galaxies grow differently, depending on where they live. And there's even more. Astronomers are now looking at how individual voids might be connected, forming enormous networks of emptiness, huge tunnels and channels of space with almost no matter at all. This shows that voids aren't just isolated pockets. They're part of an even bigger system, a complex structure of empty and filled regions that stretches across the universe like a cosmic lacework. These giant gaps aren't just nothing. They are dynamic, active regions where the effects of cosmic expansion are most visible. The Bootes void, while an extraordinary and separate entity, is just one piece of this grand puzzle. It reminds us that the universe is not just a place of stars and galaxies. It is also a place where vast emptiness plays an essential role in the design of everything. In the silent, haunting vastness of the Bootes void, we find not a void of meaning, but a profound part of the universe's story, where gravity, dark matter and dark energy shape even the quietest corners of existence.